Welcome to this course on Wi-Fi penetration testing. This course is an introductory course in Wi-Fi penetration testing. It introduces you to wireless systems and Wi-Fi systems in particular, followed by security and Wi-Fi security. Then goes through various information about Wi-Fi security to help you to understand Wi-Fi security. Unlike wireline systems, wireless systems have certain additional security related challenges. For example, because wireless is an inherently broadcast medium, so it's a bit more difficult. It's not impossible, but there are those challenges, and it's good to be aware of those challenges when trying to design security for wireless systems. Various security mechanisms will be looked into, and these include things like WEP, WPA, both PSK or personal mode, and enterprise mode. Now, it turns out that Wi-Fi security historically has been very weak. There are reasons for that, so it is another sub-objective then within this objective of understanding Wi-Fi security, where we would be giving some reasons why this was the case. And another thing that we'll look into then is vulnerabilities and then exploits related to Wi-Fi security. Because for you to be able to do Wi-Fi penetration testing, you need to understand the vulnerabilities of Wi-Fi systems and how they are exploited. This understanding of exploits will not be just purely theoretical, but also practical. So considerable time will be spent to demonstrate various practical exploits that can be done on Wi-Fi systems. And these will be using certain hardware equipment, software equipment, and so on. And these will be covered in the videos later on. Besides understanding Wi-Fi security, we want to understand, as mentioned, how to exploit Wi-Fi system vulnerabilities. There are certain principles behind these exploitations, and so we will cover these and the related theory of what's going on, because we don't want you to be just some kind of like script kiddie, just running scripts without understanding what's happening. The problem with being a pure script kiddie with a limited understanding of what's happening is that whenever there's some change, something a bit different, something unexpected, you might have trouble coping with that. So once you understand the principles and the theory, then when there's some changes, for example, the Wi-Fi access points might start using certain defense mechanisms. Let's say against WPS, we will see that certain defense mechanisms have evolved over time. Then you will be better able to deal with these unexpected defense mechanisms and perhaps find ways around them as well. So you can be creative even while using these tools that we will show you. And of course, so we will show the tools as part of the course. I would be trying to cover the various topics and the tools from a view of trying to help you to understand what really is happening, rather than just giving like certain recipes that you don't understand. This will best equip you to deal with whatever variations, whatever changes you might encounter when you're actually attempting these exploits. Now, I should mention also that you have to be careful about what is legal or what's not legal, and generally in many countries you need permission from the owner of the Wi-Fi network in order to be using some of these tools and doing some of these things that we'll be showing. And then besides looking at the tools, then on the other side, the third major objective will be to understand how to best protect Wi-Fi systems. You don't just want to break into them. The reason for the penetration testing, after all, is to help the organization that's deploying this Wi-Fi system to better understand weaknesses in the system and then how they can strengthen the security of the system. So eventually we'll end up with seeing and understanding why WPA2 Enterprise is the best way to secure Wi-Fi systems. In practice, there are even if you're using WPA2 Enterprise, there are different ways of going about it because it reuses things that are more general, so things like EAP, Extensible Authentication Protocol. And EAP is so flexible, it can be used with certain weak authentication protocols. It also could be used without end-to-end encryption. So there are certain ways of using EAP that are recommended and are stronger. Now, having said that, WPA2 Enterprise is not always practical because not many people know how to set up a radio server. So we do have a secondary recommendation, and if WPA2 Enterprise is overkill for a particular organization, WPA2 PSK is still okay. It's not as secure, and we'll see why. But the main thing is a strong password. So it should be something that's basically impossible to find in any of the word lists that might be out there, or even combinations or variations of words in word lists. And then turn off WPS. Never use it. And also never use WEP. So having seen these three objectives then, which is understanding Wi-Fi security, understanding how to exploit Wi-Fi system vulnerabilities, and then understanding how to best protect Wi-Fi systems, these three objectives then will become like three legs of a table, and that will be your ability to perform Wi-Fi penetration testing. So that enables you to do the penetration testing and then to write appropriate reports and make recommendations based on the information you get here and also related information that you should be able to then find out on your own. We continued the introduction of this course by giving an overview of what we'll be covering. Well, firstly, just to say a few words about penetration testing in general and Wi-Fi penetration testing. The main idea, we had talked about objectives in the previous video. So the main thing is that we want to help improve the security of Wi-Fi systems. And that's why we're going through all of these details and information. And that's why we demonstrate the breaking of weak security mechanisms, kind of learning by doing. So it's not just, as I mentioned in the previous video, it's not just about running certain scripts without understanding. So not just blindly running certain scripts, but to understand principles and what's behind it, so that in case you come across any problems, you know how to deal with them, hopefully, or you can Google to deal with them. And at the same time, so on the one hand, it's about demonstrating that maybe your client hires you to do Wi-Fi penetration testing, and you demonstrate that they might have certain flaws in their deployment. So the passphrase, let's say, is something that you can retrieve using some of these techniques, and then you can recommend stronger security mechanisms, ways that make it almost impossible, practically speaking, to break their system to get access. Now, talking about breaking in and getting passphrases and doing things in a system, there are certain legal implications, of course, doing Wi-Fi penetration testing or any penetration testing in general. So this is something where you should consult your lawyer for legal advice. This course is definitely not providing legal advice, just some general information and technical information. So just very broadly speaking, in most countries, it's illegal to be accessing Wi-Fi systems that you are not authorized to access. So even if you say, well, my neighbor didn't secure their system, there was no password, it was just open, doors were wide open, I just walked in, I used that system, you could be legally in the wrong because there might be laws against it. So it's best to check. I am Daniel Wong, and I'll be presenting this course. I have a PhD in electrical engineering. Now you might say, well, how is electrical engineering related to that? Well, wireless communications has a lot of interesting electrical engineering related topics and areas, how wireless signals get through the air and from transmitter to receiver and so on. So that's where electrical engineering comes in, but it's that's also the computer science aspects as well. And I have many years of experience in wireless systems and teaching wireless systems. I also have various certifications such as the WCP from IEEE, Cisco CCNP. It might have expired sometime. I need to. I'm not claiming that it's still unexpired. And then I'm involved in various IEEE activities as well. That's Institute of Electrical and Electronics Engineering. IEEE is the organization that created the standards for Wi-Fi systems, in particular IEEE 802.11. The course outline is as follows. The beginning part of the course will provide background information on wireless systems. There are many different kinds of wireless systems, so it kind of helps to know where Wi-Fi systems fit into the whole universe of wireless systems that are out there. We want to know the different characteristics compared with other wireless systems, so that gives us some perspective and context for talking about Wi-Fi systems. Then we go into talking more specifically about Wi-Fi systems, the different variations, the frequency bands and things, especially where it relates to things that we would be needing to understand in order to better appreciate what we do in penetration testing of Wi-Fi systems. So, for example, we talk about things like monitor mode, which might often not be described in some general course on Wi-Fi, unless we're talking about Wi-Fi security and having certain capabilities from things like monitor mode. There will be some brief introduction and coverage of network security principles and practice, but this is by itself a very broad area, so we wouldn't be able to get into a lot of detail there either. Again, we focus on aspects that then are related to things that we will be doing in terms of the practical demonstrations. And so just like our coverage of Wi-Fi systems, also we'll pick aspects that are especially relevant to the rest of the course. We will continue talking about the outline in the next video, and particularly about some of these Wi-Fi security systems that are found in Wi-Fi systems. Before we move on to talk about Wi-Fi systems and their security related issues in more detail, we will briefly introduce wireless systems, because Wi-Fi systems are a subcategory of wireless systems, so it helps to have an overall picture of what wireless systems are about. More specifically, we're talking about wireless communication systems. So it's not just any wireless systems. We're not talking about garage door openers, for example, though those you can also say have security issues. We're talking about wireless communication systems. And what are they? Why do we call them wireless systems in the first place? The reason is that wireline systems are more prevalent, more traditional in a way. They are perhaps not as glamorous and so don't get as much attention, but the old phone network is a good example of a wireline system that just works and delivers the goods, so to speak. Wireline communications are around both for voice and data and have been around for a long time. So the question is then, why do we want to have wireless alternatives? The main difference here then is that wireless allows the communication device to be untethered, not tied down somewhere. The classic example might be for wireline, you have a phone, and so the phone number is related to that line and that physical location where that line comes in and plugs into a device. The communication endpoint then is related to that physical location because of the position of the wires and the wire just ending there. Wireless, on the other hand, allows a person to move around, to roam, to be tetherless, and that is a great attraction for many of us, so much so that we are willing to give up some of the kind of data rates and reliability and performance we can get with wireline systems in order to use wireless systems that may be a generation or two behind in terms of achievable data rates and quality and reliability. Categories of wireless systems include fixed versus mobile. So here we're talking about some very broad categories of the kinds of wireless systems that are around, because there are many wireless systems, and we want to talk about Wi-Fi systems, and they are belonging to a specific categorization. So we're still taking a look at the overall picture. Fixed versus mobile. Fixed wireless systems are those that, even though we had talked about a benefit of wireless being the tetherless aspect and moving around, with fixed, the endpoint of the network might be in a fixed location. The amount of mobility you get with it is not as great as with so-called mobile wireless systems. And that's why mobile wireless systems perhaps are more glamorous. Fixed wireless systems have their purposes, but we don't have time to get into that today. Wi-Fi is a form of mobile wireless. So fixed wireless might be a case where you don't want to lay down the cables, but you know that between this point and this other point, you want to have communications, and it might be convenient to then put in highly directional antennas on both sides and then do your communications over this wireless link. There's also terrestrial versus satellite, and most of the communications we will be concerned with in this course are terrestrial, because Wi-Fi systems are generally terrestrial systems. Satellite systems are much longer range, and they make use of satellites orbiting the Earth to facilitate communications. There's also broadcast versus personal modes of communications. Broadcast will be things like radio and TV, where it's going from one to many. It's not personal. Because of that, you don't get a personal TV signal from the broadcast station. Now, of course, there's things like Netflix where you get more personalization, but that has to do with the application and distribution, and it's not a broadcast model. Coverage area, data rates, and kinds of communications. These are also other ways where we categorize wireless systems. And we will see more examples in the next slide. But when we talk about kinds of communications, some might be more focused on voice, some on data, maybe specific kinds of data with specific requirements. So here are some examples then of wireless systems. I've already mentioned about radio and TV as classic examples of terrestrial broadcast systems. There might also be satellite broadcast systems because of the wide areas that TV or radio might try to reach, especially TV. So you might have satellites involved. They are fixed and they have large coverage areas. The data rates are increasing these days as we have higher and higher resolutions, the quality going up. So HD TV and then Ultra HD and 4K and various sorts of standards for higher and higher resolution and better quality of TV signals. Then the cellular, so things like mobile phones, Wi-Fi and so on, fall under this. That's because the geographical area might be distributed, broken down into different cells where there's some kind of frequency reuse, and that helps to use the spectrum more efficiently because you can reuse frequencies in cells that are not necessarily next to each other but maybe some distance away. And there's the frequency planning and so on that goes into that. So cellular networks are very popular. Most people have mobile phones, and these are terrestrial, personal, mobile, metropolitan area networks. So kind of a few kilometers or miles in radius compared with the wireless LAN networks like Wi-Fi, also known as 802.11, and these are similar to cellular in some ways, like being terrestrial, personal, mobile, but they're smaller coverage area, local area network, and these days we're getting higher and higher data rates with them. Of course, there are other differences between cellular and Wi-Fi as well, but this shows that there's a lot of similarities. One of the differences I can point out is that cellular tends to use licensed bands, whereas Wi-Fi is unlicensed. We continue with our brief introduction of wireless systems, ending by zooming in to Wi-Fi in particular, and that's where we'll be spending the rest of this course. We had talked about a variety of different kinds of wireless systems and categorization for wireless systems in the previous video. Now let's consider why wireless in the first place. As alluded to in the previous video, performance of wireless systems is not as good as wireline. In what way is it not as good? There's data rates, for example. The reason that we have performance is not as good is because wireless is more difficult, more challenging. Given the state of our understanding of signal processing and various kinds of technologies, we can always do better in the less challenging environment of wireline communications, meaning that the channels are easier to model, they are not so time varying as wireless channels, you don't have multipath and other things as much as wireless, so it's easier to get better bit error rates and higher overall throughputs and things like that. But people still are very interested in wireless and use it because of other benefits. So things like the ability to move around when using wireless communications. You don't have to be tethered to some wire that's connected to this device. So from the performance point of view, then wireless is not as good, but people want to use it for other reasons. So as long as we can get decent performance as far as performance is concerned, people are okay. Generally 1 or 2 steps behind wireline. From the point of view of security, it's harder than wireline because of various features that we'll be talking about in subsequent videos. So we will postpone this for now. But because of convenience, mobility, and freedom, people want to use wireless. Just one example of the many places where we see people really love Wi-Fi is just to look at some surveys that were done of travelers, and the fact that they might look for hotels that have good Wi-Fi services, maybe free Wi-Fi service, and even that the availability of Wi-Fi or lack thereof could be a deal breaker as far as deciding whether to stay in a particular place or not. Things like that. Now, just to do a final big picture comparison between Wi-Fi and other wireless systems before we zoom in on Wi-Fi and remain there for the rest of this course, let's compare Wi-Fi with some other similar types of technology. So these are also terrestrial systems and tend to be used for personal communications, not really broadcast communications. We can compare Wi-Fi with cellular on the one side and Bluetooth type systems on the other side, because Wi-Fi is a wireless local area network system. So it generally means a few hundred meters radius or diameter of coverage, and that's smaller than what we see with cellular systems. So things like 3G, LTE, and so on, those are cellular. Those are wireless metropolitan area networks or wide area networks. And then on the other side, you have Bluetooth, smaller coverage areas like 10 meters or even as low as 1 meter, wireless personal area networks, WPAN. And technologies like Bluetooth are more for cable replacement, short distance communications, very short. Whereas cellular, you can see some other differences besides it being wider area. It also came from telephony routes where data was added later on, whereas Wi-Fi came from data communications routes. It started with data communications from day one, and voice over Wi-Fi is just another application. It's just another data application that goes over Wi-Fi. So you'll be some kind of voice over IP over Wi-Fi. It doesn't have special provision for voice, unlike cellular, which had these very different routes. So therefore, Wi-Fi focuses on enabling wireless local area network and data. Today we see Wi-Fi everywhere. It's in all kinds of devices and appliances, laptops, mobile phones, set-top boxes, various things everywhere. And one thing we would like to also add is that it uses unlicensed bands and has been doing that since the early days, because it's a different model from cellular systems. With cellular, you have licensed bands, and so then certain operators would pay high amounts of money to a government and then license the spectrum, and then they can use it and operate their system. With Wi-Fi, it's more of a free-for-all. Different people can deploy their systems, and these are found in homes, offices, etc. You don't need licenses, but security issues abound. It could be argued that it's related to this kind of more free model of deployment. There's less control. There's also other reasons for the security issues, and we will get to those in subsequent videos. Let's talk about Wi-Fi. What is it? Where does it come from? And what's going on with it these days? It seems that it's everywhere and it's being used for lots of applications. So let's go take a look. There's a number of different terms that you might hear. You might hear about wireless LAN. You might hear about 802.11. You might hear Wi-Fi. Are all of these synonymous? Or there's some differences between these terms? Firstly, let's take a look at what it is in the first place. Comparing with other wireless technologies, the range of communications that Wi-Fi supports can be considered to be mid-range. So it's not as short range as technologies like Bluetooth, for example, and those will be within a few meters, cable replacement type technologies. And then on the other hand, you have the longer range wireless like cellular, and that will be on the order of a few kilometers. Besides that, you can have even larger ranges like satellite communications, but we're here talking about terrestrial communications anyway, so mid-range. Considered as a mid-range wireless communication system, we also see the term WLAN, or wireless local area network. So Wi-Fi can be thought of from the perspective of being something like the local area networks or LAN technologies that we knew of before Wi-Fi came on the scene. So, before Wi-Fi came on the scene, we are familiar with things like Ethernet. Those are making local area networks possible. Now, then, Wi-Fi can be thought of as a wireless version of local area network technologies. Wi-Fi is seen in all kinds of devices and all kinds of applications these days. We see Wi-Fi in digital camcorders, in computer peripherals, in digital still cameras, portable AV players, portable music players, game consoles, DVD players, DVRs, set-top boxes, TVs, music receivers, home theaters, mobile internet devices, cellular handsets, netbooks, laptops, and so on. So that was the application perspective. From the standards perspective, Wi-Fi is something that comes from IEEE, the Institute of Electrical and Electronics Engineers. What is 802? 802 is a set of standards for technologies about networks carrying variable size packets. Within this 802 family of standards, there are various things like, for example, Ethernet, token ring, and so on. Each of them will be like 802.3, 802 for Ethernet. And when it came around to Wi-Fi, it got the number 11. So 802.11 is the standards for Wi-Fi. It's interesting to note that these days 802.11 and and wireless LAN and Wi-Fi are almost synonymous, but it doesn't have to be. So in fact, the term wireless LAN is something more general. Before IEEE standardized 802.11, there were a variety of proprietary solutions for wireless LANs, and these were not compatible with each other, didn't really take off because it was like different companies coming up with their own solutions. This is something that therefore took a standard to gather the momentum to actually explode and become what it is today. So we have Wi-Fi everywhere. All right, so that's kind of between wireless LAN and 802.11. So the third term here, Wi-Fi, where does that come in? Well, there is this thing called Wi-Fi Alliance, which is a global non-profit industry association. And this brings in the remaining piece of the puzzle, because you have the standards which allow vendors to manufacture devices that are compatible and work together because they follow the standard. You need one more piece of the puzzle, and that comes from this Wi-Fi Alliance, because with the test suites that they provide, make sure that the devices from various vendors conform to the standards and to certain specifications about certain subsets of the standards, certain features, and that's what really is the missing piece. It allows devices to be certified, and then they can work together. So you can go buy Wi-Fi adapters, access points, which can be made by different vendors, and you see this Wi-Fi certified logo on these devices. You can be assured that they will be compatible, at least up to certain degrees and supporting certain features. Just a quick market overview, because it's not really a course about markets, but Wi-Fi today is everywhere, so we see it in more devices than even LTE, which is talking about the cellular side. I mean, LTE is doing pretty well, and it's interesting to note that, for example, travelers really love Wi-Fi, so you need Wi-Fi to be provided free by a hotel. If not, people might not want to stay there. It could even be a deal breaker, and they will book elsewhere because it's so important for them. But besides travelers, most other people also like to use Wi-Fi. As we see in this chart, there is a capacity gap in terms of mobile data, because the demand for mobile data has been increasing and increasing, and it just keeps growing exponentially. And cellular cannot provide it for various reasons. So macro network capacity is limited, and there's this room here then where Wi-Fi has been filling a lot of the gap, and so that's what we see here. We continue on with our introduction of Wi-Fi. Let's talk a bit about the history of Wi-Fi. In 1985, a very important ruling was made by the FCC. The FCC is the Federal Communications Commission, and it's a very important organization in the US as far as communications is concerned, and in fact it has influence over the whole world as well, because many other countries also observe carefully and follow some of these developments that happen in the US. So for example, this important ruling in 1985 was that the FCC allowed the use of some experimental ISM radio bands. What does this mean? Industrial, scientific, and medical. But what's so special about these bands? Well, it's not about the locations of the bands themselves. So let's say like 2.4 gigahertz, 900 megahertz. It's not so much about the locations of these bands, but the way that these bands could be used, because these would be unlicensed. You see, one of the problems with deploying new wireless systems, or investigating and experimenting with new wireless technologies, is that usually the FCC would be requiring licenses so that you prevent various kinds of interference from happening. Now, sometimes when you want to experiment with things, it's not so convenient to be talking about licenses and stuff because you're not sure exactly how your communications will be used, and you want to be able to adapt and do things. So having these unlicensed bands was a great way to enable innovation and trying new things. But it also was a foundation that allowed for Wi-Fi to emerge later on. Well, one thing about these unlicensed bands is that it's not completely chaotic. It's not like the FCC says, okay, within this band you can do anything. Okay, so there are still some rules for these unlicensed bands. The radio transmitters have to play nice. They have to follow certain rules. There's certain limits on the transmissions, but they don't have to go get a license from the FCC in order to be legally transmitting in these bands. So that's a big deal. Anyway, because of that, so wireless LAN systems started to emerge. There, as I mentioned before, various proprietary solutions were developed by private companies even before 802.11 emerged. They did not quite take off because they were not compatible with each other and didn't really get the kind of ecosystem, large, wide-scale ecosystem that you need for something like Wi-Fi to become ubiquitous like we see it today. Anyway, in 1990, then work began within IEEE 802 to specify some kind of solution for wireless local area network. By 1997, the first version of 802.11 was published. It got off to a bit of a slow start, as with many technologies. There were certain flaws and problems and so on. So a revision quickly came out in 1999. But also in 1999, another important thing that happened was the formation of the Wi-Fi Alliance. At that time, it was known as WECA. But as I mentioned before, with the Wi-Fi Alliance having this stamp of approval, it allows compatibility when different devices from different vendors can work together. So then you have Wi-Fi certified labels applied to these devices, and that's an important final piece of the puzzle. Besides the standardization itself, to have this other organization that can help to ensure that vendors' devices are working nicely with each other by following certain things according to the standards. So, as we see in this timeline, wireless LAN, WLAN came first, followed by 802.11. Finally, Wi-Fi, the name Wi-Fi through the Wi-Fi Alliance, that came last, and it was the final piece. And then we had everything that, together with the demand for mobile data, created this situation where things were just in place for this tremendous explosion and growth of Wi-Fi. So there was this exponential growth, with especially at this time also the increasing popularity of laptop computers. People soon realized that, wow, standardization really made a big difference. It allowed for this interoperability between systems and growth of this whole ecosystem of Wi-Fi devices, access points, and related products. In fact, within a couple of years, cellular operators started feeling threatened around 2000 2001, and cellular had been established for a couple of decades already. So you imagine the great success of Wi-Fi that allowed this development to occur. There were various basic enhancements that started to be added after Wi-Fi came out, and there's a certain process where IEEE will then introduce amendments. And so here's an example of some of these. 802.11i is an important one for our course today because it's about security. Physical layer amendments we will talk about in this course as well. And anyway, so there's a certain process where these amendments get introduced, and later some of them get rolled into the main base specification. In order for us to be able to effectively do Wi-Fi penetration testing, there are certain concepts about Wi-Fi that we need to understand. These have to do with the architecture of Wi-Fi networks and some of the protocols, fundamental protocols that are used in Wi-Fi systems. Firstly, let's take a look at some of the architecture concepts in Wi-Fi. There are two fundamental units of or groupings of devices in Wi-Fi, and one is the base service set. So with a base service set, that's where you have devices communicating with each other over Wi-Fi, but they are not specifically connected to a larger infrastructure. Whereas what we see on the right side, we have the so-called extended service set. Here's where we might have multiple access points that are connected to each other through a distribution system, DSS distribution system, such as an Ethernet-based distribution system. However, it can even be a wireless or Wi-Fi distribution system. So you have multiple access points connected through a distribution system, and then there's a portal that connects all of this to an external network. So this is a more typical architecture that we'll see implemented for systems that use Wi-Fi. So you have multiple access points in a distribution system, and then with connecting through a portal to an external network like the internet. The mode with just a standalone base service set is also known as ad hoc mode. And the mode where you have this infrastructure and then connecting to the external network is known as infrastructure mode. So you can have multiple BSSs then linked by a distribution system into an extended service set, and that's the more common way that we see things set up. Now, I mentioned access points, right? So there's access points and then there's stations. So all these devices that you and I might be using, let's say with our laptop, our mobile phones, whatever, to connect through Wi-Fi to the internet, let's say. So we might be, let's say with our laptop here, we're trying to find a suitable access point. So we might be then scanning for access points that we can access. And then through that access point, then we get connectivity to the external network like the internet. So there are stations and there are access points. Access points are very similar to stations, except they have some additional functionality. So in terms of communications, though, the underlying communication protocols, MAC protocols, very similar, except access points have some additional capabilities that allow them to control the individual BSSs. And another thing that you might notice if you're just doing a simple scan around is that there's names as well. You'll see names, and these are the BSS IDs, so the base service set IDs, because each of these access points, then you have they would be related to a BSS, and then there'll be an ID. So BSS ID is something that you see. This would be the so-called names of the different Wi-Fi networks that you see around. And then sometimes you find that you cannot connect. In fact, most of the networks these days, you wouldn't just simply be able to connect if you just turn on your device and try and look for networks to connect through, because there's some security that's set up, and we will be talking more about these ways that security can be set up so that you can't just have a random person trying to connect through your access point to get connectivity to the network. By the way, this image here of the access point being another laptop, it's not that is a wrong picture, but because theoretically an access point could be implemented in an access in a PC or laptop as well, not necessarily in some specialized hardware. And it's a good thing to know because it's possible to go, as part of penetration testing, to go set up a fake access point, for example. We will be talking more about how control is done in Wi-Fi networks, because there are certain vulnerabilities in the way that things are done, and so we need to understand how things are done, and then we can talk more about the security vulnerabilities and issues. So if you just imagine you have your device and you're trying to find a way to connect using Wi-Fi to the network. So you're going to see multiple Wi-Fi networks around. They're going to be on different frequency channels. Which frequency channel do we select? All right. So this is one of the things. Which Wi-Fi network to connect to, and then you need to select to then connect to the frequency channel related to that Wi-Fi network. Okay. But let's say you make a selection. Then there's a question about whether there's any access control for that Wi-Fi network. So you might need to know a web key. You might need to know some kind of pre-shared key for WPA2. And then actually, let's say you know the key and so on. So then what's actually happening in terms of the protocol, the signaling that's happening in order to get set up with this chosen access point. So there are certain procedures, and we will talk about that. So you can associate with an ESS or a BSS. And then if you're doing IP communications, there's the question about getting the MAC address for sending your IP packet. So what's the MAC address for the next hop? Let's say, for example, the MAC address of the access point, or the other way around, the access point trying to get the MAC address for the device that you want to receive on, because it's trying to send an IP packet to you. What if we want to just what if we want to move away, or we're just using a different Wi-Fi network? What happens then? So these questions we'll get to in the next couple of videos. Continuing on with basic Wi-Fi concepts, we had previously asked these questions, and let's take a look at what you might find in a typical laptop. You might find some kind of helper tool like this, let's say on a Windows operating system, where it's looking around for the access points that it can see, and then it tries to connect. So in this case, well, okay, no, maybe not that many connections. So it sees one, and the signal strength is pretty strong. That's why you see about 80% here. If there's others that might be further away, then it might also show others. So people typically would then select one of these, and then your laptop Wi-Fi network interface card, or NIC, would then try to connect to that network. So what is happening when it's trying to connect to that network? What does it mean? So this issue about the multiple Wi-Fi networks around, what's actually happening is that in order to show you a GUI like what we saw in the previous slide, the network interface card is actually scanning through different frequencies to find the different Wi-Fi networks around. Now, depending on the capabilities of your network interface card, it might be scanning at 2.4 gigahertz to 5 gigahertz, or maybe both. And it's like tuning to an analog radio station. So you just scan through different frequencies. And what it's listening for is beacon signals that are being transmitted by the access points. So it's going to gather beacon signal information. It's going to then be able to know about the networks that are around. Now, the selection of the network, there can be different ways that it's implemented. So in the example that we saw here, the GUI is letting the user choose, and sometimes it might store the preferences so that the next time you turn on your laptop and try and look for a Wi-Fi network to connect to, it might automatically connect to something that you're previously successfully connected to before. So user might be presented with a choice, or it might try to be smart about it and automatically reconnect with something you had connected before. Now, just seeing these networks doesn't mean that you can connect to them. So after you select a network, there might be some access control that might prevent you from connecting to your selected network. That's where authentication is very important, because remember, this is wireless. So the access point is just receiving some signals over the air. It doesn't really know who you are. It's not like a wired network where there's cables connected to certain devices. So physically, there's this physical connection. So therefore, the network needs to do some kind of authentication. Various schemes are possible, and we'll talk about them. Some are much stronger, some are much weaker than others. In fact, the so-called open authentication is actually not doing any authentication. It's like letting everyone and anyone in. So after authentication, there's another concept about actually getting set up to talk to the access point. You need to associate with the BSS or the ESS. Because, yeah, the access point, okay, recognizes that you are authenticated as a particular user, but you still need to associate to the access point, to this BSS or ESS. Associating is kind of like actually the analogy in the wired local area network is actually connecting this cable from your laptop or PC or whatever to the switch, and then you're able to physically get the packets to and from the to and from the destination and source. Now, typically, because we're talking about connecting to the internet, then there's another step that needs to happen after that, because in the process of authentication association, this is beneath the IP layer. So these things are happening without reference to a specific IP address. So it's just about at the layer 2 getting things set up. So then let's say you want to get IP packets to and from devices, then something needs to be done, and ARP is the solution, address resolution protocol. ARP we might already know from just wired LANs. It also can and does happen on Wi-Fi networks. Because similarly, you need to have this mapping between IP address and MAC address that you transmit to. Now, when we then move to, let's say, to a new access point in the same network, so you're just moving within the ESS, then you can just reassociate. But yeah, because basically an ESS, as far as the IP network is concerned, an ESS looks like one big local area network. So you're not changing your IP address when you're moving around within the same network. You just need to handle things at layer 2 to reassociate with the corresponding new access point. And then once you do that, you're good to continue with communications. And to then tear things down, you disassociate. Oh, and there's one more step that was not mentioned here, but you can also de-authenticate. So de-authenticate is like even more separation, because then the AP no longer recognizes you, meaning the station, as authenticated. So you want to get set up again, you have to go from the beginning to authenticate again. Continuing on with basic Wi-Fi concepts, we had previously asked these questions, and let's take a look at what you might find in a typical laptop. You might find some kind of helper tool like this, let's say on a Windows operating system, where it's looking around for the access points that it can see, and then it tries to connect. So in this case, well, okay, no, maybe not that many connections. So it sees one, and the signal strength is pretty strong. That's why you see about 80% here. If there's others that might be further away, then it might also show others. So people typically would then select one of these, and then your laptop Wi-Fi network interface card, or NIC, will then try to connect to that network. So what is happening when it's trying to connect to that network? What does it mean? So this issue about the multiple Wi-Fi networks around, what's actually happening is that, in order to show you a GUI like what we saw in the previous slide, the network interface card is actually scanning through different frequencies to find the different Wi-Fi networks around. Now, depending on the capabilities of your network interface card, it might be scanning at 2.4 gigahertz, 5 gigahertz, or maybe both. And it's like tuning to an analog radio station. So you just scan through different frequencies. And what it's listening for is beacon signals that are being transmitted by the access points. So it's going to gather beacons signal information. It's going to then be able to know about the networks that are around. Now, the selection of the network, there can be different ways that it's implemented. So in the example that we saw here, the GUI is letting the user choose, and sometimes it might store the preferences so that the next time you turn on your laptop and try and look for a Wi-Fi network to connect to, it might automatically connect to something that you're previously successfully connected to before. So user might be presented with a choice, or it might try to be smart about it and automatically reconnect with something you had connected before. Now, just seeing these networks doesn't mean that you can connect to them. So after you select a network, there might be some access control that might prevent you from connecting to your selected network. That's where authentication is very important, because remember, this is wireless. So the access point is just receiving some signals over the air. It doesn't really know who you are. It's not like a wired network where there's cables connected to certain devices. So physically, there's this physical connection. So therefore, the network needs to do some kind of authentication. Various schemes are possible, and we'll talk about them. Some are much stronger, some are much weaker than others. In fact, the so-called open authentication is actually not doing any authentication. It's like letting everyone and anyone in. So after authentication, there's another concept about actually getting set up to talk to the access point. You need to associate with the BSS or the ESS. Because, yeah, the access point, okay, recognizes that you are authenticated as a particular user, but you still need to associate to the access point, to this BSS or ESS. Associating is kind of like actually the analogy in the wired local area network is actually connecting this cable from your laptop or PC or whatever to the switch, and then you're able to physically get the packets to and from the to and from the destination and source. Now, typically, because we're talking about connecting to the internet, then there's another step that needs to happen after that, because in the process of authentication association, this is beneath the IP layer. So these things are happening without reference to a specific IP address. So it's just about at the layer 2 getting things set up. So then let's say you want to get IP packets to and from devices, then something needs to be done, and ARP is the solution, address resolution protocol. ARP, we might already know from just wired LANs. It also can and does happen on Wi-Fi networks. So similarly, you need to have this mapping between IP address and MAC address that you transmit to. Now, when we then moved, let's say, to a new access point in the same network, so you're just moving within the ESS, then you can just reassociate. But yeah, because basically an ESS, as far as the IP network is concerned, An ESS looks like one big local area network. So you're not changing your IP address when you're moving around within the same network. You just need to handle things at layer 2 to reassociate with the corresponding new access point. And then once you do that, you're good to continue with communications. And to then tear things down, you disassociate. Oh, and there's one more step that was not mentioned here, but you can also de-authenticate. So de-authenticate is like even more separation, because then the AP no longer recognizes you, meaning the station, as authenticated. So you want to get set up again, you have to go from the beginning to authenticate again. Over the years, to keep up with the times, amendments have been added to the base Wi-Fi specifications. Among the most prominent of these amendments are physical layer subsystems that provide Wi-Fi systems with the capability to communicate with higher and higher data rates. So as time has progressed and technology has improved, we have seen the introduction of various amendments such as 802.11b, 802.11g, 802.11n, 802.11ac, and so on, which have added capabilities to Wi-Fi. Now, these are not the only amendments that have been added to the base specifications over time, but they tend to be the most well-known because you can find them on product packaging and labels, since they have direct impact on what you can do with the system. For example, you get higher and higher data rates as you go up and get to the more recent amendments. There are also other amendments that are more behind the scenes and might not be as well known to people. We will briefly go through what these amendments are and the frequency bands they use and things like that in the next few minutes. In 1999, two amendments were added to the base Wi-Fi specifications, one of them being 802.11b and the other 802.11a. Originally, the base Wi-Fi specifications only allowed for communications up to 2 megabits per second. So 802.11b was known as a high-rate physical layer because it enhanced the capability to go up to 11 megabits per second through the use of something known as CCK, or complementary code keying. 802.11b was designed to work in the 2.4 GHz unlicensed ISM band. Simultaneously with 802.11b, work was being also done on something which was known as 802.11a, which it came out slightly later than 802.11b, also in 1999, but the numbering is this one's A and the other's B because this one was started slightly before 802.11b. 802.11a goes further than 802.11b in some ways because it is using OFDM, so it's the first Wi-Fi physical layer to use this advanced transmission scheme, OFDM. And with OFDM, we are still seeing OFDM being used in more recent systems like LTE. Also, 802.11a was the first to use the 5 GHz bands. There are pros and cons of using 2.4 GHz versus 5 GHz. 5 GHz propagation is not as good, so the signals do not propagate as far. But 802.11a has the benefit then of operating in a less cluttered band, because 2.4 GHz you can find lots of other transmitters there, other systems. With unlicensed systems, that's one of the problems you get. However, at the time that 802.11a emerged, things were not as cluttered in 2.4 gigahertz, so it was not really successful. People were sticking with 802.11b in the easier to work with 2.4 gigahertz band. And another point about 802.11a is that it offers adaptive data rates. So if you're not able to actually get the 54 megabits per second maximum data rate, you can still communicate, but the data rates might be scaled back to 48, 36, 24, and so on megabits per second. This depends on the channel conditions. It will try to give you higher data rates if possible. And here are some of the system parameters having to do with the OFDM system. Since we had this issue about using 802.11a, which comes in the 5 gigahertz band, and it's not really backward compatible with 802.11b, hardware manufacturers did not want to include hardware support, which includes antennas, radio transmitters, and receivers for both 2.4 and 5 gigahertz. The next amendment to be introduced for the physical layer was 802.11g. This takes an OFDM system that works up to 54 megabits per second, and instead of operating at 5 gigahertz, this comes down to 2.4 gigahertz. So it's also backward compatible with 802.11b. It therefore has these advantages over 802.11a, that it can maintain that 54 megabits per second, but work more nicely with 802.11b. This came out in 2001, and it was a great success. Because of these backward compatibility reasons, it's more cost effective to make multi-mode Wi-Fi devices that support both 802.11b and 802.11g. So it was a great success. Even while 802.11g was emerging, work already began on the next generation of Wi-Fi physical layer. And in fact, this was not just the physical layer. There were also enhancements in the MAC layer. This was quite a major step forward because multiple new powerful ideas were introduced in 802.11n. So you had greater throughput up to 300 megabits per second in 20 megahertz, and then there was the introduction of larger channels as well, 40 megahertz channels, so they got you up to 600 megabits per second. Plus various other ideas like data aggregation, MIMO, which is multiple input, multiple output, and that refers to multiple antennas on both the transmitter and receiver sides. And that gives you longer range, increased reliability, all these other. We continue on with our examination of Wi-Fi physical layer alternatives. Now, these come in different amendments to the base Wi-Fi specification, and it should be added that these are optional. So not every Wi-Fi device needs to include support for all of these physical layer alternatives. However, from a practical market point of view, if you're just going to build products that use some of the less powerful physical layers, let's say 802.11a and b only, your market share is not going to be doing very well because people are looking for the more recent amendments. However, having said that, you can find products out in the market that might not support the latest. So maybe you have products that go up to 802.11g or products that go up to 802.11n and not to the latest, which currently is 802.11ac. Why is that? There are two reasons for that, at least, and one of these reasons is that it's more costly to include the most recent, latest, and greatest physical layers. So things like 802.11ac are more complex. The signal processing is more sophisticated. You need corresponding hardware to also handle that. And for some people, the alternative, which is cheaper, which is to go with just, let's say, 802.11g or n, can make it attractive to just limit themselves to something like that, 802.11n, for example. Because maybe they don't need gigabit per second speeds, so maybe a few hundred megabits per second with 802.11n, that could be sufficient for their purposes. Another reason why some products would be still not going with the latest, maybe 802.11n only, is that sometimes when the latest and greatest physical layer alternative is being finalized, it might not yet have been officially ratified by IEEE Standards Association, but already vendors might be making so-called pre-standard products because most of the features would already be known and specified. It's just a matter of ratifying, and there might be some small tweaks towards the end. Now, these pre-standard products can be a bit risky in the sense that they might not be fully optimized or fully compatible with the final standard that actually comes out eventually. But for some people, they might not want to wait. They might just go with one of these before the final standard emerges. So continuing where we left off, we were looking at 802.11n. And as I mentioned, it has a greater throughput than earlier physical layer alternatives, things like 802.11g. And it builds on the success of 802.11g. It introduces certain innovations like allowing wider channels, like 40 megahertz channels, and then things like MIMO with multiple antennas on both sides, allowing multiple streams of data at the same time, and thus resulting in greater throughput. It operates in both the 2.4 and 5 gigahertz bands. As you might remember from the previous discussion, there's some benefits of going with 5 gigahertz because it's not as congested as 2.4 gigahertz, but the radio range is not as far as 2.4 gigahertz. However, starting with 802.11g and then more so with 802.11n, because of the increased congestion at 2.4 gigahertz, 5 gigahertz just becomes more and more attractive. So at the same time, the cost of dual band radios was decreasing by the time we get to 802.11n, so having something that operates in both of these bands becomes more and more attractive. Additional features like DFS and TPC as well. This opens up more channels in the 5 gigahertz band. DFS is dynamic frequency selection. Anyway, because of various hardware advances, 40 megahertz was no big deal compared with 20 megahertz. And so there's not much more spectrum in 5 gigahertz as we see here, 400 megahertz more spectrum. And this is generally the best way to increase capacity in a wireless system when you throw more spectrum at it. All other things being equal. So by 2007, 802.11 was everywhere, and there's something which happens every 5 or whatever, some certain number of years. Then the 802.11 amendments that have been published in the past few years would then be rolled into the main specifications. So for example, 802.11a, b, d, e, g, h, I, j, all of these got rolled into the base specification, and in the 802.11 2007 revision. So then officially now we shouldn't be talking about 802.11a, 802.11b, e, and 802.11g and so on, because they are actually part of the base specification. But for convenience and out of habit, people still do refer to these 802.11g, etc., rather than the corresponding section in the base specification. Similarly, when 2016 came, 2012 came around and 2016 came around, then additional amendments were rolled into the base specification. So for example, you might be interested to know that 802.11n now is rolled into the base specification in 2012. And then the latest and greatest of these higher and higher data rate physical layers, 802.11ac, was rolled into the 2016 revision. So technically, we shouldn't be speaking about 802.11n or 802.11ac anymore, but the corresponding sections in the base specification. But you look everywhere on product specifications and so on, you will still see these around. Then going beyond 802.11n, talking about 802.11ac, because there were these different new use cases for Wi-Fi needing even higher throughput than before. I mean, things like HDTV were becoming more common. So there's something called very high throughput that is, well, 802.11ac. Uh, well, it's higher throughput, very high throughput compared with high throughput in 802.11n. Besides the 20 and 40 megahertz channels that we find in 802.11n, there are also 80 megahertz channels that are added in 802.11ac, plus some optional support for even wider channels going up to 160 megahertz. And there's additional other technology innovations that were added. So you have, for example, modulations like 256 QAM, quadrature amplitude modulation. So this gets you up into the gigabit range. But this is not where it ends, because 802.11ax is around the corner. It's coming within a couple of years. Powerful tools exist that allow us to capture and inspect all frames that come through a particular network interface. Wireshark is perhaps the most widely known, and it's freely available and it's a good tool to use. However, if you were to try Wireshark and just turn it on to capture and inspect everything that's coming in through your wireless network interface card, you might be disappointed, because you might find that you're only seeing traffic that's going between your access point and your computer. You're not seeing other traffic between your access point and other devices, and you're not seeing traffic that is going on between surrounding nearby access points and those devices that are connected to those access points. Why is this? Well, it's actually a good thing for most of the time, because in most normal ways of using Wi-Fi, you don't want to be bothered by frames that are not meant for you. You just want to be, let's say you're browsing the web or whatever, you want to be seeing things that are meant for you. And so it's a good thing. And Wi-Fi is designed to filter out most of the other signals that are coming in, and so you only get what's meant for you. That's good for normal modes of operation, but when you're trying to do Wi-Fi penetration tests, you actually would prefer to see more of what's going on. You want to see more of the frames, even frames that are not meant for you. You want to see what's going on between your access point and other devices, and surrounding nearby access points and other devices. In a sense, you want to be a busybody, so to speak. Well, so what's happening? I mentioned that all these other frames are being filtered out. So how is that happening? We're going to go through some of the ways in which things get filtered out. And then we'll talk about a couple of modes where you can set your network interface card to these modes if your network interface cards support these modes. And you'll be able to actually then capture more of these other frames that you would not otherwise be able to. Let's look firstly at the physical layer, because some of the filtering happens at a physical layer, some of it also happens at a MAC layer. So the first thing perhaps that we would think of is that, well, certain access points are too far away, so by the time the signal gets to you, it's very weak, and so you cannot receive. So physical distance is the first reason why some frames are not arriving at your receiver. Now, even if physical distance is not an issue, so you might be getting reasonably strong signals from an access point, you might be listening at a different frequency band from the transmission. So let's say you're listening at 2.5 gigahertz, it's transmitting at 5 gigahertz. You also don't hear what it's transmitting. So more frames get filtered out this way. Now, even if you're using the same frequency band, so you're listening at 2.4 gigahertz, but the access point might be transmitting on a different channel within this band. So let's say you're listening to channel 1 at 2.4 gigahertz. The access point might be transmitting at some other channel like channel 6, 8, 9, 11, whatever, that's not overlapping with channel 1. Then you don't hear it either. Besides all these, in a sense, physical constraints having to do with physics, there's also the transmission scheme, the frame format and the modulations, and that has to do with the physical layer alternative that is being used. As mentioned earlier, there's various alternatives like 802.11a, B, G, and AC, and so on. And not all devices support all of these alternatives. So, for example, you might have your network interface card that only understands A, B, G, and does not know how to interpret signals that are encoded for 802.11n or 802.11ac. So if you have access points transmitting or devices transmitting in these formats like 802.11n, you will not be able to understand them. Additional filtering at the physical layer can happen due to errors in the reception. So your network interface card, for various reasons because of noise and interference, might detect some bits wrongly. Therefore, Wi-Fi has a built-in CRC test that helps the network interface card to detect some errors. So it might detect it because it fails a CRC test, and then that whole frame gets dropped. That's also something that can happen. Now, closely related to dropping of frames is encryption or ciphering. So even if a frame doesn't get dropped, it might not be understandable because it's encrypted and you don't know how to decrypt it. So these are all ways that then things get dropped or hidden from your site. In the case of encryption, if it passes through, you might still see it in Wireshark, but you might not be able to understand it. It might look encrypted and you don't know what the frame contains. Besides the physical layer, there is also filtering happening at the MAC layer. So now the subset of frames that pass through the physical layer filtering and come to the MAC layer then get further filtered based on things like the destination MAC address. So usually you only are interested in frames that are addressed to you. So the network interface card checks the MAC address and sees if the destination is not you, it's an unknown MAC address. It also discards the frame. Furthermore, you have to be associated with a BSS, and so it's also filtering by the BSS that you're associated with. And because of all that, generally then you will not really be seeing much unless you turn on one of these other modes, not the normal mode, but monitor mode or promiscuous mode that are designed to allow a network interface card to pass up more frames to the application layer so that an application like Wireshark can then let you inspect these frames. We go to promiscuous mode first. This applies to both wireless and wired LANs in the sense that the network interface card that is in promiscuous mode will just pass up all frames, even those where the destination MAC address is a different device. For the case of wireless LANs in promiscuous mode, they have to be associated with a BSS to see other traffics in the BSS. Therefore, this might not be so powerful in a sense because you have to be associated with a BSS. It's kind of like being plugged into a wired LAN. So when you're associated, then you belong to that wireless LAN, and then you see all the traffic in it in promiscuous mode. Even more powerful though is monitor mode, where you don't even have to be associated with BSS as long as a frame passes in and you can detect it. Just go ahead and send it up to the application layer. Sometimes it might even be failing a CRC test and be corrupted, but well, it can still be passed through. So monitor mode is very powerful, but only some network interface cards support it. About security. The first thing we need to do is to define what we mean by security. This is because when two people are talking about security, they could be meaning two different things. For example, a bank might be concerned with the physical security of the physical assets like cash, gold, and other things that are stored in its vault. They want to protect these against those who might want to steal it. Information security is another area of security, but of something very different. It's security of information. Information these days is very important. Your passwords, for example, are information that you would rather not have someone else know about because they are quite powerful and grant you access to all kinds of things. When we're talking about Wi-Fi penetration testing, the kind of security that we're interested in is information security. Now, we can further subdivide information security into things like system security, network security, and physical security. So, for example, you have a PC, there's some information in it that you would like to be secure. That's why you log into your PC and you don't just let anyone access your PC because there's valuable information in it. Logging into a PC is one of the aspects of what is known as system security. Besides system security, there's also physical security. So maybe your PC, you lock it to your desk and you don't make it easy for people to just grab your PC and bring it somewhere else where they can slowly break the system security measures that might be in it. So that's an example of physical security. Network security is the area where we are most concerned with when we're talking about Wi-Fi penetration testing, because network security is about security of information as it's being transmitted over a network. So how secure is the network communications? We want to protect against various kinds of vulnerabilities because attackers can find ways to exploit such vulnerabilities. So for example, when we have wireless networks, you can imagine some other receiver that's not really your intended receiver listening to the signals that you're transmitting. If these signals are not encrypted, they can see what you're sending. That's why, for example, you need to encrypt if you don't want them to know what it is you're sending. Now, it's a hard problem for various reasons. One being that there's so many different ways that attackers can try to attack the system, and there's many different possible vulnerabilities. Another reason why it's hard is that it's kind of a negative problem. You're trying to avoid the system being vulnerable in all these different ways, but they just have to find one way in which it's vulnerable and then they can attack it. Furthermore, the attackers are not going to tell you when they find a vulnerability. Well, maybe they might want to boast to their friends, but what I'm saying is that sometimes it's better for them if you don't know and they can keep exploiting that particular vulnerability and stealing your data or doing other things that you actually don't want them to be doing with your precious information. Alright, so Wi-Fi security is about network security. We can be even more precise when we're talking about network security, and to do that we need to consider the kinds of vulnerabilities that may exist when we're communicating over a network, and then how we can protect against these vulnerabilities. So the first thing that we might want to protect against is people listening to the traffic that's going over the network. So that's known as eavesdropping, and we want to protect against eavesdropping. The technical term for this is that we want to provide confidentiality services or secrecy services so that the traffic is confidential and it's not something that an attacker can just see by just eavesdropping on the channel. Another thing that an attacker can do, so let's say the attacker is not able to see the traffic because it's encrypted and so it's confidential. The attacker could try to impersonate another device and that way then be able to try to trick the other side, the sender, to send information to the attacker. To protect against that, we need proper authentication. So you authenticate who the other side is. A third major way that an attacker can try to attack your network communications is by altering messages that are going over the network. And this could be done in order to break your eavesdropping protection or your impersonation protection. And so we also need to ensure the integrity of the data, meaning that if the data is not altered, then we can trust it, whereas if it has been altered, we would like to know and that we don't make use of altered data. We live in a digital world. As such, network security then becomes about protection of digital signals, namely ones and zeros, as these digital signals are going between a transmitter and a receiver over a network. There are a number of underlying fundamental building blocks that are used in most of the cryptographic algorithms out there, and they process digital signals, ones and zeros, and combining these primitives allows us to build various cryptographic algorithms. Some of these primitives are pseudo-random generators. Now, actually, it would be good to have truly random numbers for some of these algorithms, but in practice, pseudo-random numbers are good enough. What do we mean by that? A pseudo-random generator generates streams of ones and zeros that are not actually random, but for most intents and purposes, they appear random. If you do various statistical tests on them, they look random. It's hard to tell that they are not random and follow some kind of deterministic algorithm. Besides pseudo-random generators, other primitives you would find in cryptography are ciphers. Block ciphers are where blocks of bits are encrypted and then the results are concatenated together, but each block is processed separately. Stream ciphers, on the other hand, are where you have streams of ones and zeros going into the cipher and then a stream of encrypted ones and zeros coming out. The important thing about ciphers is that it needs to be hard to do the reverse, so that if you have ciphering happening at the transmitter and then someone other than the intended receiver receives this encrypted data, it would be hard for them to decrypt the message. Only the receiver is able to decrypt it properly. And one way this might be done might be if the transmitter and receiver share a key that only the receiver then can use to unlock the message. Another security primitive that is found in cryptographic algorithms is a cryptographic hash. In order to protect the integrity of a message, the transmitter might compute a cryptographic hash of the message and attach that to what is sent, maybe attach that to the encrypted data. On the other side, the receiver can then check to see if the received message, when it's hashed, it matches the message digest that was sent along with the message. This works because cryptographic hashes are designed to be hard for an attacker to find another message that produces the same hash. So if an attacker actually has modified a message, it will very likely have a different hash. It's very hard for an attacker to, after modifying the message, to then make some additional modifications perhaps, such that the resultant message would produce the same hash. So the hash is not going to match. Now all of these security primitives can be combined in various ways, and they are done so in different cryptographic algorithms, but they are not easy to do. It's difficult and tricky to apply. A standard feature of cryptographic algorithms is the use of keys. So if a transmitter and a receiver are sharing a key, for example, in some cryptographic algorithms, this means that it's very difficult for an attacker without that same key to be able to decrypt the message sent from the transmitter to the receiver. There are two main models for how these keys are related. In the first model, known as shared secret cryptography or symmetric cryptography, the two keys K1 and K2 are the same key. That's reasonable, makes sense, and it's easy to see why then if the attacker does not have the same key, the attacker might not be able to decrypt the message, because the key is what unlocks the message. There is, however, not just this model, but another model where the two keys are still related but they're not the same. They are in fact different keys, albeit related keys. This is the public key cryptography model, also known as asymmetric cryptography. The reason it's called asymmetric is that the two keys are not the same, so it's not symmetric, whereas in the case of symmetric cryptography, the two keys are the same. So let's take a look at shared secret cryptography first, and then we'll try to explain why people use different keys in public key cryptography. So in shared secret cryptography, we have actually not just in shared secret cryptography, in both shared secret and public key, we can look at this diagram. We have Alice wanting to transmit to Bob the message, unencrypted message M, passes through a transformation T, together with the input of a key K1. This produces the ciphertext C, which then goes to Bob, and that passes through the function U that is unencrypting and resulting in M being received by Bob, the message M. So the function U needs to take the key K2. It's easy to see why with shared secret cryptography you share this common secret, so the two keys are the same, and then in a sense U is just reversing what T did. On the other side you get back M. What about with public key cryptography? In the case of public key cryptography, K2 is the private key of Bob, and then K1 is its public key. So the public and private key are related. Very interestingly, the public key K1 can be freely distributed and widely known without affecting the security of K2. So you're not able to derive K2 just by knowing K1. And without compromising the security such that just because someone knows K1, they might be able to eavesdrop. It's more about having K2 that allows an attacker to be able to decrypt successfully. So the attacker doesn't have it. At most, the attacker might have K1. So this is very useful in the sense that the key K1 can be published, and Bob doesn't have to spend a lot of time to go arrange shared keys with all the devices that Bob wishes to communicate with, Alice and others. But you still have a key management problem, because how does Alice know, for example, that the key K1 is indeed the public key of Bob, right? So then, but at least it's useful to have different keys, so that now you only need to keep K2 private. A disadvantage, though, of public key cryptography is that it's computationally more expensive. So one popular way that it's used is that it's used to derive a shared key between a transmitter and receiver, following which the actual data communications would be encrypted with that derived shared secret. What about in Wi-Fi? Which of these two models do we see? In WEP, we see a shared secret. In WPA, also. WPA2 PSK, which is WPA2 pre-shared key, also uses a shared secret. However, WPA2 enterprise mode may or may not use public key cryptography, depending on the specifics of the protocols actually used. So it has that possibility. One reason why Wi-Fi penetration testing is important is that wireless security is hard. It's hard. An organization that wants to secure its wireless network needs to be aware of many factors and considerations, many challenges, and compared with a wired network, wireless adds additional challenges. What I mean to say is that both wired and wireless networks have certain security-related challenges in common, and if you're trying to secure a wireless network, you have additional challenges to deal with. Here's a high-level list of the challenges that an organization would have to deal with in order to try to secure its wireless network. Firstly, there are the general considerations, which are things that apply to both wired and wireless networks. The next slide is going to go through some of these general considerations. So we move on to the next item in this list. When you have a wireless network, you also have the specific challenges arising from wireless, such as the broadcast nature of the wireless medium. Unlike a wired network, where the signal is somewhat constrained within a wire, the wireless medium is inherently broadcast. Yes, you can have directional antennas instead of omnidirectional antennas, and that can channel your energy in a certain direction, but it's not really the same as sending it in a wire. And if you really want to do really pinpoint accuracy with directional antennas, that runs into other challenges with your antennas as well. Furthermore, if devices are going to be moving around, you can't really be doing that very well because you have to keep tracking and shifting your beams, and it's not really the way to go. So it's something that we have to deal with from the security point of view. Additionally, there are specific challenges arising from mobility. As you move around and you're changing your point of attachment to the network, that makes it more difficult to secure your communications compared with wired communications where you're physically connected to a network and you're not really moving from that point of attachment. Then wireless devices also need to be concerned about battery consumption of energy, and that also makes it difficult. So anyway, let's take a look at the general considerations first. In any network that's trying to secure the communications, there are cryptographic algorithms being used. These use sometimes pretty sophisticated math to secure the communications. However, it's not easy to get these right, so there can be flaws in the building blocks, whether it's the pseudo-random number generators, ciphers, whatever building blocks they're using. Sometimes there are flaws that can be discovered in them, and then that can compromise the security of your system. Even if building blocks are themselves okay, sometimes then the combination of these building blocks, if you don't combine them appropriately, that can also lead to compromises in your security. Now, even if you get all that right, and you have a theoretically sound system, you might still be having poor usage of certain aspects of your system. So for example, you might have everything great, but the keys that you're using are just too short. Then you might become vulnerable to simple brute force attacks because there's not enough combinations of keys. And that's about securing your cryptographic algorithms. Now let's say you have got your cryptographic algorithms well done and well designed. Even then, you still have other concerns because the hackers might be trying to get around these protocols through other means, such as social engineering. With social engineering, we're talking about how organizations are made of people, and these people might not really be very security savvy. So you might find hackers being able to trick someone into revealing information about the system, revealing things like their passwords, and whatever other human mistakes that people can make. So that's where the social engineering comes into play and makes it hard. You have to educate your users. Besides that, poor policies can also cause problems. Example is that there are certain best practices like periodically changing passwords, but if these policies are not in place and people don't actually do that, you might end up with a situation where the system is not as secure as you think, because attackers can spend a lot of time. They have a lot of time, passwords are not changing, they can gather data at their leisure and eventually might be able to compromise the security of the system. One final challenge here is regulatory constraints. Export controls, for example, in the US, can mean that security algorithms are put in place that are weaker than they might otherwise be, so that the Department of Commerce will not disallow a certain system from being exported out of the US. In fact, that's one of the reasons why WEP for Wi-Fi at first was so weak, because at that time there were concerns that making it too strong might cause problems getting Wi-Fi technology out of the US. Then we get to the wireless specific challenges, and I already mentioned about the broadcast nature of the wireless medium being one of the problems. Because of this, WEP was introduced in Wi-Fi. There was the fact that wired communications was going in wires and the signals were constrained within cables, whereas in Wi-Fi it was inherently being broadcast. So wired equivalent privacy was meant to be something not super secure, but to make the privacy in Wi-Fi somewhat equivalent to signals in wires in a wired network. And then for mobility, you have additional challenges. Devices are changing their network attachment points as they're moving around, and it's not easy for the system to know that the device is actually who it claims to be as it moves from one point to another point. This means that authentication is harder and needs to be done more frequently. And now, last but not least, wireless devices also have constraints. They impose constraints on what we can do from a security point of view. Because of hardware limitations, for example, the algorithms that can actually be used might be limited. You might not be able to use the most strong algorithms. And similarly, battery or power concerns also can limit what can be done. And this is not just theoretical. WPA uses certain cleverly designed protocols that can work even on hardware that is somewhat limited. We have given a general introduction to Wi-Fi, and we have also given a general introduction to network security. It's now time to bring the two together and talk about Wi-Fi security. Our approach will be to take a look at the development of Wi-Fi security in a historical context. We will first look at the early approaches and the problems with those approaches. Then we will see how later approaches like WPA, WPA2, and so on address the problems that were in the earlier approaches. We will also explain why some of these earlier methods like WEP were chosen even though they are today considered so weak. There are reasons why they were put in the system in the first place. Using this kind of historical approach, as we trace the developments, we will be then seeing fumbles and the trade-offs involved, because it's not a straightforward decision which cryptographic algorithms to include for a system like Wi-Fi. Anyway, we start with authentication. Remember, authentication is to prevent impersonation attacks, and it's particularly important in the context of Wi-Fi because Wi-Fi is a wireless system and supports mobility. This means that the devices that are using Wi-Fi can be moving around and trying to connect to the network. It's one of the benefits and attractions of wireless. You don't have to be tied to a particular location. You can move around and still communicate. However, this flexibility brings security challenges with it because that means now that it makes it harder for the system to know if this device is actually who it claims to be. Imagine from the point of view of the network, you're having a device authenticated and then communicating at one point, say an access point somewhere, and then sometime later you see a signal that claims to be from the same device coming in through another access point and claiming that, well, it has moved and wants to now continue communications at this other access point. How does the network know that this is genuine, that it's actually the case that the device has moved and is now trying to continue its communications at this new access point? It's not so easy for the network to know. So therefore, the device needs to authenticate again at this new access point. Therefore, authentication becomes more challenging and important than in the case of wired communications, where the device would be physically plugged in, connected to a wire somewhere, and generally it's not moving around. In that sense, the physical wire is a form of continuing authentication of the identity of the device. Whereas in wireless, the devices are moving around and we need to authenticate as they try to attach to the network at different points. Because of this importance, early on in the development of Wi-Fi, two authentication models were introduced, and we see them in 802.11 1999. The two authentication models are so-called open authentication and shared secret authentication or shared key authentication, also known as web-based authentication. Web as in WEP, not WEB. I mean, that's also a common term, web-based authentication, but we're talking about WEP-based authentication. Anyway, we first look at open authentication. As we see in the diagram, in open authentication, a station would be sending its identification, its MAC address, and it indicates algorithm 0 for open authentication, whereas the shared key authentication would be algorithm 1. And the access point will see this and then decide whether to admit the station. In the case where the access point doesn't really care about which MAC address the station uses, the access point would then just accept. So in some implementations then we find that open authentication is in this sense a bit useless because the access point accepts all requests and it's like a door with no locks. Anything goes. Any MAC address is acceptable and comes into the network. However, it's also possible to implement open authentication with MAC address filtering. MAC address filtering is where the access point can have a list of MAC addresses that it wants to deny entry to, or it can also have a list of MAC addresses that are the only ones that are acceptable that it will allow in. Either way, when it receives this request, then it can either look at the list of acceptable MAC addresses and allow the device if it's in the list, or you can look at the list to deny and see if it's there and then don't accept it in that case. Well, this authentication model is not really very helpful, as you can imagine. So let's take a look at the other one, the WEP-based model, and let's see if perhaps it might be a better way of doing things. So in this case, the station sends its MAC address again. This time, the access point sends a challenge. It doesn't immediately accept. So it sends a challenge to the station that was requesting authentication. This is typically a 128-bit random number, and the station then has to encrypt this challenge with WEP. Therefore, it's known as WEP-based authentication or shared key authentication, because what this means is that the station has to have the same key as the access point, so it's a shared key. If the station does have the key, it can compute the correct challenge response. The access point will verify that, and it will allow the station to come in. So this is a better way to control access to a network. However, it does have its flaws as well, because now the access point is not authenticated. It's only the station that's being authenticated. So you can imagine you could have a rogue access point that's just sending the challenge out, and the station has no way of knowing. The station just computes the challenge response. And you can imagine that an attacker could be doing this to get information about the system and try to crack the WEP encryption. Another problem with this is that there's no token returned here by the access point. So after this authentication happens, even if it's successful, then there's no way that the access point will know later when this same station is trying to communicate with the access point. It doesn't know if it's the same station or not, because there's nothing to associate this station with this authentication that just happened. In the previous video, we have gone through an introduction of Wi-Fi security, and we have touched on WEP in the context of WEP-based authentication. In this video, we will cover more of the details of how WEP works. He can just spoof this MAC address and then get into the network as well. So we have to be careful about MAC address filtering. It's useful in certain contexts or if part of a multi-layer security solution, but beware that it's not foolproof. Anyway, now let's move on to look at WEP. WEP stands for Wired Equivalent Privacy, and it's used for both authentication and privacy in Wi-Fi systems that are implemented. This is actually not a best practice because you should be using different keys and different protocols and algorithms for authentication than for privacy. In modern systems, you don't find the same mistake repeated, but that was years ago when WEP was introduced. And for various reasons, it was done this way. Now, one of the reasons is that WEP was not really meant to be super strong. It's not meant to be military security. It's just meant to be something that's reasonably strong, reasonably being a very subjective term, yes. But back then, the observation was made that with wired LANs, there is some kind of authentication in the sense of the wire being connected to the local area network, whereas in wireless, you didn't really have that same kind of even basic authentication. So therefore, WEP was introduced. But it was not very strong, and purposely so, for reasons like the export control laws of the US at that time, and also to make it more easy to implement in low-cost hardware and software. WEP uses RC4, which is a stream cipher invented by Ron Rivest, a famous cryptographic expert. And RC4 itself is not a terrible encryption algorithm. The weaknesses in WEP have to do more with the way in which the RC4 is used. I mean, it's a building block used in WEP, and the way in which it's used is not very strong. For example, originally there were these 40-bit keys that were used. You might hear that the keys were actually 64 bits, but it depends on what you mean by the keys, because you have 40 bits that are variable and then 24 bits of the so-called IV, initialization vector, which in some systems were never changed or was a well-known sequence of initialization vectors. So effectively then you only have 40-bit keys. Later on, 128-bit keys were added as an option, but in that case you still have the same 24-bit initialization vector. You subtract that away and you get 104 bits of variable bits. So it's either 40-bit or 104-bit keys. Here's a block diagram of how WEP works. Let's take a look at this. It's meant to provide data integrity protection so that on the receiver side, the receiver will know whether the data has been modified in transmission. So other than that, then it's a bit by bit XOR of the key sequence with the plain text to give you the ciphertext. So it's relatively simple to describe, and that's what we have here. The initialization vector is also sent together with the ciphertext in the message, so on the receiving side, the receiver will know how to decrypt the message, because then the receiver can, if the receiver has the same secret key, the receiver is then able to generate the key sequence given the IV, and then can do another bit by bit XOR to get back the original plain text. Originally, WEP was introduced to Wi-Fi to provide Wi-Fi with a level of privacy somewhat equivalent to what was found in wired LANs, and hence the name WEP. Because in wired LANs, there were cables that were providing some inherent security, as signals were found inside the cables, compared with in the case of Wi-Fi, where it is an inherently broadcast medium. However, it soon became clear that WEP doesn't even provide this level of security. And it's not so much in the cryptographic strength of RC4 itself. RC4 is the cipher that's used in WEP. However, it's more about certain other problems in the way that the keys are used. For example, one problem with key usage in WEP is that the same key is used for both authentication and privacy. Cryptographers consider this to be a very bad practice. You don't use the same keys for authentication and privacy. You should use different keys. So this rule of thumb was not obeyed. Furthermore, the lengths of the keys were not long enough. At first, WEP was just using 64-bit keys. Later, it was extended to also allow for 128-bit keys. However, of these 64 bits or 128 bits, 24 bits are actually coming from the initialization vector. This IV, or initialization vector, is often unchanging. Since 802.11 doesn't specify how frequently it should change, in some implementation it did not change, and it was just the same fixed 24 bits. And even if it was changing, it might be a known sequence and known way of changing, and eventually it would repeat in a few hours in a busy network. Therefore, you only have effectively 40 bits, or effectively 104 bits in the case of a 128-bit key. You only have effectively 40 or 104 bits for your key. Then this key is is used with the initialization vector, which is sent in clear text along with the message. So this is a very bad way of doing things because your key space is not large enough to sufficiently protect against brute force attacks. Then the key is also shared by multiple stations and the access point. This made collisions, which means repetitions of IV, even more likely, which made it easier for attackers to break the whole scheme. Besides the poor key usage, another problem is poor integrity protection. There is an integrity check value, or ICV, which is computed for every frame that's sent with WEP. And the idea behind such schemes, in terms of providing data integrity, is that it should be something that's not easy to compute. And when, let's say, an attacker modifies as little as even 1 bit in the crypto text, the resultant ICV should be difficult to compute. So the attacker cannot simply easily modify the ICV to provide a valid ICV if the attacker changes 1 or more bits in the crypto text. The problem is that the ICV that's actually used in WEP is a linear CRC32. It's not a cryptographic CRC, so it's easy for an attacker to modify 1 or more bits in the crypto text and then to correspondingly modify the ICV so that it becomes a valid one, and thus this nullifies whatever integrity protection might otherwise have been offered by this ICV. A third problem that WEP faces is that there's no replay protection. There is simply no sequence number in the frames that are sent, and so the receiver has no way to tell whether a frame is genuinely being transmitted by a transmitter, or whether it's being replayed from something that an attacker heard previously being sent. This has resulted in many different attacks on WEP. The key stream can be discovered through a passive attack that's waiting for IV collision. IV collision refers to finding 2 or more frames that use the same IV, initialization vector. Because then we can XOR 2 frames with the same IV and the same key, and then we get the XOR of the 2 plaintext messages. Since XOR, when you XOR something with itself, then everything becomes all ones. So this effectively removes the encryption, and you have the XOR of these two plain text messages. This allows us to do statistical analysis to recover the actual plain text. Furthermore, such statistical analysis works better as the number of frames with the same IV increases. And there are variations where if we can somehow get some known plain text to be encrypted and then sent, perhaps coming from a friendly website, friendly to the attacker that is, then the AP might encrypt that and it goes over the air and the attacker can get more information more quickly this way. Besides that attack that I just mentioned, there are others as well. There's numerous attacks actually that have been proposed over the years. Another one is a passive attack to guess the key. There are a number of these. Perhaps very famously, we have FMS, which is based on weaknesses of RC4 and knowing the IV. Another one is correct, which improves on FMS. And then PTW, even better. Generally, with FMS, you need about 6 million frames before you can recover the key. With correct, you only need about 200,000, and this number drops to 60 to 70,000 with PTW. Besides the passive attacks that we've talked about, there are also active attacks that can be used, which can speed up the time needed to break WEP. So if we can actively inject traffic, then we can do things like chop chop, where we have fake ARP, and we can do things like the fragmentation attack. We can guess a few bytes from similar headers, and then we can recursively send fragments that the AP would combine and then send them back to the network to get more of the key stream. Partly as a result of the problems encountered with WEP, and also out of a desire to add additional layers of security, some additional security-related measures soon emerged. These predate better improvements like WPA, WPA2, and 802.11i that we will talk about in subsequent videos. But their emergence was a sign that the industry was trying to find some patches for Wi-Fi security, and also a sign that the Wi-Fi market was growing very healthily and robustly and quickly. In general, these measures were not modifying WEP, and the 802.11 specs are still followed, but these are more like workarounds in the implementation of Wi-Fi. They are by no means the best ways to patch the problems that came with WEP, but could be thought of as symptoms of the underlying disease, the disease of poor security, and the industry was trying its best to improve the situation. 3 such measures are listed here on this slide. Firstly, hidden SSID. Typically, an access point would be continually broadcasting its SSID. So, for example, if you have your laptop and you just do a scan, your laptop will show you SSIDs of Wi-Fi access points that it can hear around you. So you might have a few dozen of these that you see in your laptop. That's because your Wi-Fi network interface card is able to see these as they are being broadcast by the access points. Now, what if we don't broadcast the SSID? Then it's harder for attackers to know about the existence of an access point and SSID. The stations that are actually meant to be part of this network, we can argue that they should already know what the SSID is. They don't have to hear it from the access point. So then they can send the SSID and receive a response from the access point, whereas attackers might not know what the SSID is. And therefore, the SSID becomes something like a secret password. However, this is not really very secure because there are other ways for attackers to find out the SSID of a Wi-Fi network, but still it's better than nothing. It does have the disadvantage though that if you want your network SSID to be visible by people using their laptops nearby, then it would not be visible. So depending on your setup, whether that's a pro or con depends. The second thing on the list here is MAC address filtering. In some of the early systems without WEP, only open systems authentication can be used. In this case, the station sends its MAC address along with its request. So the access point can check to see if this MAC address is on an approved list or on a reject list, depending on how the MAC address filtering is set up. And then it can either approve or reject this request depending on the presence of the MAC address in one of these lists. If MAC addresses were indeed unique and unchangeable, then this is certainly a good measure that will definitely work. However, it's possible to change a MAC address. So an attacker could figure out a MAC address that it knows will be acceptable, and then it can change its MAC address to that MAC address in order to get in. The third measure we see here is browser hijack, which takes the philosophy that Wi-Fi security is lacking, but this is happening at physical and MAC layers. So the philosophy behind the solution is that instead of trying to fix things at the lower layers, it just applies security at higher layers. It gives up the desire to try to solve things at the lower layers and just goes with securing things at higher layers, such as the transport layer. Browser hijacking is not a standard or specific way of doing things, but it's more of a concept, so there can be different implementations. Here is a typical way it might be implemented. We have a station trying to access a network. It does some kind of weak authentication with the access point, perhaps web-based authentication, and then it associates with the access point. However, the access point is keeping track of which of these stations have just joined and have not yet been further authenticated using something more reliable at the higher layers. So the first time that the user of the station tries to go to a website like google.com, for example, the access point will know that the station has not yet done the higher layer authentication and would redirect this HTTP request. So instead of going to google.com, it goes to an access controller. So this is a key step here, and it's the reason for the name browser hijacking. You're hijacking a browser session that's meant to go somewhere else like google.com, and you're bringing it to your access controller, where you can then get the user to be authenticated, perhaps getting a user ID and password from the user. And in fact, that might be all that it needs, and then it can grant access. There are different variations. So in this diagram, we see a variation where the user name and password from the mobile might then be actually authenticated by some authentication server somewhere else, as we see here, the home network of the station. But this is just one of many variations. The key idea behind browser hijacking is this redirection here of the initial HTTP requests. So the access point needs to keep track of who has already successfully been authenticated at the higher layers and who has not. Within a couple of years of the introduction of Wi-Fi, and in particular the 802.11 1999 revision of Wi-Fi, two things happened. Firstly, Wi-Fi took off. Many people loved being able to browse the web, do email, and other network-related activities while on the move. So they could bring their laptop around and remain connected, and it was a huge success. But the second thing that happened was a growing realization, first among security experts and then even the general public, that the security of Wi-Fi was not quite up to the mark. It was lacking in a number of ways. It had originally been meant to be wired equivalent privacy, but it was not even that. Worse still, exploits were being published to allow attackers to break WEP. Something had to be done, and IEEE got started working on 802.11i, an amendment to 802.11 that would introduce much enhanced security. The Wi-Fi Alliance, meanwhile, realized that this was a big threat to the continued growth of the Wi-Fi market. What was to be done? They introduced WPA, Wi-Fi Protected Access, as a stopgap measure. It was something that was designed to be stronger than WEP, but not quite all the way to 802.11i. Therefore, as the name implies, TKIP. TKIP is one of the parts of WPA. It's Temporary Key Integrity Protocol, because WEP was well known to have poor key usage, as we have already seen in earlier videos. So one of the main features of WPA to address weaknesses in WEP was the introduction of TKIP, Temporary Key Integrity Protocol, which would immediately address some of the main problems with WEP. It was temporary, it was a stopgap measure, better than WEP, but not as good as using AES, which comes with 802.11i. In fact, it still uses RC4, but at least fixes some of the most serious problems with the way that keys were used in WEP. There were two main concerns, actually. One was the weakness of WEP, and the second main concern was that there was a lot of hardware that was out there that could not handle stronger but more computationally intensive cryptographic protocols like AES. Given these two concerns then, certain compromises had to be made, and so TKIP was one of these compromises. At least it fixed the major problems with the usage of keys. And at the same time, it was something that could be handled by the existing hardware that was out there. So we no longer appended the IV with the master key to form a per packet key. Instead, there was a per packet key mixing algorithm. This is one of the three main improvements of WPA, the use of TKIP. A second improvement is an improvement as far as message integrity was concerned, because WEP, as we noted earlier, has a very weak linear 32-bit CRC that it uses for its integrity check value. So Michael was introduced. Michael is a message integrity code algorithm with no multiplications. No multiplications means it's easier to compute, and it could still work on less powerful hardware. A third improvement introduced in WPA is replay protection. That was not something that WEP could do. So with WPA, we see that there is a sequence counter which helps in that aspect. So here is a block diagram of WPA. We see TSC, which is the TKIP sequence counter that helps with replay protection. And now going back to talk about TKIP as far as improving the key usage, we see phase 1 key mixing with the transmitter address and a transient key. So the use of transient key is another improvement over WEP. So instead of using the key directly, the master key is used to generate the transient key, and then it's mixed with the transmitter address. So we're having every pair of station and access point using different keys, and also the keys are changing every frame. So more powerful key mixing that helps to make the encryption harder to break, even though it's still using WEP encapsulation, meaning it's still using RC4. And then as far as the integrity protection is concerned, there's the use of Michael here. After all the bad publicity received by WEP, the IEEE had several items on its wish list of items to fix. One of these is that it's not a good idea for all the stations in a Wi-Fi LAN to share the same key, because that means that if one of these stations is compromised and the key gets out to an attacker, then everyone's security is compromised. 802.1x is one solution to this problem that allows each station to use separate credentials for its encryption and for its authentication. It also provides some other security benefits that we will talk about. As its name suggests, it was not originally designed for Wi-Fi security specifically, but it is under the 802 umbrella. That's why 802.1x. In fact, 802.1x was originally designed for Ethernet and then generalized for other 802 LANs, because even for Ethernet, it's useful to have network access control, and 802.1x is a good way of doing that. You have authentication and access control tied together by the 802.1x framework in a flexible framework. The key entities in 802.1x are a supplicant, which is the device wishing to access the network, an authenticator, which is like a guardian of the network entry point, and then an authentication server, which is an identity verification service, which may support multiple means of verification. Now let's compare this with what we have seen before for WEP. In WEP, there is a supplicant, which is a station that wishes to access a network, and then the access point acts as both an authenticator and authentication server in the sense that it is the guardian of the network entry point, and it also verifies the identity of the supplicant. But as we saw in earlier videos, this authentication part is a bit weak. If it's just based on having knowledge of a shared key, it's very weak. So there's much better authentication that can be done, and 802.1x helps us to do that. So we have seen one of the key features then of 802.1x is that it separates the guardian of the network entry point from the identity verification service. There are a couple of benefits of doing this. Imagine if we didn't have a separate identity verification service, but every access point, every guardian of network entry, needs to be able to decide whether to let any supplicant in. Then every access point would need to have all the security related information, all the credentials, and it's not a good way to do that because then the network becomes less secure. Rather, it's better to securely keep various credentials and authentication related functions in a central server like a Radius server. And this can function as the identity verification service, leaving the access points to focus on their job of guarding the network entry point. Furthermore, 802.1x also provides for flexible end-to-end authentication between the supplicant and authentication server using EAP. This has actually two benefits, the flexibility and the end-to-end. In terms of end-to-end, that means compared with the browser hijacking model that we had seen in an earlier video, now the supplicant talks directly to the Radius server, the identification verification service, and does not have to reveal its credentials to the authenticator even, which is somewhere in between. The flexibility comes from the use of EAP, which is Extensible Authentication Protocol. It supports multiple different authentication protocols in a flexible way. Some of these even allow for mutual authentication, two-way authentication, which is authentication of both the server and then the supplicant. There's another concept that we will briefly mention here, and then we will take a look at the flowchart to explain this further. So this is control port versus uncontrolled port. This is a logical concept at the authenticator, which in this case is the access point. Basically, the access point will have two ports for traffic from the supplicant, and the control port is the one that it does not allow the supplicant to use, does not allow traffic from the supplicant to pass through the control port until authentication is successful. So only EAP related traffic can pass through the uncontrolled port and move on to the Radius server. Here is the diagram showing what how these things are put together. We have a supplicant, which is the station, and an authenticator, which is the access point. And there's different places that the authentication server could be located. In this case, we have an example where it's in a separate network. And you can imagine that perhaps the station is roaming from its home service provider. So the authentication needs to happen at the home authentication server, which is possible with Radius, because Radius will help to locate the authentication server. So then we see that the EAP authentication is end-to-end, and it can be protected with PEAP or TTLS, so you have a secure encrypted end-to-end channel where even various legacy username and password based authentication methods might be supported. Things like EAP MS CHAP v2, for example. The flow of 802.1x is as follows. First, there is initialization, where the authenticator port for the supplicant is set to unauthorized, meaning that the control port is closed. So only the uncontrolled port is open for traffic from the supplicant, because this is the port that it needs. It needs to at least be able to have some communication through the network so that it can attempt authentication with the authentication server using EAP. And so that's what is allowed. Initiation is where the authenticator sends an EAP request to a special layer 2 address, and the supplicant responds with its identity, which then can be forwarded to the authentication server. EAP negotiation also needs to happen because there's different EAP authentication protocols that are supported by EAP, since it's extensible and flexible. And then the end-to-end authentication between the supplicant and server can then happen. Upon success, in the case of Wi-Fi, when we're using 802.1x with Wi-Fi, upon success, then the master key for this session is returned. And also the authenticator opens the control port to the supplicant so that all traffic can pass through. WPA, as we saw earlier, was a stopgap measure. It was put in place while awaiting the completion of IEEE 802.11i. Eventually, 802.11i was ready, and then the Wi-Fi Alliance moved on with WPA2. WPA2 and 802.11i introduced the concept of a robust security network, or RSN. Therefore, you might sometimes see this term RSNA algorithm or pre-RSNA algorithm. Algorithms related to 802.11i and WPA2 are known as RSNA algorithms. They are the ones that provide this higher security. And then pre-RSNA algorithms like WEP then are being phased out. In fact, 802.11i was mostly implemented in WPA, except that it was still using RC4, but with stronger key mixing. Finally, with WPA2, the introduction of a stronger block cipher came into the picture. This is known as AES, Advanced Encryption Standard. In WPA2, AES is used operating on blocks of 128 bits. So what happens is that you have an input of 128 bits, and that 128 bits of encrypted output comes out. The question is that how do we then use a block cipher like AES when we need to have a stream of data coming in and a stream of data coming out? Because our frames are much longer than 128 bits. There are multiple ways to convert block ciphers to so-called stream ciphers, which will support this streaming of input and getting a stream of output cipher text. And so therefore we see this CCMP, which is talking about the way that AES is used, basically how it's converted to a stream cipher, both for confidentiality and for integrity protection. For confidentiality, it uses AES in so-called counter mode, and for integrity, it uses CBC MAC. Therefore, we have CCMP, which is counter mode with CBC MAC protocol. For confidentiality, counter mode is one of the ways to convert a block cipher to make it a stream cipher, and in fact it's a recommended way. It's one of the 2 recommended ways of doing it, even though there's multiple schemes like ECB, OFB, CFB, and so on. ECB is electronic code book. Each of these has their acronyms. One of the advantages of counter mode is that both the encryption and decryption are parallelizable. This is a very useful property to have, because then it's better for the hardware to be able to compute in parallel. Meanwhile, as far as data integrity is concerned, a much enhanced data integrity mechanism is introduced. It's known as CBC MAC, and one thing I need to note here is that CBC MAC stands for cipher block chaining for message authentication code. We will see what cipher block chaining is in a couple of minutes. But first, this term message authentication code. Because we have people coming from 2 areas of expertise, one is security and cryptography, the other is data communications, sometimes we see problems with acronyms. MAC from the cryptography world stands for message authentication code. Message authentication code is a way of doing data integrity protection. You authenticate that the message has not been modified using message authentication code. It's a way of doing data integrity protection with a key and then doing some ciphering on that. However, from the data communication world, MAC often stands for medium access control. So we talk about the MAC layer of Wi-Fi, for example. In the Wi-Fi specs, then, we see that this is then called MIC, Message Integrity Code. But it's just terminology. So to be clear then, well, when you see CBC MAC, you know what it's referring to, depending on whether you're from one community or the other community. Okay, then we have each block of plain text being XORed with a previous block of ciphertext. We will see a block diagram, and I think that makes it easier. In either case, AES is used with a 128-bit key and 128-bit block size as the building block for both of these confidentiality and data integrity protection. CBC MAC is shown here. Cipher block chaining, so we see the chaining happening here. So we have encryption happening block by block, and then the ciphertext then is XORed. So this 128-bit of ciphertext is XORed with the incoming plaintext in the next block. And then you have the key as well. So this is the cipher block chaining. That's why it's called this. Eventually you end up with a very powerful MAC, or message integrity code. Counter mode, on the other hand, does not do that kind of chaining. So as we see here, each block of ciphertext then does not have to go into the next block encryption. And each block of plain text is XORed with something that comes out with a counter. So that's why we have the counter mode, and then we have the key. Here then is a picture of CCMP as used in WPA2. We see a transient key. So again, it's not the master key that's being used, but something that's derived. So this is something that even in WPA we saw, better than WEP. Then we have a packet number for replay protection, because it's just like the TKIP sequence counter in WPA. And we see that now we have the CCM encryption using AES. It's stronger than RC4. And the MIC here, as mentioned in the data communications world, we want to avoid using MAC for the same for message authentication code. It can be argued that the big three, as far as security services is concerned, are protection of confidentiality, protection of data integrity, and protection against impersonation. Now, we have already seen how WPA and WPA2 provide better confidentiality and data integrity protection than WEP. What about protection against impersonation, namely user authentication? How do they handle that, and how do they improve on WEP as far as authenticating the user is concerned? Let's recap first how confidentiality and integrity are protected in WPA and WPA2, and how they are protected more securely in these schemes compared with WEP. So recall that WEP uses RC4 with a poor usage of keys, and the ICV that's meant for integrity protection is a linear 32-bit CRC, not a cryptographic CRC. In WPA, RC4 is still used, but it's with better key mixing and per packet keys in a scheme known as TKIP, Temporary Key Integrity Protocol. As the name suggests, it's temporary, and then also the key usage is improved, so the key integrity is improved, therefore temporary key integrity protocol. Then Michael is used for integrity protection. In WPA2, things are enhanced even further with the use of a very strong block cipher known as AES, Advanced Encryption System. As it's a block cipher, it needs to be used in certain modes to convert it to a stream cipher. So it's used in counter mode for confidentiality and in CBC MAC for integrity protection. Now then, what about authentication? It would appear, we have already seen how 802.1x helps to solve authentication problems. So it would appear that we could just use 802.1x in Wi-Fi, and that would solve all our authentication problems. And then we can stop right here. However, there's also other considerations that the Wi-Fi Alliance takes very seriously, and that is how easy is it to use Wi-Fi, because it can impact the Wi-Fi market negatively if it's very difficult to set up and to configure Wi-Fi systems. So there are certain ease of use considerations that the Wi-Fi Alliance has considered, and because of these, then in home or small office Wi-Fi networks, there are some alternatives to using 802.1x. There is WPA PSK and also WPA2 PSK, where PSK stands for pre-shared key. So instead of using 802.1x, we use a pre-shared key, and this is known as personal mode. And another solution arising out of ease of use considerations is WPS, which we will talk about in the next video. So in this video, we'll focus on comparing personal mode with so-called enterprise mode, which is actually using 802.1x and is more secure. In personal mode, there is a pre-shared key that the whole BSS shares. Any new device can come into a network and be granted access as long as it has the shared key. Authentication and access are then based on knowledge of the shared key. If a device has this shared key, then it will be allowed to use the network. This is convenient for home users, but clearly it's not a best practice as far as security is concerned. There's also another convenience that has been put in place, and that is instead of entering a key directly, a user can enter a passphrase. So it can be a shared passphrase rather than a shared key that is entered all the devices and the access point. And then there are some algorithms to convert from passphrase to the actual key itself. Generally, these algorithms are okay, and so we don't see specific attacks based on the fact that we're using passphrases rather than entering the keys directly. Another thing to note is that the pre-shared key is not used directly, but it's used as the so-called pre-shared, the pairwise master key. Pairwise meaning between the transmitter and receiver, is a pairwise master key from which the transient key is derived. As we saw in the block diagrams for both WPA and WPA2, there is a transient key which is used as one of the inputs rather than the pairwise master key. This is better than WEP, where the key is used directly for encryption. Still, because of the sharing of the key among so many different devices, it's not really a good way to do authentication. Enterprise mode is the better way, and that uses the 802.1x model that we saw in a previous video. One of the benefits is that individual authentication credentials are used then. It's not sharing a key. EAP is flexible as mentioned before, so you can use different ways to authenticate the user, or maybe the user's phone in the case of SIM card identity. EAP does end-to-end communications, and some of the methods even provide for mutual authentication, which is better than just authenticating the client, because then it protects against man-in-the-middle attacks. Some EAP authentication methods provide a secure tunnel for legacy username and password authentication protocols that might not have that inherently. The pairwise master key is per session, and only the supplicant and authentication server can generate it, which is a secure way of doing things. So it's generated upon successful authentication, and the server passes it back to the access point. So much better than using personal mode. Besides the personal mode of WPA and WPA2 that the Wi-Fi Alliance has introduced to make it easier for people to use and set up Wi-Fi in home and small office environments, there's also WPS, Wi-Fi Protected Setup. This was introduced for convenience. It's certainly not introduced for security. It's not meant to make things more secure. And it was introduced some time ago in 2006. The Wi-Fi Alliance considered it too burdensome to require that the shared key be entered on each device that wanted to use a Wi-Fi network. Even if this just had to be done once, and then after that it would be remembered, somehow this was considered to be too troublesome. Even though it could be just as simple as entering a passphrase in each of these devices, that was still not easy enough. Alright, so then what easier methods were introduced? 4 methods were introduced in WPS to simplify the joining of a Wi-Fi network. 2 of the main methods that are found in most of the implementations are to push a button on the router to accept a joining request. What this means is that it's like you push a button on the router and then you make your request to join. So within a few minutes of pushing this button, the router will accept whatever request it receives. Seems a bit not secure. Well, what if an attacker's also trying to join and then wait for you to push the button and then the attacker can join? Alright, but anyway, that's beside the point. So then there's also the 8-digit numerical PIN that can be used. And we'll talk about these 2 methods. First, here's an example of a user interface on a Windows machine where you have the push button alternative of WPS. So at the point where the user would typically have to enter the security key, instead of entering the security key, the user could just push this button on the router, and then magically there'll be some signaling that happens in the background, and then this device becomes connected to the network. The security key would be set up on this network without the user having to actually type it in. The method with the 8-digit PIN is as follows. The WPS enabled device, let's say like the router, would then come with an 8-digit PIN. These might be hard-coded into a router so that it's not changeable, and often you might find it written on a sticker on the router or something like that. Then based on that, then when you try to add devices to the network, you go look for this PIN on your router, and then you go to your device and you enter this 8-digit PIN rather than your chosen passphrase. I suppose that Wi-Fi Alliance considered this to be more convenient than even entering a passphrase on whatever device that wants to join the network. But a hard-digit PIN, and also the PIN is consisting of digits. So there's only 8 digits, and each of them has 10 possibilities, 10 possible values, 0, 1 to 9, right? So the immediate thought is that, well, you could maybe brute force this PIN. But when you think about it, okay, so how many combinations are there? It might at first appear that you would need 10 million combinations because you have 8 digits, each of which can take 10 different values. So you just consider 10 to the 8, right? That is if this 8-digit PIN was implemented securely. However, there is a very serious flaw in the way that WPS implements this 8-digit PIN, because it checks the first 4 digits and returns an answer whether it's correct or not, basically, and it returns that. So you could actually brute force the first 4 digits first. You try all 10,000 combinations of the first 4 digits, find the right first 4 digits, and then reuse this correct first 4 digits together with your attempts to guess the last 4 digits. So that means that you're brute forcing the remaining 1,000 combinations for the remaining 4 digits. So you only need 11,000 attempts rather than 10 million. So that's much easier than 10 million. Clearly, this is not a secure way of doing things, so we don't recommend using WPS. Many people recommend turning off WPS if your router enables you to turn off WPS. What equipment do we need to do Wi-Fi penetration testing? We will be going through the equipment that we need, including hardware like computer Wi-Fi adapter or network interface card, and then also software related equipment. So that's the virtual machine, which is optional but convenient, the operating system that you would be using, and software tools that will be running on that operating system. Generally, there are not so many specific requirements for the laptop on which you're running your software tools, but one thing that you might want to know is that for some of the brute forcing type attacks where we're trying to recover a key by running through many different keys, then you would want to consider the amount of processing power that your laptop has. This is generally not that important. You could just use a regular laptop if you understand that this might need to be done. Brute forcing might need computational power, and you then could move the brute forcing processing to another machine, so perhaps a more powerful machine, after you have captured various information over the air and then stored it in a file. You could also be doing it in the cloud. So for example, you could be setting up something on Amazon Web Services and then doing the processing there. So besides the processing power, there's also other computing resources that this laptop would need to have. And generally, for something like our requirements, it depends on whether you're using a virtual machine. So if you're using a virtual machine platform, say VirtualBox or VMware, with a virtual machine, then you need to have enough RAM and resources to run the virtualization platform, and then to be running the operating system and software tools inside of it without affecting performance by having not enough resources. The laptop doesn't even need to have an inbuilt Wi-Fi network interface card, because for the most part we can just use USB Wi-Fi network interface cards. There can be difficulties if we are using something like PCI in the host machine and then trying to get access to this network interface card within the virtual machine. Generally, USB is the easiest and cleanest way. We will see that, for example, when we insert a Wi-Fi NIC, a USB-based Wi-Fi network interface card into a USB port, then VMware, for example, would pop up a dialog box asking if this network interface card should be available to the host machine or to the virtual machine, and you can then decide it. And in this case, that you're running your Wi-Fi penetration testing tools in the virtual machine, you would choose the virtual machine. Besides the laptop, the network interface card itself is something that you would need. And here we have a couple of important requirements. We cannot just use just any Wi-Fi network interface card. And as explained in an earlier video, the reason is that for general purpose usage, the network interface card would function as a regular station. When it's doing so, that is perfectly fine for normal Wi-Fi usage, for doing your web browsing or other internet-related networking over Wi-Fi. The problem is that when we want to do penetration testing, we need to be able to do more things over the Wi-Fi network, including things which might not be common in typical everyday usage. So for example, if we want to be able to see more of the frames that are being transmitted and received within that Wi-Fi network, within that BSS, we need to have either promiscuous mode, or even better, to have monitor mode enabled. So therefore, the Wi-Fi NIC needs to support monitor mode. And a second requirement, now this is something which is strictly speaking not a requirement, in the sense if you are very patient and can wait long enough, you can passively gather frames and then run your attacks. However, in practice, it takes a long time to passively gather frames, so it's much easier and better if the Wi-Fi NIC is able to inject frames even while it's scanning and listening. So not all Wi-Fi NICs can do that. So if you have one that can do that, as well as that is able to do monitor mode, then that is what you're looking for. Plus, as I mentioned, USB for convenience when a virtual machine is used. So how do you know which Wi-Fi network interface cards will support these requirements? There are different vendors clearly for network interface cards, and they use different chipsets. There's just a small number of different chipsets that are available, and these chipsets are what's inside the network interface card. It may be coming from a different vendor. This is, in a sense, more important than who makes the outside package, because the chipset determines the capabilities of what the Wi-Fi hardware can do. And in addition to the chipset, there's also the driver for the chipset that may also enable your monitor mode and packet injection to work freely, or it may restrict your capabilities to do that. So it's important to have a chipset and drivers that are cooperative to allow us to do our Wi-Fi penetration testing. In the previous video, we started talking about the equipment that you would need to set up to do your Wi-Fi penetration testing. So we started with talking about the laptop PC that you would be using, what kind of hardware you need for that. There's not so many requirements for that, but the Wi-Fi card that you are using would be something that's more critical, because it needs to be able to go into monitor mode and be able to inject frames into the Wi-Fi network. We ended up by introducing the importance of the wireless chipset, because if you want to know whether something can go into monitor mode and can inject frames, you should not be just looking at the Wi-Fi card itself, but the chipset that goes inside it. That chipset might be coming from a different vendor, and sometimes it might not be so easy to find out which vendor provided that chipset for the vendor that's selling the whole interface card. Furthermore, there can be a number of different drivers that could be used. The driver is what goes in the kernel space or the operating system to talk to the hardware and provides an API or other link to user space such that applications in user space can then access the capabilities of the Wi-Fi card. So that's also very important. You want to be using a Wi-Fi network interface card that has a suitable chipset and also a suitable driver that's not hindering or preventing your efforts to read and write Wi-Fi signals. Here are some examples then of chipsets and drivers that would be good for our purposes. Now you can also do some Googling and look around for other equipment that is recommended by other people. These are just examples, and we are not promoting any particular brand or saying that anything is better or worse. Just some of the examples that you might typically find if you just look around. So for example, for chipsets and drivers, Arteros chipsets are quite good. That's one example of a good chipset. Arteros is a vendor, and the chipset that they make normally would not have problems getting into monitor mode, injecting frames, and so on. There have been some reports of difficulties with one of the drivers for Arteros chipsets, that being the ATH6KL. So generally, as you see here, you can go look around and try to see what other people say about their tests with various equipment and their tests with various drivers. Rawling, Realtek are some other chipsets that generally have pretty good reports. But again, you can go do some Googling to find out and get people's opinions. And these chipsets can be found in various network interface cards, some examples being shown here. So things like the TP-Link TL-WN722N, which is pictured here. So it looks something like this. It's a USB NIC, so it's also convenient for when we're trying to use a virtual machine. And the alpha AWS 036H is here. Generally, there might be a number of different variations of the network interface cards, and the differences might be things like whether they support 802.11n or not, whether they support 802.11ac, that kind of thing. And sometimes also some models might have antennas that have higher gain, and so they can communicate with access points that are further away. Depending on your purposes, if you would like to be able to see access points that are further away than normal, you might also consider antennas that can support that. So you can extend the range of your Wi-Fi network using things like the high gain antennas. Antennas with higher gain might be having higher gain in all directions. So in that case, it would be an omnidirectional high gain antenna. So something that looks like this. There's no particular direction that it seems to be favoring. Whereas you can do even better in some cases by using directional antennas. If you know that the target access point is in a particular direction, then you can direct the communications, the wireless signals, to and from that direction. This is more power efficient. And so here are two examples of directional antennas. Now, Wi-Fi communications are in the unlicensed bands, and there are certain rules regarding the EIRP. So that's equivalent isotropic radiated power. And these rules then do not allow arbitrarily large power levels to be transmitted. This is because they are unlicensed. I mean, these bands are unlicensed. So then devices that are transmitting in these bands need to play fair and not exceed certain limitations. If the EIRP limitations were strictly based on EIRP limits, then directional antennas might not be too helpful, in a sense that you wouldn't be able to get further by using directional antennas and still remain within the limits. However, the limits do change and are more relaxed for the case that directional antennas are used. We have been talking about the equipment that you would need to prepare to do your Wi-Fi penetration testing. And we have talked about the requirements for your laptop computer and the Wi-Fi network interface card. If you want to be able to get some extension for the range of your wireless network interface card, there are options for adding antennas that can extend the range. Now, in this video, we will be talking about more software related aspects. So the virtual machine environment, which is optional but something that could be convenient, the operating system, and then software tools. The virtual machine you might want to use. Why might you want to use a virtual machine in the first place? Well, we're going to recommend using a Linux distribution called Kali Linux. And so one reason you might want to use a virtual machine to be running Kali Linux is that this distribution is not really meant for general purpose usage, and it is specialized for penetration testing and security related functionality. Because of that, we would recommend that you run it in a virtual machine so you can stop it when you're not using it, and you can be using something else which is more suited for general purpose usage when you're not using Kali Linux. Now, what kind of virtual machine environment would we want to use? There's different possibilities. There's things like VMware, and there's things like VirtualBox. VMware is commercial software that generally is easier to use and easier to configure than something like VirtualBox, which is free and open source, but you need to spend a lot of time to configure it, and then you might still have problems getting it to work. Anyway, this is up to you. One challenge when using virtual machines is to be able to get the hardware from the host machine to work. You want to be able to get accessories and things like network interface cards to be available to your virtual machine. So generally, we would recommend using USB Wi-Fi network interface cards because these could be easily accessible in the virtual machine. Whereas other kinds like PCI interfaces might not be as easily accessible. As for the operating system, normally a lot of people like to use Windows-based operating system or Mac OS, but these are good for various kinds of applications and for doing general purpose work and entertainment and so on. But when we're doing things like Wi-Fi penetration testing, we need to be able to have more control over the hardware, and there's certain things that we need to be able to do that are not typical or normal usage. So we might find, for example, that these general purpose operating systems do not have as good support for putting the Wi-Fi network, the network interface card specifically, into monitor mode and then seeing every packet that's being transmitted and received in the Wi-Fi network. Because for normal usage, people wouldn't be using monitor mode. So these operating systems are good for normal usage, but it might be a bit, well, not to say it might be, it can be quite challenging and troublesome to get them to do what we would like when we want to do Wi-Fi penetration testing. So we recommend using Linux, which allows you to have better control over what's going on at the lower layers and in the kernel. And there are many distributions of Linux. We would recommend not just using any distribution, but something that is specialized for security and penetration testing. One that has been around for some time is Backtrack, which is actually a merger of two different distributions and collects various tools. It was therefore designed to be convenient for doing penetration testing because of the various tools that it comes with. It was based on Knoppix, but rebuilt in 2013 by Offensive Security to a distribution that's based on Debian, and this is named Kali Linux. So generally people would use Kali Linux. Now, there's different ways to run Kali Linux because it can be run from a live CD. So that's where you just put the CD into a CD-ROM drive. You can also install from a CD onto a virtual machine, or you can download the virtual machine images and run directly. So whichever way you're using, we would recommend either install from CD into a virtual machine or get a virtual machine image directly and then just run that. So anyway, whichever way you're running your operating system, then various software tools are also available. In Linux, there are the so-called Linux wireless tools, which can be found in most distributions. They include things like iwconfig, iwlist, and so on. More recently, there's a suite of tools called IW. So you have IW space list and IW space whatever the different members of this suite of tools. These are more powerful and should normally be used rather than the older Linux wireless tools, even though IW config is still very convenient to use. Then there's all kinds of other software tools like the Aircrack NG suite. Used to be called Aircrack, then the more recent version of these tools is known as Aircrack NG. And there are quite a number of these tools. The most commonly used ones, and we will be going through these, are listed here. So things like Aircrack NG, Airmon NG, Aerodump NG, Air Replay NG, Aerolib NG, and so on. And then besides the Aircrack NG suite, there's other tools as well. Wireshark is just one of these other tools, but we will be going through some of these as we go along in other videos. Almost every distribution of Linux comes with the Linux wireless tools. These tools have been around since the early days of Wi-Fi, and they are a set of user space tools that talk to the drivers and allow us to configure the wireless card and also to retrieve certain information from them. For example, scanning results to scan the access points around the device. We're going to log in to our Kali Linux virtual machine and look at wireless tools for Linux, followed by the newer tools based on CFG 802.11. Typically, these Kali Linux virtual machines are configured with a password that's just the reverse of the root username, so TOOR. But you can change that if you like. We'll first open a terminal window and see what are the network interfaces. So at the moment, there's no wireless interface. Let me connect one wireless NIC, USB NIC, to my physical machine. It's a Mac, so VMware detects that I have done that, and it gives me the choice whether to connect that to Kali Linux or to connect it to my Mac. So I want to connect it to Kali Linux so that I can use it here. So that's what I'll click on. Alright, so now we see it. It didn't show immediately, but there we have it. Wireless LAN 0, WLAN 0. And we're ready to try wireless tools for Linux. Let's begin with IW config. We see WLAN 0, and the information given in the IW config output is not the same as what we get from the IF config. So we see things like IEEE 802.11, transmit power 20 dBm, encryption key off, power management off, various things like that that are not shown here. In certain distributions, I think in BSD, the Linux extensions for wireless are incorporated into the IF config display. So instead of having IW config, then you just type IF config and an enhanced version of IF config shows additional information. But anyway, in Kali Linux, this is what you might do, IW config. We can also try IW list. And it shows that we need to provide an interface. So IW list, WLAN 0. And what do we want to do there? Typically, we want to do some scanning. And this is showing us various access points that are around. And we see things like the frequency. So like this access point is using channel 6, which is at 2.437 gigahertz with an ESS ID of Singtel-CFD5 and so on with this MAC address. So we get these kinds of information just using the standard Linux tools without needing to even be using something like the aircrack NG. I mean, we're not there yet. We're just looking at this wireless tools for Linux that comes with most distributions. Now in this example here, I'm logged into root. So if you just log into a user account, you might not be able to see as much information because some of these provide limited information except for the root user. Besides doing IW list WLAN 0, scanning, followed by an optional ESS ID, like we just did, we can see that there are other options for using IW list. However, most of these are not very useful. We can try frequency. We can try channel. Gives you the same thing. It lists the different channels, which are the same as the frequencies. Let's go back to see what else there was. There's channel frequency, bit rate, encryption keys, and so on. But many of these, it's not able to show. So yeah, so you might see things like that. Event shows something. It shows the wireless events supported. But anyway, that's wireless tools. When we look at the newer IW command, we'll see that it supports more. It is able to show more information. So instead of using IW list, you might want to use IW instead. Let's take a look at the IW suite of Wi-Fi configuration tools. Like the earlier wireless tools for Linux, this is a collection of user space utilities for Linux and for configuring Wi-Fi in particular. However, it is more powerful than the earlier tools. You might still use IW-config for certain purposes, just for convenience, sometimes to see at a glance about the information related to Wi-Fi. But let's take a look at IW now to see how it can give you even more information than the IW list and related commands. So IW has something known as list as well. So rather than IW list being one command, everything is IW space something. Okay, so IW list gives you much more information about wireless LAN 0. So for example, the supported ciphers, 40-bit web, 104-bit web. And then interface modes. Information about the bands. HT, we see HT a few places. That stands for high throughput, and that tells us that this is 802.11n, the physical layer that it's looking at. is 802.11n, supporting various bit rates. These bit rates are the non-HT bit rates, so that's the 802.11 whole IW list. IW list being one word. Now with IW space list, this is part of the IW tools. And all kinds of frame types that are supported. HT capability overrides. Remember, HT refers to 802.11n, high throughput. So that's much more information here with the IW command than with the previous set of wireless tools. We can also do scanning. So this is one way of doing it. If we forgot what are the wireless interfaces, we can do ifconfig. We see that our WLAN 0 is still there. iwconfig also gives us that. And anyway, so iw def WLAN 0 scan. And this scans for surrounding access points and provides more information than the wireless tools that we saw earlier. So for example, for this SSID Singtel CFD5, we have the beacon interval, how often the beacons are sent, and then various things like the supported rates. WMM is about quality of service, so there's best effort, video, voice. There's 4 classes of traffic that are supported, and that's actually from the 802.11e specifications, at least the amendment, which then got rolled into 802.11. What else can we see? Yeah, we see Daniel Wireless Software. We see RSN's robust security network. That's a concept that was introduced with the 802.11i amendment, so including the information about ciphers that are used. And again, HT capabilities is about 802.11n, high throughput. That's what HT stands for. And we also see information about WPS. So this access point supports WPS. What else can we do with IW? By the way, instead of typing DEV, in cases where there's no ambiguity, you can drop the DEV. So then something like IW's WLAN 0 scan will also do the same scan. You can do IW event to listen to events, but let's not spend too much time in looking at IW, because we're going to be looking more at the Aircrack NG suite of tools for our purposes. I just want to point out that we can also do things like turning on monitor mode with IW. Let's say we turn on monitor mode for our Wi-Fi card. Then the question that we would have next is, what would be a good way to see the incoming frames? Because we're going to be seeing lots of different frames as we have monitor mode turned on. Wireshark is a popular and powerful tool that lets us inspect the frames that are coming in, and it works perfectly with monitor mode, as frames are captured from different Wi-Fi networks around us. It will display the frames and a lot of useful information about the headers and the contents of these frames. we will now demonstrate the use of Wireshark after we have turned on monitor mode. In fact, we're going to see the difference before monitor mode is turned on and after monitor mode is turned on. Let's explore more on monitor mode and the differences between monitor mode and managed mode. So let's first take a look here and confirm that we are in managed mode. So in managed mode, we are operating as a normal Wi-Fi network interface card would, and we're not seeing much of what goes on around. We can do scanning, which is what a normal Wi-Fi NIC card might do, but we can't be capturing a lot of traffic that's going on between access points and the stations. So let's, rather than just believing what I say, let's take a look. When we start Wireshark and we're in managed mode, let's see what we can see. Wireshark is starting. So it's a network analyzer. It's not specific to wireless, but it's okay. Now, since I'm running as root, I would get this warning because generally it's not good to use it as super user, but anyway, it should be okay for our purposes. Now, we see that we have to choose a network interface that we wish to be capturing traffic on and monitoring. There is no WLAN 0 in this list. Let's see if perhaps it's because WLAN 0 is not up. Indeed, we see that WLAN 0 is not listed in the interfaces here. So no problem, we just turn it on. And we do that by using ifconfig WLAN 0 up. That brings it up. So now it's listed here and we see WLAN 0. Double click on it and ooh, there's nothing that we can see here. Well, generally it's not so bad. If the station connects to an access point, then we would be able to see something. But that will be very limited because it would only be its own traffic to the access point, and so not very helpful for Wi-Fi penetration testing. Let's consider now if we change this to monitor mode. How do we change it to monitor mode? There's several ways to do that. Let's try. One is arrow-dump ng. An interesting thing about arrow-dump ng is that it will not operate in managed mode, so it will automatically turn on it will automatically turn on managed mode for you. That's a useful side effect that it has. In fact, let's verify once again that we are in managed mode. Then we do arrow-dump ng. We need to specify the interface. Arrow-dump ng WLAN 0, and Wireshark tells us that this network adapter is not running anymore because what happened was that it turned on monitor mode, as we see here. So for a very short amount of time, WLAN 0 was unavailable. That's why Wireshark complained. Now we look at ifconfig, we see that yeah, it's there, it's up. And in fact, it is up because when we look at arrow-dump, we see that it's capturing data from various surrounding access points. We see that here. So it's in monitor mode, it's capturing data from surrounding access points. Coming back to Wireshark then, since it lost the capture, no problem, we started again on WLAN 0. And by the way, since we started monitor mode on WLAN 0 using arrow-dump ng, which did that as a side effect, it didn't create a virtual interface such as WLAN 0 mon, which airmon ng would have done. So depending on the way that we turn on monitor mode, there's different behaviors. With airmon ng, it creates that virtual interface for our convenience so that we are very sure that that's in monitor mode. With arrow-dump ng, it just turns on monitor mode for the existing physical interface and doesn't bother creating a virtual interface with a different name. But no big deal. So here we see the amount of data that is captured. So all these frames that are coming in to Wireshark, and then we can look at these and see what's in them. Request to send, clear to send. These are some of the control frames that are used in Wi-Fi systems, because there are multiple stations that are connecting to the network through an access point. So it does this for medium access control. Anyway, that's a whole other topic about how the MAC protocols work in Wi-Fi. It's very interesting too, but it's not really relevant for our purposes for today. So anyway, we see all these frames going between access points and devices. We see that Wireshark understands MAC addresses to have certain prefixes, meaning that they are manufactured by certain vendors, because the different vendors are assigned MAC addresses in certain ranges of the address space. So it automatically interprets that for us, TP-Link, Apple, and so on. Let's say we turn on monitor mode for our Wi-Fi card. Then the question that we would have next is, what would be a good way to see the incoming frames? Because we're going to be seeing lots of different frames as we have monitor mode turned on. Wireshark is a popular and powerful tool that lets us inspect the frames that are coming in, and it works perfectly with monitor mode, as frames are captured from different Wi-Fi networks around us. It will display the frames and a lot of useful information about the headers and the contents of these frames. We will now demonstrate the use of Wireshark after we have turned on monitor mode. In fact, we're going to see the difference before monitor mode is turned on and after monitor mode is turned on. Let's explore more on monitor mode and the differences between monitor mode and managed mode. So let's first take a look here and confirm that we are in managed mode. So in managed mode, we are operating as a normal Wi-Fi network interface card would, and we're not seeing much of what goes on around. We can do scanning, which is what a normal Wi-Fi NIC card might do, but we can't be capturing a lot of traffic that's going on between access points and the stations. So let's, rather than just believing what I say, let's take a look. When we start Wireshark and we're in managed mode, let's see what we can see. Wireshark is starting. So it's a network analyzer. It's not specific to wireless, but it's okay. Now, since I'm running as root, I would get this warning, because generally it's not good to use it as super user, but anyway, it should be okay for our purposes. Now, we see that we have to choose a network interface that we wish to be capturing traffic on and monitoring. There is no WLAN 0 in this list. Let's see if perhaps it's because WLAN 0 is not up. Indeed, we see that WLAN 0 is not listed in the interfaces here. So no problem, we just turn it on. And we do that by using ifconfig WLAN 0 up. That brings it up. So now it's listed here and we see WLAN 0. Double click on it and ooh, there's nothing that we can see here. Well, generally it's not so bad. If the station connects to an access point, then we would be able to see something, but that will be very limited because it would only be its own traffic to the access point, and so not very helpful for Wi-Fi penetration testing. Let's consider now if we change this to monitor mode. How do we change it to monitor mode? There's several ways to do that. Let's try. One is arrow dump ng. An interesting thing about arrow dump ng is that it will not operate in managed mode, so it will automatically turn on it will automatically turn on managed mode for you. That's a useful side effect that it has. In fact, let's verify once again that we are in manage mode. Then we do arrow dump ng. We need to specify the interface. Arrow dump ng WLAN 0, and Wireshark tells us that this network adapter is not running anymore, because what happened was that it turned on monitor mode, as we see here. So for a very short amount of time, WLAN 0 was unavailable. That's why Wireshark complained. Now we look at ifconfig, we see that, yeah, it's there, it's up. And in fact, it is up, because when we look at arrow dump, we see that it's capturing data from various surrounding access points. We see that here. So it's in monitor mode, it's capturing data from surrounding access points. Coming back to Wireshark then, since it lost the capture, no problem, we started again on WLAN 0. And by the way, since we started monitor mode on WLAN 0 using arrow dump ng, which did that as a side effect, it didn't create a virtual interface such as WLAN 0 mon, which airmon ng would have done. So depending on the way that we turn on monitor mode, there's different behaviors. With airmon ng, it creates that virtual interface for our convenience, so that we are very sure that that's in monitor mode. With arrow dump ng, it just turns on monitor mode for the existing physical interface and doesn't bother creating a virtual interface with a different name. But no big deal. So here we see the amount of data that is captured. So all these frames that are coming in to Wireshark, and then we can look at these and see what's in them. Request to send, clear to send. These are some of the control frames that are used in Wi-Fi systems, because there are multiple stations that are connecting to the network through an access point. So it does this for medium access control. Anyway, that's a whole other topic about how the MAC protocols work in Wi-Fi. It's very interesting too, but it's not really relevant for our purposes for today. So anyway, we see all these frames going between access points and devices. We see that Wireshark understands MAC addresses to have certain prefixes, meaning that they are manufactured by certain vendors, because the different vendors are assigned MAC addresses in certain ranges of the address space. So it automatically interprets that for us, TP-Link, Apple, and so on. We will now continue to look at the features of Wireshark, such as the ability to filter for frames related to a specific access point, because there's a lot of data out there. Even though Wireshark is helpful to show us the contents and the headers of the different frames, sometimes we don't want to see everything. We just want to focus on, let's say, for example, frames belonging to a specific access point. We will see how Wireshark and arrow dump can be used in conjunction with each other. So for example, we would be using arrow dump ng to find out the BSS ID or MAC address of the particular access point, and then we can put that into a filter in Wireshark and filter out everything else except for frames that are going to or from that access point. The combination of arrow dump and Wireshark is very powerful. There is some overlap in the functionality and features, but they are different tools, and it's often a good idea to use both of them together. As we can see from arrow dump, there's a number of different access points around, and Wireshark is capturing the frames from all of them. So we might often want to take a look at frames that are just for one of the access points. So we can do that. For example, there's a access point test 1 here with a BSS ID of 00. This is just the MAC address, the BSS ID. By the way, the information provided by arrow dump, we can see the BSS ID and ESS ID. Remember that an ESS might have multiple BSSs because it's an extended service set. So you can imagine a situation where you have the same ESS ID. Maybe it's a company that has a few different access points with the same ESS ID, but they will have different MAC addresses. So those access points will have different MAC addresses, which would identify their BSS IDs. So the different BSSs would then be what's listed on this side. We see the power beacons data. These columns here represent the number of beacons or number of data frames that have been received while we have been monitoring since we started arrow dump. And then other useful information like the data rates, the encryption, WEP, WPA, and so on, and the cipher as well. So in WPA2, it might be using CCMP, whereas if you are using WEP, then it's just WEP, which is actually RC4. So let's say we're interested in this test 1. We can copy the BSS ID and apply a filter to filter out the other access points. Wireshark has a large number of filters, as we saw. But let's, instead of typing it in, let's just paste it here. So this access point, I know is a Cisco Linksys access point. So correctly, Wireshark put the source as Cisco Linksys. And I'm using a network interface card that is a TP-Link network interface card. So we see both Cisco and TP-Link correctly identified. Anyway, we see probe request and probe response. There's beacon frames also coming from the access point. So it's very useful. You can take a look at the contents of the beacon frame, for example, and well, you see binary data, but it interprets it up here. So this is useful for seeing what's inside each of the frames. Let's stop arrow dump, and one question you might be having in mind is, now this is in monitor mode. If I want it to go back to manage mode, how do I do that? What about AirMon? Well, you don't know, because AirMon NG, we know from previous experience that it creates a virtual interface and puts that in monitor mode. So now if we're just having our physical interface in monitor mode, can AirMon NG stop it for us? Let's try. No, because AirMon NG is expecting that we have a virtual interface that's in monitor mode, which is what AirMon NG would have done if we had started the monitor mode using AirMon NG. So what can we do? Not to worry, we can use IW, and we can use IW to then turn off monitor mode. So set type managed. Oops. The device or resource busy. Well, we can't change the mode from monitor to manage while the interface is up, as we saw here. It's up. So first we can bring it down. And then Wireshark complains, as it should, because it's no longer able to get the frames that are coming in from there since it's down. And now we can change from monitor mode to manage mode. So we go back to this command. Now it doesn't complain. And yeah, so this is a way, for example, if we had done arrow dump and then we cannot use AirMon NG to bring it back to manage mode, we can use IW. So IW, the device which is WLAN 0, and the set type managed. We could have turned on monitor mode also similarly by doing this, and then we see that it's in monitor mode. So back to manage mode, and then when we're ready, we can do ifconfig to bring it up again. Let's take a look at how we can test the capability of our network interface card to inject frames into a Wi-Fi network while in monitor mode. Firstly, we take a look at the configuration. So we have WLAN 0 and ifconfig Okay, so with ifconfig we see that the network interface card is down, and we can bring it up so that then we see that it's up. Now, in order to do an injection test, we need to turn on monitor mode. But the injection test that we're going to do is using air replay ng, and this generally works better when monitor mode is turned on for a specific frequency or a specific channel rather than the general scanning monitor mode that is looking at all the different channels. What do I mean by that? If we look at Ammon ng, we see that we can optionally select a particular channel or frequency. So this is what I mean. If you try to do your injection test without setting a specific channel or frequency, sometimes it may not work. Depends on your network interface card. Anyway, so how do we know which channel or frequency we want to be doing our injection test on? Depends on where we have access points. So let's start by doing a scan to see where we have access points around. So we see one access point here, and then we see a second access point with SSID Daniel Wireless software. We're going to try on this one. The channel is channel 11. All right, so that's what we were looking for, channel 11 for Daniel Wireless software. Now that we know that, we go back to Ammon ng, start it with the network interface card on WLAN 0 and then channel 11. Alright, so WLAN 0 mon has been created, and meanwhile WLAN 0 has been disabled. iwconfig and ifconfig are giving us what we expect, so WLAN 0 mon is ready to go. Right, so what we're going to do is use air replay. Now air replay can be used for a variety of different purposes in Wi-Fi penetration testing. It is generally used for injecting various kinds of frames, and these can be part of different attacks. So it can be used to inject up frames. It can be used to inject frames that are related to a handshake, various kinds of things. But for now, we are going to use a function of air replay that allows us to test. So let's say if we try to do this, there's a number of other options, but the simplest way is to just do ---- test, and then the interface. We need to do air replay ng. Now, since WLAN 0 is down, it gives us this error message. So that's one reason why Ammon ng is good for turning on monitor mode, because it at the same time brings down the wireless interface that is not in monitor mode. So that's WLAN 0. So anyway, so in case we make mistakes like this, it will say no such device. All right, so then we go with WLAN 0 mon, which we had set to be monitor mode for channel 11, and we know there's an access point there, because otherwise you might see something like found 0 AP here, because what this air replay ng test is doing an injection test, and it tries at first by sending broadcast probes. If it finds no access points, that's not very helpful. But so it found one access point, and then it tries directed access probe requests. directed to that particular access point. We see the MAC address of the access point here. We see the channel, so we had selected 11 before, and the SSID that we saw was this. It's confirming that this is the SSID. The ping times that follow here give you some indication about the delay in communication with this access point. So larger values would indicate that the access point is further away. And then we have a power value, 28 of 30, so 93%. Generally, if the access point is closer, we would have a higher success rate here. So this is pretty good. I mean, we can try again, and then we can see. So it might not be 28, it might be something like 30. So we have 100% success this time. And so yes, we have successfully done packet injection. So we know that we can turn on monitor mode and we can inject packets. We are ready to go and do penetration testing. In the last video, we introduced basic injection testing, where we could test the capability of a wireless card to inject frames into a Wi-Fi network. This can be useful as part of determining if the network card is going to be useful for Wi-Fi penetration testing. In certain cases, for example, if we want to be in some kind of stealth mode and we don't really want to be testing our injection capabilities on actual Wi-Fi networks, because maybe, for example, we don't want to alert the target access point that we are out there and trying to do something to break in, right? So in those sorts of cases, we can still do injection testing, but we will need to do it on our own Wi-Fi card. So we will have two Wi-Fi cards, and one will act as an access point. The other will then inject frames into the network of the first one. For the next couple of injection tests that we will do, we will need to have two wireless interfaces. Let's take a look. Okay, we have WLAN0 and WLAN1. What about ifconfig? In fact, let's do this. Okay. Neither of the WLAN interfaces is up, so we will bring them both up. We'll bring up WLAN0 with ifconfig WLAN0 up, and then bring up WLAN1 with ifconfig WLAN1 up, and verify that they are both up. So yes, they are. And we're going to be trying some injection attack tests. So these attack tests involve these two wireless interfaces, because one of them will be acting as an access point and the other will be injecting packets, doing some simulated attacks, which we can do in various ways. So let's say we turn them on using IWDEF, WLAN0, set type monitor. Okay, they have to be down first. Should have turned them to monitor mode before we brought them up. So ifconfig WLAN0 down. We do the same for WLAN1, and then now we can set them to monitor mode. Now it doesn't complain. IWconfig to verify that they are both in monitor mode. Now we can bring them up again, and we will be ready to run our attack injection test. Okay, both are up. We will use a replay for this as in the other injection tests. And then -9 or -- test either way. -I WLAN1 means that WLAN1 will be the interface that will be pretending to be an access point in terms of its responses. So it will receive packets and then respond in certain ways to what WLAN0 is injecting into the network. Let's see what happens. So it's trying broadcast probe requests, injection is working, card-to-card injection. All right, so what did we see? We saw that most of these attacks work. Sometimes attack 5 might not work, and that could be due to certain drivers, differences in the cards, but that's okay. Generally, we see that most of these attacks are working. It's going card to card over the wireless network. And we can also run the attack injection test with AirServe. AirServe is another member of the AirCrack-NG suite. What it does is it allows a Wi-Fi card to be accessed through TCP/IP in a client-server manner. This way, we can share an access card among multiple applications. And in fact, the application could be running somewhere on the other side of the world, and it accesses the network card to configure and control it just over TCP/IP and using AirServe-NG. So it's quite interesting and powerful. You can imagine doing a penetration testing from somewhere else, as long as perhaps your associate is physically present with Kali Linux and having set up AirServe-NG. But you do something like this. So it's opening port 666 on WLAN0. We can go to another terminal and do air replay ng -9 and then loop back. So we see here the AirServe-NG reporting the attacks happening, and in the other terminal we see that the injection tests are happening through AirServe-NG. Finally, we've reached the point where we're ready to launch some actual attacks. We're going to begin with attacks on WEP. Later, we will also look at other Wi-Fi security mechanisms and how we can launch attacks on those mechanisms as well. Just a reminder here, it might be illegal in various places. It probably is illegal in various places to be doing these things on a network where you don't have permission to be doing it. So don't do anything illegal. We begin with passive attacks, where we are just listening, and even by just listening, we're able to figure out the key. Later, we will also look at active attacks where we can inject frames as well into the network. These can be helpful in situations, for example, where the network is idle and there's not much traffic that's going on inside the network. There are various possible attacks on WEP. We begin by a passive attack on a WEP access point, attempting to discover the key of the access point. We are not going to inject frames, so this is called a passive attack, which assumes that there will be some other activity going on in the network, so we can just listen. We will be using AeroDump-NG and AirCrack-NG for this. Let's begin by taking a look at our wireless configuration, which we see, well, we have WLAN0 and WLAN1. We don't actually need to use both of them. So let's say we use WLAN0 and we run AeroDump on it. I have two windows open because I'm going to be running AirCrack in the bottom window. We don't need to finish gathering frames in order to start aircrack ng. So arrow dump ng is going to be capturing frames, and then aircrack ng, once it has enough frames, will be able to recover the key. So we will run arrow dump ng up here. One thing we will do first before capturing frames from the desired access point is to take a look at the different access points around, because we want to know the BSS ID of the desired access point. In this case, our ESS ID is test1, so we can get the BSS ID, which is the MAC address of the access point, by copying from here. And we also get the channel number, which is channel 6. And we quit by just doing a Control-C. So now we can do a more targeted dumping for specifically BSS ID, and then we paste. And we also want to specify the channel. So that's channel 6. Last but not least, we want to specify a place where we can write the output file. So we pick test1 as the name for the output file. So what it's going to do is it's going to be capturing all the traffic on this Wi-Fi network, test1, and putting it into a file. So we see that it's capturing packets, and it's not very fast. It's getting a lot of beacons, but look at the number of data packets, not much. So this is going to take a very long time. Well, we can already start aircrack ng. Meanwhile, before we do that, let me just show you what has happened here. Previously, so it just created these files. Previously, they were not here. Now it has created these 4 files because I specified that the output file will be called test1. Notice that it added a -01 at the end of the name, so it's test1-01. The reason being that we don't want to overwrite something. If already there was a test1, we didn't want to overwrite it. So it will append 01, and then the next time it appends a 02, and so on. Also, the output comes in 4 different formats. So we have the cap file, which is what Wireshark uses, but also CSV, and then Kismet CSV and Kismet Net XML. These are 4 different formats that can be used, because for some purposes you might want to use one or another. So then let's try running aircrack ng. And here we can optionally specify the BSS ID. We don't have to specify the BSS ID here because we have already done filtering in our capturing in arrow dump. So this is optional. But imagine if arrow dump was not filtering specifically for this BSS ID, we can filter at this point. So in that case, the capture file could be bigger, and we're just picking out those that are relevant to this BSS ID. So then we just need to specify the name of the file, which is test1-01.cap. And there we go. Aircrack ng is running. It says it failed because there were not enough IVs. You see that we only got, what, 400 something frames. It needs thousands of IVs in order to succeed. What it got here, we see that it got only 437 IVs because at that time the number of data frames was 437. And as it says up here, the attack will be restarted every 5,000 captured IVs. So aircrack ng is smart about that. Even as test1-01.cap is being populated, it will wait, and then it will continue with trying to find the key. And notice that it is using the PTW attack. This is the most efficient way to retrieve the key in the sense of needing the fewest IVs. Later we will see that if you use some of the earlier, older ways, you might need more IVs before you can get the key. So let's try to have more traffic in this network so the number of frames can increase at a higher rate. So we see that the key is found already, because what happened was that I started doing some file transfers and the number of frames is much higher now, 70 something thousand. So looking back at what happened here, we see that it took At first it got 437 IVs, that was not enough. Then at 5,000 it continued, and 10,000, see 10,000 IVs, that was still not enough. Kept waiting, and then 15,000 IVs, still not yet. 20,000, and so 20,029 IVs. At that point it found the key, 41A19005AA. In the last video, we saw a passive attack on WEP using aircrack-ng. We will see another passive attack on WEP because the default uses the very efficient PTW that does not require a lot of different IVs. So in just over 20,000 IVs, it was able to find the WEP key. We can also use an older but less efficient way, which is the correct way, and we will see that in this video. Both are passive attacks, meaning that the attacker is just listening for frames in the Wi-Fi network. And this has the advantage that it's harder to be detected because it's just listening. So whoever's operating the Wi-Fi network would probably have no idea that the attacker is listening, capturing frames, and then running this attack on the frames. The disadvantage of using passive attacks is that it needs traffic to be in the Wi-Fi network. When we have less active network, it might take a long time to gather enough different IVs. Still not yet. 20,000, and so 20,029 IVs. At that point it found the key, 41A19005AA. The file is continuing to transfer, so we see that we have number of data frames still increasing. And what we're going to do is to try to use a correct attack, which is less efficient, so that needs more IVs. So we put a -K and let it run. So 150 something thousand IVs, still not enough. Still going. Speeding up the video here to save time. 181,000 IVs. Thankfully, the file that we're transferring is pretty large, so the number of data frames are still going up very, very quickly. By the way, we see what's happening here. There's two stations that are connected to this access point, associated with this access point, and I'm transferring a file from one of them. So I have turned on file sharing on one of them, and the file transfer is happening from that shared folder to the other one. So that's why we have the number of frames for both of these stations increasing rapidly, because a file is being transferred from one to the other, going to the access point, and then from the access point to the other station. And the total number of frames is effectively then double of the individual number of frames for the two of them. Over 300,000 IVs so far. It's a statistical attack, so sometimes we are less fortunate and we might need more IVs, other times fewer. Speeding up the video again. This time the speed up is much more. And finally the key is found here. It took 513,000 IVs, but finally it did it. So it's a statistical method, and sometimes it just takes that many IVs. I tried another time, it was like about 200,000. It varies, and it can vary quite a lot. We have seen a couple of passive attacks on WEP networks. We will be looking at some active attacks in the next video. Let's talk a bit about them before we get into that. In the case where a network is idle or there's low traffic, it helps to be able to inject frames to stimulate traffic to be coming from the access point or other devices in this network. This allows the attacker to be able to capture enough frames with different IVs in order to recover the WEP key. The disadvantage of active attacks is that there's a higher chance of detection. Note also that it's not normal traffic that will be injected in these attacks. So it's quite possible that an access point could detect anomalous, strange traffic and realize that an active attack is being carried out. The most common varieties of active attacks on WEP are listed here. So up, request, replay, chop, and fragmentation. We will be showing these in subsequent videos. And we will be using a tool known as Air Replay NG to do this. We have already seen Air Replay NG used for injection testing, and that's with the -9 or --" test option. There are also other options. For example, --" off count to or -0. These are synonymous, just like -9 and --" test were synonymous. This is to deauthenticate a station or all stations. This is useful in certain attacks because then you might expect that the stations will try to reauthenticate, and that traffic could be valuable for certain attacks. There's other things as well, but for now we want to focus on --" up replay or -3, --" chop or -4, and --" fragment or -5. What can we do after we have recovered a WEP key? A lot. However, just as an example, we will take a look at using Wireshark to view the contents of various frames. And these will be viewable after the WEP key is recovered. And we'll see how we can put that into Wireshark, how we can let Wireshark know about it so that then Wireshark can interpret the frames using that WEP key. We have been able to find the WEP key in two ways. One is using the more efficient PTW attack, but also Correct was able to do it. Now, the question is, what can we do with the WEP key? And we will use Wireshark to demonstrate that once we have the WEP key, things are much easier in terms of being able to see encrypted packets and the data within the different frames in the Wi-Fi network. So let's start Wireshark. And remember that the file name was test1.cap. So it's a huge file because we captured a lot of data in order to get the Correct attack to successfully retrieve the WEP key. So we double click on it to open. Wireshark is taking a while because there's just many packets that we see 1.2 million packets. Now, when we first take a look at it, it's full of different Wi-Fi packets. So the first thing that we want to do is to apply a filter. Let's do this. I will provide you a URL that you can use to go find more of these filters just for your convenience. But for now, anyway, let's proceed with this. So this is a filter for Wi-Fi frames of type 2. Type 0 and type 1 are management and control frames. So type 2 is for data frames. We will apply this filter and we will see that these frames will be filtered out. So we will be left with the data frames. Now it needs to rescan and apply the filter again because this is such a large capture. It's taking a while, but normally if you don't have as much data in there, it will be faster. All right, so protocol 802.11 as expected. And these are the data frames. We can take a look at all kinds of data, but we don't really know what kinds of data. And the reason, we can go take a look, the data is all encrypted. So Wireshark is not able to decrypt without us providing it a WEP key. The way that we can provide the WEP key and then Wireshark will know how to decrypt the data is to go to Edit Preferences, Protocols, look for IEEE 802.11, and edit the decryption keys. We want to add a WEP key, and we enter it here. Remember that the WEP key that we recovered using our passive attacks was this. So we enter it, click OK, and now it's rescanning, but this time it's going to be able to make more sense of the data frames that it's seeing. Because this time it has the WEP key, so it's going to be able to decrypt the data frames, and instead of just showing data here, it's going to be showing that some of them are HTTP, some of them are Dropbox, various data frames that it sees. So again, it's scanning because it's a large capture. And another thing that we will see is that if there's various plain text, then it might be things like usernames and passwords, and such data will also then be visible in tools like Wireshark. So we see decrypted WEP data, and yeah, we can see more information that some of these are TCP retransmissions and so on, because we can see the higher layer information as it has been decrypted already. If we look in here, we can see beyond 802.11. We can see the LLC, IP, and TCP layers. As an example of finding more specific information, now that we have the web key and are able to decrypt the data over the Wi-Fi network, I shared some files on a Samba file server and viewed those files from another machine in the same Wi-Fi network. To find these related frames out of the many frames that were captured over the air, we can filter. There's a lot of different filters, so Wireshark is really powerful in this sense. It recognizes lots of protocols and understands lots of protocols. But in this case, we're talking about file sharing with Samba, so we just put at NNSMB. More specifically, the file name was secret.txt, and there was some text there about some secret, supposedly. So we can even do something like this, SMB file contains secret, and filter for this. It's rescanning again. We speed up the video that shows the scanning, so we're almost done. And here we have them, the frames that are related specifically to the Samba protocol. There's requests and responses, and we see here secret.txt, Samba, message block protocol. You can use your imagination, the sorts of things you can do once we have the WEP key. As mentioned in the earlier part of this video, there are various references for the sorts of filters that we can do for WLAN for Wireshark. You can Google to find. This is just one example, and the URL is there. I have no connection with the people who did this, but it's kind of a useful thing, useful reference that you can use to do filtering as appropriate to find the frames that you're looking for. Now we move on to a demonstration of an active attack on WEP. And in this active attack, we're going to be sending ARP requests using AirReplayNG. Suppose we have a Wi-Fi network that is relatively inactive. There's not much traffic on it. So let's try an active attack. We will try an ARP request attack. The way the ARP request attack works is that the Wi-Fi network card that we are injecting frames with is going to be sending ARP requests into the Wi-Fi network. But in order to be able to do that, it needs to authenticate and associate with the network first. So it will do that using air replay ng. After it has done that, then it can start the ARP request. What it's going to do is to keep sending ARP requests into the network. Why is that helpful? The reason is that as it's a wireless LAN, the access point must rebroadcast any ARP requests that come in from any associated devices. The reason is that it's supposed to look like a LAN, a broadcast medium. So when an ARP request comes in, it needs to go out to every device in the Wi-Fi network. This means that the access point will be generating these rebroadcasts with different IVs, and this will allow us to capture frames rapidly and eventually have enough frames to find the WEP key with. We begin by looking at the IW config, and we see we have WLAN 0 and WLAN 1. So this time let's try WLAN 1. They're both in monitor mode already, so we don't have to put them in monitor mode. Well, anyway, arrow dump and G will do that for us. I have changed the channel of test 1 to 11, and it shows 11 here as expected. I have also changed the WEP key so it wouldn't be the same as the one that we retrieved in our passive attacks. However, it doesn't show on arrow dump ng, of course, because arrow dump ng just knows that it's using WEP and doesn't know the key at this time. We need to use aircrack for that later. The way to do an ARP request attack is to use air replay. Now we're just going to do this air replay attack. We're going to try it without authenticating. Notice that we are not authenticated with test 1. We are just scanning up here with arrow dump. We're just monitoring what's going out in these different Wi-Fi networks. So we don't expect to succeed. But let me just show you. We copy and paste the BSS ID as usual. Paste it here. And then typically we will want to put in our MAC address, but I haven't found that yet. So let me just press enter and do something like this to get our MAC address. iwdef WLAN1 info. So this is the MAC address. I'll copy this. Then press the up arrow twice to get back where we were and paste it in, and then WLAN1. Now we don't expect this to succeed because we haven't even authenticated with test 1 yet. Furthermore, we see another problem, and this is something which I intentionally made a mistake now to show you what can happen sometimes. This will happen to you sooner or later if you're doing this enough times. Because what happened was that we had WLAN1 monitoring on all these different channels, so we see that it's hopping around between the different channels. At the same time, we're trying to use air replay to do an ARP request attack on test 1, which is on channel 11. We find that it's not the right channel, but it's not just on channel 8, it's hopping around. So if we try this again, up arrow and press, then we're going to see that it's going to be on some other channel, not 11. So now it's on channel 6, not channel 11. So this is something that can happen sometimes because we're using multiple different tools, and if we happen to be using the same Wi-Fi card, one tool might be scanning around on different channels, the other tool needs it to be sitting on a particular channel. What can we do about this? Well, we can use two different Wi-Fi interfaces. In fact, we have WLAN 0 and WLAN 1. Or we can also stop the scanning on the different channels, since now we have identified that we're interested in channel 11. So we can just then have it go on channel 11 minus C11. So arrow dump and G will be just looking at channel 11. And now we don't have this problem again because arrow dump and G is just sitting on channel 11. And then when we try air replay with this BSS ID, it's also needing to go on channel 11, so that's okay. So now we don't have a problem with the channels, but we have another problem. Again, I intentionally did this so that we can see the sorts of things that might happen, and you need to recognize these things and know what to do about them. So we see 0 up request 0x. The reason this is happening is because we forgot to do a fake authentication with this network. We need to do the fake authentication, so we get authenticated and associated, then we can successfully do our up request attack. So we stop here, and we need to do a fake authentication. The way that we do that is as follows. Also air replay ng. Remember, there's different options in air replay ng. So -1 is the one for fake authentication. The parameters would be something as follows: 0 for the re-authentication time, minus e test1 because we're interested in ESSID test1, minus a, the BSSID, copy and paste it, minus h, and we can copy and paste the rest of this, copy and paste. So we are authenticating and associating our MAC address with test1. We see it's successful. Both the authentication and association are successful. Now we can try our air replay ng -3. So this is the up request attack. We can try this again. Before we do that, let's start capturing on arrow-dump ng so that then we can use aircrack ng on the captured frames that are written to a file. We want to specify the BSSID again here so that we will be filtering out unnecessary BSSIDs on channel 11, such as this other BSSID here. Copy and paste, and then we want to put the output into a file, write it to a file, test1. Remember that, let's proceed with this. It's capturing. And we see there's not much data. It's a very idle network, so it's 0. There's only beacon frames that are out in this network. So we can now do our up request attack. And we're off. The data frames are increasing, but it seems to be pretty slow. The reason is that in order for this to work, we need to have at least one up packet that can be replayed. So I'm going to get my iPhone to connect to this network as well. Yes, so I have entered the WEP key on my iPhone. So we see now there's up request and acknowledgements. And I'm going to open one more terminal to run aircrack ng. We're up to test1-07. Let's do that. Aircrack ng. And off we go. And there we have it. 06C3D96450 with just 17,512 IVs. We're going to demonstrate a fragmentation attack, which is another form of active attack on WEP. First, we take a look at IWconfig that's showing both our wireless cards, WLAN 0 and WLAN 1. Both are managed. We can turn on monitor mode for both of them. So start WLAN 0. And WLAN 1. Now, yes, we have them both in monitor mode. Let's take a look at IFconfig. They are both up, ready to go. And let's see what we have around using arrow-dump ng. Oops. Let's say, yeah, let's do this. Okay, that's test 1 on channel 11, our familiar test 1 with this BSSID, which we will need to copy and paste. So it's jumping around. Let's stop this. And zoom in on channel 11. I think we need minus BSSID. Copy, paste. And let's use ~0 for this. All right, so we're dumping the frames from just test 1. The next thing we need to do is to do a fake authentication to the access point so we can communicate with it. And to do that, we also need to get the MAC address of WLAN1 mon, which we will be using to do the attack. So that's given there. And now we can do a fake authentication, which we will do here in another window. Replay ng -- fake of 1. So there's a 1-second delay for authentication. -01, just one packet at a time. -e test 1. -b, and we paste the BSSID that we copied earlier. -h, and here's where now we will put WLAN1 mon's MAC address. Paste WLAN1 mon, and we're doing our fake authentication. Oops, it's somehow it's trying on channel 5. Okay, let's stop this and start it on channel 11. Start WLAN1 11. IWconfig shows that yes, it is on channel 11, just like WLAN0 mon. And now we can try this again. Authentication successful, association successful. We're going to keep this process just here in case we get disassociated. Then we will get reassociated as this process replaced authentication requests and association requests. All right, so now that we've set that up, we can begin our fragmentation attack, and we'll do that down here. So replay ng -- fragment for fragmentation attack, -e test 1, -b, this stuff here. Copy and paste. Yeah, we can start this again. And then come back here, ready to begin our fragmentation attack. So it's bootstrapping. There was no traffic on the LAN, so I had to fake it by, well, I mean, not to say fake it, but I mean, I used a client to try to authenticate and associate. And so anyway, now it has found a packet that you can use. So I say yes. All right, so it has got a relayed packet, and now we can build a packet using packet forge ng, which is another member of the aircrack ng suite. Notice that it has saved the chosen packet in replay src so on .cap, and it saved the key stream that it found. This is a portion of the key stream. It doesn't have the key yet, but at least it has a key stream that can be used to generate packets that will be valid. Anyway, in this fragment.xor. Good. Then you can XOR this with plain text to get ciphertext. Now we can make an ARP request using packet forge ng. Packet forge ng --ARP. So we want to generate an ARP packet -a, and then here's where again we need the MAC address, the BSSID, and also the MAC address of our device, but we have a couple more parameters. So we have this -k and -l. So -k will be the destination IP address, and -l will be the source IP address. We can pick some IP addresses for these. -l, and then Why? Here's where we're going to be using the key stream that we captured. Fragment 0713073933.xor, and I write it to, I'm gonna write this to forged arp.cap. All right, now we can inject this forged ARP request. Finally, replay ng something like this, forged -h 8416 f9 18 AO FO .1 mon. That's it. Now take a look at the number of data packets. It was 210, which is not really great as far as running aircrack-ng is concerned, but we can already do that. Aircrack-ng test 1-01 cap. So it's not going to be enough yet. There's only 210 IVs, and we are hoping that with this forged ARP request that we'll keep replaying, it's going to be able to get more different IVs. So let's see. Oh yes, great. The number of data frames is going up. It's working. And meanwhile here it's sending out these packets, and now it's gotten over 5,000. So aircrack-ng is continuing to do its thing. Beautiful, isn't it? We wait for it. It probably might take something like 20,000. So it's already got 10,000 unique IVs. 15,000. Should be getting close. Yes. Done. Less than 20,000 packets. 15,412. Alright, great. Rather than continuing to plow through attack after attack, let's slow down a bit and do a bit of a post-mortem analysis to see what happened in our successful fragmentation attack. We will try to use the WEP key that we retrieved to inspect the frames that were captured during this process. We saw a successful fragmentation attack, and let's try to look further at what happened, and we'll use Wireshark to help us. One reason why is that we saw captures in .cap format, but we're not able to view them. So if we try to take a look at the forged ARP, for example, we will not be able to view them because it's a binary format. And similarly, we can't see the key stream fragment. What else did we have here? So we had not only the forged cap, we had this replay source capture, but all these we cannot see without a suitable tool. So let's use Wireshark to take a look, because Wireshark can open .cap files. Let's try to open test. Well, before we take a look at that, let's take a look at the forge ARP, see if we can see anything. Or maybe, well, let's say this capture file. And as expected, we don't see much because it's encrypted data. It's web encrypted. Even though we were able to get back a little bit of the key stream, we haven't told Wireshark what the key is. So Wireshark is not able to show us much more about what it is. Similarly, we can open the forged ARP packet, and we also cannot tell much about it because it's encrypted. So let's go enter the WEP key so that we can see more interesting information. Protocols. IEEE 802.11. And let's edit the WEP keys. We can remove this one and add another one. The WEP key that we recovered was 06C3 D96450. We enter that. Okay. And now we can see that indeed our forged ARP request is an ARP request, because now Wireshark is able to interpret this since it has the WEP key. And the -L and -K flags for the source and destination IP addresses are also seen here. 192.168.1.107 and 192.168.1.108. These two IP addresses. The target MAC address is the broadcast address as well as all zeros. And we see this 8416F918A0F0 that we had set as the sender address. So it's a regular ARP request. And we were able to do this using the fragmentation attack. Let's also go back to look at the source packet that was captured. So this was a DHCP packet. So this was a frame that was captured in order for us to get our fragmentation attack going. So we needed to be able to figure out the keystream fragment. And we got this captured packet, the keystream fragment in the XOR file, and from that we were able to use packet forge to forge our ARP request. So both of these now are viewable now that we have the WEP key, of course. And we can also go and try opening test101.cap, and let's scroll down. Yeah, so we see all these ARP requests, and these are we can open any of them. Let's say this one. Yeah, so this is what we saw before also. So it is our forged ARP request that we are replaying. So it's from 1.108 and asking about 1.107, and we see the source MAC address. So we can open, I mean, there's tons of them. So we can just scroll around and click on another one, the same thing. So it looks very much like an ARP request replay attack, except that this is using a forged ARP request that we had generated, rather than in the ARP request replay attack where we were listening for an ARP request from some other device and then replaying that. We can try to take a look at the XOR file, see if that works. But aha, so we cannot. It's not something that Wireshark understands. There's another category of attacks on WEP having to do with isolated clients. They go by exotic names like Cafe Latte and Hirte. But what do we mean by attacks on isolated clients? So far we have been looking at cases where we have an access point that is using WEP encryption, and then we try to focus our attack on that access point. We have seen, for example, the use of passive attacks with PTW, correct FMS, where we just listen to traffic to and from the access point, and also active attacks where we go inject frames into the Wi-Fi network. So far, therefore, we have always been having an access point and some clients around it. Well, what happens if we don't have an access point that's easily accessible? Maybe, for example, the access point could be in a secure location and you cannot get close enough. Are we then unable to do anything about it? One point to realize is that when we use WEP, not only the access point has the WEP key, it's a shared secret. Therefore, all the clients also have the same WEP key. This is important because now we can think about how we can recover the WEP key even if we don't have the access point around and it's just a client. The idea is to try to get the client to generate frames with different IVs even though the access point is not around. How can we do that? The first such attack that we'll talk about is the cafe latte attack. Before the cafe latte attack was introduced, there were already ways that people could do this kind of thing, using tricks like forcing the client to de-authenticate, but it would take a very long time because the client would have to re-authenticate, and so it was not very practical. The cafe latte attack, in fact, goes by that name because it was something that could be done relatively quickly. Supposedly, the amount of time it took you to have a cup of cafe latte would be similar to the amount of time it would take for you to be able to get the WEP key with this attack. The idea is to do ARP replays. So we have already seen ARP request replays in earlier videos. In this case though, this is without the presence of an access point. So we would naturally ask that how do we make a valid ARP request when we don't have the access point and we don't have the WEP key? We need to replay something that is going out over the air. The problem is that the isolated client, even though it has a WEP key, it cannot associate with the access point since the access point is not there. It therefore cannot send ARP frames. It needs to be part of that Wi-Fi network before it starts sending the ARP frames. So you cannot rely on the isolated client to help you with ARP requests. Therefore, one of the key features of the cafe latte attack is that we set up a fake access point with the same ESS ID as the original access point. The beauty of this is that, well, beauty of it, depending on your point of view, if you're thinking about WEP and how horrid it is that it has all these errors and in design and problems and vulnerabilities, maybe you don't think of it as the beauty. But anyway, I'm saying that there's no server-side authentication, so the clients do not authenticate the server. So you can set up a fake access point and just claim to have that ESS ID, and the client will try to associate it with it. So the client will try to associate, you just tell it that it's successful, and then upon association, the client will send gratuitous ARP requests with its MAC and IP address. This is its normal behavior when it joins a LAN, so that others will know whenever there's an IP packet that is addressed to its IP address, the other members of the LAN will know which MAC address to send it to. So this gratuitous ARP is so called because it's sent not in response to an ARP request, but let the other members of the LAN know. So it's gratuitous in that sense. And how do we generate the ARP request then to get the ARP responses? Because now this client is sending this gratuitous ARP. What can we as the attacker do? We can capture a gratuitous ARP, which happens after association with the fake access point. And there's a few bits that can be flipped to transform it into a genuine ARP request. So it's no longer a gratuitous ARP request, but a normal ARP request. And then this can be sent, because now, let's say we just have this one or a few gratuitous ARP requests. We can generate a few genuine ARP requests. That's not going to be enough. We need to get many more IVs, but we can by sending out this ARP request many times. We'll be getting ARP responses from the other clients. Well, in this case, let's say we just have one isolated client. So our attacker could be generating this ARP request from that network card that's faking as an access point. And this isolated client would then be generating ARP responses in response to the ARP requests. The ICV, as mentioned, is easy to modify too. So there's no way that the client will know that this is not a genuine ARP request, and it will respond with ARP responses. And once we gather enough of them, we can crack the WEP key. The Herte attack is similar to the cafe latte attack, except for a couple of differences as mentioned below. You can use any IP packet, not just gratuitous ARP requests. There's a more complicated process of transformation, and it involves the use of fragmentation as well. We will now demonstrate the cafe latte attack. The setup is that we have a client which has previously connected to our access point test1. Meanwhile, test1 is offline. So we can imagine that this client has moved somewhere very far away from test1, but the client has the WEP key. So we will demonstrate that we will be able to retrieve the WEP key using this attack, even though the access point is not around. We will try with two ways. One is using air replay NG and the -6 option, and the other is airbase NG with the -L option. The difficulty with the air replay NG option is that it requires an ARP request to replay, but without the access point, it's a bit hard to get hold of a valid ARP request for this network, since a client needs to be associated with the access point and then only it sends an ARP request. Airbase NG, on the other hand, creates a fake access point, so a fake test1 access point. So it accepts association requests from the client, and after which the client then sends the ARP request, which can be used. And furthermore, Airbase NG has built-in support for the Cafe Latte attack. So not only would our network card be acting as a fake access point, it will also then initiate the Cafe Latte attack with the ARP request. So that's something that we will see as we look at the demonstration now. Let's take a look at the Cafe Latte attack. And first, we check the IW config to see we have WLAN 0 and WLAN 1, two different network interface cards. We try using the air replay NG version of the Cafe Latte attack. This is with air replay -6. We need to have the MAC address, and so we take a look at IWDEF WLAN 0 info to get the MAC address of our network card, copy it and paste it. The air replay NG version of the Cafe Latte attack with this -6 flag is going to be sending ARP requests using this MAC address 56A3967968F6. The problem is that the air replay NG version of the Cafe Latte attack is just sending ARP requests, and it's not associating with the access point since the access point is not around. So we see that it's unable to get anywhere. We need to have a valid ARP request that we can capture and then modify it to replay it. One way we can do that is using the Airbase NG version of the Cafe Latte attack. Airbase NG is a member of the Aircrack NG suite of tools, and what it will do is set up an access point, and it will call itself test1, as we see -E test1 here. Put that on channel 1, so -C1, and then -L is for the Cafe Latte attack. We use -W1 to be using WEP for this fake access point, and the reason for doing this is that now the isolated client has an access point it thinks is test1, and it will try to associate. After that, then it would send a gratuitous ARP request. That is what the Cafe Latte attack can use to replay. And we don't have to separately run air replay NG, because with this airbase NG command, it knows what we're trying to do since we put -L, and it will conveniently for us automatically start the Cafe Latte attack. So we see this client 9091 E107 2171 associated with our fake access point because our airbase NG started advertising itself as test1. So we can see the arrow dump output where there are frames that are showing that there is traffic on test1. This is our fake access point, and so all this traffic is from the client, the isolated client that now has what it thinks is test1. And finally, now we see that the cafe latte attack has started here, and we see that the rate of the frames is increasing very rapidly. It's also increasing 3 times faster than in real life because we speeded up the video. And in fact, we should have more than enough for PTW, so we should have started aircrack NG as well, which we will do now. And we see that this is just based on those ARP requests and the rebroadcast of the ARP request. We see that the key has been recovered successfully. We do a post-mortem on our cafe latte attack and then also demonstrate the Herte attack. Let's use Wireshark to inspect test1-08.cap, where we had captured what was happening with the cafe latte attack. So Wireshark. We are going to go get this file and open it. Now, in a previous video, we had already entered the WEP key, so we don't have to do that. That was the one on the fragmentation attack. So now Wireshark still remembers that WEP key, and we can just proceed to take a look and see that indeed it understands that these web encrypted frames are ARP requests and responses. If we scroll through, we see that there's lots of ARP requests and some responses. The one interesting thing is that it's asking, let's scroll this up here. It's asking for 169.254.57.242 and sending from 169.254.57.91. This is a special APIPA IP address for the case where you cannot obtain an IP address from DHCP, for example. Why are we seeing this? In this cafe latte attack, we use Airbase NG to set up a fake access point, but we did not set up additional pieces behind it. So there's no DHCP server such that when the client authenticates with and then associates with this access point, then if it's a real access point, normally then there will be a DHCP server behind it and the client can go get an IP address. So you might see something like 192.168.1.16 or something from the private IP address space. So unlike the fragmentation attack, where we inspected it before and we saw that it was using more typical private IP addresses, in this case it's not, but it's still okay because we had the broadcast and we had the responses, and as the client is broadcasting this ARP request, it's using different IVs. Even though they all look the same, they are actually using different IVs as far as the WEP encryption is concerned, and therefore eventually then aircrack NG is able to retrieve the WEP key. We now proceed to demonstrate the Herte attack, also known as the CFrag attack. This is recommended, especially if your hardware is capable of doing fragmentation. And we can see that if we take a look at Airbase NG's help. So let's say we just do Airbase NG, scroll up. We see the options. And where is that now? -L for the cafe latte WEP attack. And it says use if driver cannot send frags. Instead, use the CFrag WEP attack, which is recommended if the driver can send fragments. This -N or CFrag for the CFrag attack, this is actually the same as the Herte attack. So we will see when we run it with -N, it's actually doing Herte. So that's a bit of something to take note, not -H, but -N. As usual, we will do RW config to see things. Okay, we already have WLAN 0 and WLAN 1, and so we can begin. We will first take a look at aerodump NG to see what's out there. We'll use WLAN 1 here. So that will have a side effect of turning on monitor mode for WLAN 1 as well, so both will be in monitor mode. And we see that most of the channels that are used are 11, 6, and Probably we should see channel 1 as well. We're just looking to see where we might have strong interference. Generally, the Wi-Fi channels, you'll find that modern access points will try to avoid interference, so you might find them starting up on channels where there's less interference. So channel 1, 6, 11. In this case, we see that the other access points out there are using 6 and 11. We don't see any on channel 1, so we'll proceed to use channel 1 for our fake access point. So we will be pretending to be test 1. So we will set up our arrow dump to be capturing that, because we know we're going to be setting up our fake access point. And we're going to be using channel 1. So channel 1, ESSID test 1. Write it to test 1 as usual. You might rename it to test 103, something like that. Then WLAN 0. So arrow dump is going to be on WLAN 0, and our fake access point is going to be on WLAN 1. We need to avoid confusing ourselves, so we have to be clear about that. WLAN 0 for our arrow dumping, WLAN 1 for our fake access point. And then we also have the client, the isolated client, which currently doesn't see test 1, it's not trying to connect. But later, if it doesn't automatically switch over, we will then manually have it look for test 1, and then we'll get things set up. So arrow dumping. And then here, we do airbase ng minus C1 minus E test 1. Minus N instead of minus L, as we mentioned earlier. And then so here we have to be careful, not WLAN 0, but WLAN 1. Otherwise we get some strange results depending on the specific hardware that we're using. But if we have two different wireless cards, then it's good to use two different ones. Okay, so this is where we'll set up our fake access point and start the HERTY attack. Yeah, we've started capturing on test103.cap. But actually, let me try and get this isolated client to switch over, because it didn't automatically switch over. It was happily associated with another access point. So let me switch over to test 1. Seems there's some problem with broken SKA. Let's try switching around the Wi-Fi cards, because perhaps one of these cards cannot handle something correctly. It's very sensitive to various drivers that we're using and things like that, and the hardware chipset. So let's try this. Okay. And now I'm going to try again to connect to the fake access point with my isolated client, namely an iPhone. And this time seems to work. So the client associated with the fake access point, and now it's starting the HERTY attack. Let's set up aircrack ng over here. Okay, so test 104. It's a bit slow compared with our Cafe Latte attack. So that's why Cafe Latte is also supported, because depending on the hardware you have, sometimes you see things like that. It could be quite slow. If things work out well, then you might find that this CFRAG or HERTY attack works faster, but well. Reaver is the standard tool for retrieving WPS pins. We'll explore it here. We now demonstrate how to use Reaver together with the Pixie Dust attack to retrieve a WPS pin. First, we look at IWconfig as usual. So we see that we are already in monitor mode. If not, we can always turn it on. We do arrow dump minus ng WLAN 0 to look for our target access point. In this case, we're looking for Daniel Wireless, which is here. So it's on channel 11 and with a particular SSID. So we can stop and we begin with the use of Reaver. So that's Reaver. In the past, Reaver and Pixie Dust might be used separately. So Reaver would understand the EAP protocol and the exchange of messages, and then it will capture some data that Pixie Dust would be used subsequently in an offline way to analyze the data. These days, Reaver is integrated with Pixie Dust, so we just run Reaver with a particular option to get Pixie Dust involved. So it's quite straightforward. There's various options, as we can see here. If we just do Reaver by itself, we can look at the different arguments. But anyway, let's use the basic Reaver with this while less than 0 minus B. So as I mentioned, it's Daniel Wireless, which is this BSS ID. Copy, paste, and make it verbose so we see what it's doing. And here's where we bring in the Pixie Dust attack. Even as we're gathering data with Reaver, we'll be using the Pixie Dust attack to analyze it. So minus K equals 1. And then we know it's channel 11, so minus C11. There was a previous session that I had been trying earlier, and we can just restore it. I just started for a few pins. So yes. Now, notice that Reaver is helpful in the sense that it will keep your previous session results so you can continue again later and not have to wait very long. And there are various mechanisms whereby wireless access points will make it more difficult for people to find a pin using tools like Reaver. So for example, you might have to wait before trying with a new pin. So this can be a bit annoying, but it just slows down the attack. Since the maximum possible number of different valid pins is only 11,000, at least that we need to check. So eventually we should still be able to retrieve the pin. But this is more than 60 seconds, so we may have run into another AP protection mechanism where the AP will actually disable WPS rather than just wait. We will try to connect to the router to see if we can do something about that rate. Now it's interesting that various sort of countermeasures are implemented in access points. So I see on my router configuration screen that there's this option here which says enable router's pin, and that in parentheses it says disabled because an attack is detected. Some APs come with such detection features. So let me enable the pin again, and then we won't have to keep waiting. But it still seems to not be working. Let's take a look at the router settings, and maybe there's something else. And I'm going to disable the router protection feature that automatically disables the pin after 3 failed attempts. I can change the number of failed attempts to a larger number, but I'm just going to try to disable that, and hopefully that will make things faster. Okay, so I'm applying it to the router. We're still waiting and waiting. No, that's way more than 60 seconds. That's the problem with some of these tools. Sometimes these are not polished pieces of software that we might be used to from big software companies. So problems like this can happen. Maybe there's a bug and could be waiting 60 minutes or who knows. Let me just try to restart this. Maybe that might be easier. Restart the previous session. No, not that either. That didn't seem to help. Let's try to run arrowdump ng to figure out what's going on. So arrowdump ng wireless LAN 1. And let's see if maybe the router might have changed channel. Yes, we see that it has switched to channel 1. When I reset the pin, it had gone to channel 1. So okay, that's why it's waiting forever for this beacon. So these sorts of things happen. Routers have their own way of doing things. So in this case, it had switched to channel 1. So good thing for us, we checked. And now it's trying more pins. It's taking a while, and we have speeded up the video meanwhile. So it's triple speed. Yeah, okay. Try another one. Yeah, it's kind of annoying sometimes this because of router protection mechanisms, so it can take a while. Doesn't always succeed in associating. And again, we are greatly speeding up the video. It's something like 5 times faster than usual now. And when it does succeed in associating, then it goes through this protocol here, trying the candidate pin, but it wasn't the right pin. We're speeding up the next almost 2 minutes of reverse action and making it fit into about 10 seconds. Sometimes we see WPS transaction fail, and we can do a minus no next. That's a suggested way of dealing with it. We're seeing a 4 times speed up in the 16 seconds of video. Yeah, so we didn't get that same error because we set the minus no next. Another speed up. Trying different pins now. And here are the next 5 minutes of reverse action greatly speeded up again. However, we see that we still have all these problems with difficulties associating with the access point. So this is caused by the signal strength of the access point not being strong enough. And what can we do about that? We have one more trick up our sleeve, because if we don't do something about it, it's just going to be too slow. In this portion of the reverse action, we only get to try 11 pins, and it will take a long time to get to 11,000. So what do? We can improve the signal strength by using a stronger directional antenna. We conclude our demonstration of reverse in this video. We are now using the new highly directional antenna, and we see that we have a better received signal strength from our AP. So it's minus 56 dBm versus minus 64 dBm that we had seen before. And we hope that this will reduce the number of failed associations that we see with reverse, and therefore speed up the process. Let's try to resume our reverse session. So we still have failed associations, but we'll see that it's not as many, and we can make faster progress. We are also going to speed up the video to help to reduce the amount of time you just wait to see things happening in real time. It looks like reverse has detected access point rate limiting. As we have mentioned before when we saw this warning before, this means that the access point is either limiting the rate because it has detected a WPS attack, or possibly it could even have disabled WPS, so you can keep waiting more than 60 seconds and it's not going to make a difference. You might have to wait till the access point is rebooted perhaps, or some admin goes to re-enable WPS. That's why it's a good feature of reverse that it gives you the option to resume the next time rather than restarting again. This also shows that with modern access points, it might be a bit difficult, and we might have to be very patient to retrieve the pin because of such countermeasures. So we re-enable the WPS pin on the AP, and then it starts trying again. However, we'll see that it's not getting anywhere, And it's because of what we had seen before, that when we re-enable WPS, then the router does a restart, and sometimes that means that it goes to find another channel where there's less interference and it starts operating on that channel. It might not be the same one as the one it was using previously. So we might have to stop and then restart Reaver once we find out which is the correct channel. So we have to find out the correct channel and then restart Reaver on that channel. In this case, we have found that the channel has switched to channel 6, and so we started again on channel 6. And we found that by using arrow_ng. We're greatly speeding up the video again as Reaver runs through more pins. So I think you get the idea. It's going to keep doing this until it gets a pin. At most, it has to try 11,000 attempts. So now it comes to 80 pins. And again, the AP has detected this WPS attack and has disabled WPS. In the case of our demo, we can go and reset it again. In the case of a real life access point, this mechanism might mean that now you have to go wait for some time. And so we will just skip ahead. We will go re-enable WPS and we will skip ahead. And now 109 pins, and it keeps going. Speeding up the video again. I'm continuing this Reaver attempting to get the WPS pin at a time when there's less traffic, so there's less load on the AP, and we see that it's much smoother. We don't have those failed associations. So we see that all these factors matter. I added a more powerful directional antenna with higher directional gain. Finally, we see this AP rate limiting. So this thing still is happening, but at least before the rate limiting kicked in, it was able to try quite a number of pins without running into problems with associating. Those happened during a busy period when there were other users using the access point. Skipping ahead some more. And finally, WPS pin 40155708. Indeed, that's correct. So it finally got the WPS pin. Success with Reaver after all the different attempts and tweaking the flags and parameters. We got the pin. In this video, we will do two main things. Firstly, we will introduce an alternative tool for scanning, which works especially well with Reaver in terms of getting information about WPS usage in surrounding access points. Secondly, we will review the various kinds of challenges that one may face when trying to use Reaver. This other tool that I mentioned is known as Wash, and it is specifically designed to provide information about WPS usage in the various access points that can be detected around. arrow_ng that we have been using before is a more general purpose scanning tool and doesn't say as much about WPS. Since different information is provided by Wash and arrow_ng, generally we may want to use both. Let's take a look at what we have. WLAN 0 in managed mode. If we try to do wash -i WLAN0 when it's in manage mode, we get an error. So unlike arrow-ng, wash will not automatically put the wireless interface into monitor mode. But no big deal. So let's say we look at arrow-ng first. It will then put WLAN0 into monitor mode. After that, then we can take a look at what wash will do for us. So anyway, we wanted to compare arrow-ng with wash. So we go ahead with arrow-ng, WLAN0. So even though it's in manage mode, as we have done so many times before, arrow-ng will just automatically, for our convenience, set WLAN0 into monitor mode. And it does that. So we are trying to see what's the difference as far as WPS is concerned in the information that is presented by arrow-ng versus the information presented by a tool like Wash, which is specifically designed for scanning for WPS. One thing we note here is that we see things like WPA2, WPA, if there is WPA also show, but all these are WPA2, and a couple of WEP. Now, we don't see WPS mentioned here, so we cannot really tell from here if WPS is turned on. We can try with Reaver, and then we'll get to know pretty soon. We'll get some error messages, and we'll know that WPS is not enabled for a particular access point. But another way to know with more certainty is to use Wash. So now that WLAN0 is in monitor mode, now Wash should be able to work. And we see that it gives a different output. So it doesn't put WPA2 CCMP, for example, but then it looks to see if WPS is enabled for these different access points. It scans on different channels and then shows the output. So this is one way we can know which access points have WPS, and then we can go try Reaver on these access points. We encountered various challenges using Reaver in the previous two videos. So here we would like to summarize some of these and talk a bit about things that can be done to help ourselves. One of the main problems using Reaver these days is that modern access points include various countermeasures. One helpful point about Reaver is that it saves the work previously done. It gives you the option to resume where you left off the next time, so you don't have to start again from the beginning. Besides the AP countermeasures, there are other problems using Reaver that are more easily handled. One is signal-related issues. So we saw things like association failures that happen quite frequently, and there's a couple of ways that we talked about to handle this. One was using better antennas with more antenna gain, and the other was trying to do the WPS attack when the network traffic was light. Here's a picture showing the same TP-Link wireless card and the antenna that it comes with, as well as another antenna which has higher gain. Both of these are omnidirectional antennas, so it's not directional antennas, but this antenna with much higher gain is able to give something like 8 to 10 dB improvement of the signal strength compared with the antenna that it came with. It was easy to just unscrew this and then screw on this one. We will show a short video clip of how using Reaver after hours improved the performance. I'm continuing this Reaver attempting to get the WPS pin at a time when there's less traffic, so there's less load on the AP, and we see that it's much smoother. We don't have those failed associations. So we see that all these factors matter. Sometimes we see WPS transaction fail, and we can do a minus no next. That's a suggested way of dealing with it. We're seeing a 4x speed up in the 16 seconds of video. Yeah, so we didn't get that same error because we set the minus no next. Last but not least, the Reaver software has some issues. So in the version that we were using that came with Kali Linux, I think that 2017, one of the 2017 builds of Kali Linux, there were problems in specifying the parameters. It's interesting that even this very important -k parameter, which is to use for including pixie dust, has a problem. Reaver comes with some help, so you should type Reaver, maybe Reaver --h or --help, just standard way of getting the help information. It gives an example on how to use Reaver, but this example uses the -k flag in this way, -k space 1. If you try using that, you're going to get this weird error from Reaver, which says that the WPS pin is not found. And eventually you'll figure out that it should be -k equals 1, which you can kind of guess from the help as well. So here's a video clip showing what happens when you use -k space 1 as following the example from the Reaver help. Unfortunately, Reaver is going to be unable to find a pin and it's going to give up. The reason is because of the way that we specified the -k option. We demonstrate how to get Hashcat installed and running on an EC2 instance in Amazon Web Services. We go to the EC2 console and click on Launch Instance. This brings us to this page, which is step 1 in launching an instance. We are looking for an instance that already has Kali Linux, and we find that by clicking on AWS Marketplace. Search for Kali Linux, and this is what pops up. So let's select. Since we want to demonstrate this on a machine with GPUs, we can go for something more powerful, but let's just go with the P2X large. That's the smallest one. We could select P2 8X large with 8 GPUs, 16X large with 16 GPUs for even more GPU power, but just for purposes of demonstration, this will do. One instance. Review and launch. Yep. Not eligible for free tier. That's okay. We pay a little bit. Okay, so we launch. I'm going to choose an existing key pair. And yeah, this is something that I have. And I acknowledge I have this. It takes over half a minute, maybe a minute to launch. And we're speeding up the video here while that's happening. It's launching now. More speeding up of the video here while waiting. And it's running. This P2X large is running. Okay, so we can connect to it. This is the IP address. EC2 uses the default root user, and let's paste the IP address here. Okay. We can actually check, just in case there's some man in the middle of the attack, we can go check for the fingerprint and so on, but we won't do that for this demo. Okay, and so we're in. Now some things we can check. We can check for the NVIDIA driver, because this comes with the NVIDIA Tesla K80 GPU. So let's see, SMI. We should do some updates. The updates will get us the latest drivers, NVIDIA SMI, and so on. Whenever we create a new EC2 instance, it is a good idea to use commands like these to get the latest updates, because updates are continually being made available and we want to make sure that we have the latest dependencies, even though we use the latest, most recent image of Kali Linux. So this fails because we need to have sudo. So it's a permissions issue because we need root permissions to install these updates. Even this failed, meaning that running the install commands with superuser privileges was not good enough. We actually have to be root, or the superuser as it indicates here. We can do this with another command, sudo su, so to temporarily become the superuser and then try again. Well, let's try this. So okay, now we are root. Speeding up the video. So it's grabbing and installing a bunch of updates that have become available since this machine image for this EC2 machine was put in the marketplace. This whole updating process took 13 minutes of real time, and we are massively compressing that into less than a minute of video here by greatly speeding up the video. And back to normal speed as we finally approach the end of the updating. And finally we're done. Alright, so the Novo kernel modules are not enabled. That's good. We don't have to go blacklist them. Let's look for the NVIDIA info. We're still not able to use NVIDIA SMI to get information about the GPU because we are missing one more update, which we will see when we resume in the next video. Finally, we come to the part of this course where we're talking about cracking WPA PSK and WPA2 PSK. 3 points I want to make here. Firstly, WPA PSK and WPA2 PSK, why are we grouping these two together? Why not WPA PSK and WPA Enterprise together, and then later WPA2 PSK and WPA2 Enterprise together? The reason is that the security protocols and exchange of messages are similar for WPA PSK and WPA2 PSK. So understanding one, we understand the other as well, and we can use the same way to attack the scheme in both cases. The difference is in how the key is used eventually. So the process of key derivation is similar, and then eventually we're using the very powerful AES for encryption with WPA2, whereas we're still using RC4 with WPA. Two more points, and that has to do with the second part of the title here, which is guessing the passphrase. Why do I write passphrase rather than password or key? Unlike the case of WEP, with WPA, we have the concept of a passphrase, which is then mapped to the actual key, which is a mapping of something which would be typically more human readable, although it doesn't have to be. So passphrase is something that the user would see and then would typically enter into the different devices. And then the key is something that would typically then be seen in hexadecimal or a binary. The guessing part of it is the third point. So why do we say guess the passphrase? And that's because unlike WEP, that's the difference here with WPA PSK and WPA2 PSK. And that is that we do not have a good way to deduce the passphrase or the key from statistical means. So we have to end up trying to guess it with a kind of brute forcing dictionary attack, which, as you may imagine, is not as effective because it relies on the password being something that's easily guessable. So compared with WEP then, the WEP key would be pre-shared with multiple stations, and is the same for WPA2 and WPA PSK, but there is a difference that this shared secret that is pre-shared with multiple stations is used directly for encryption with WEP, whereas it goes through some kind of key derivation process in WPA PSK and WPA2 PSK. As I mentioned, the passphrase is the thing that's common, but then it goes through a key derivation process so that the pre-shared master key then would be something that the user doesn't see directly. And furthermore, the pre-shared master key itself is not used directly for encryption, but the pairwise master key, PMK, is not used directly for encryption, but it is used to derive a pairwise transient key. And the pairwise transient key is the one that's actually used directly for encryption. So the pairwise transient key is something that would be different for each station. It wouldn't be the same, even though the PMK would be the same because it's the same SSID for all of these stations. With WEP, we can capture enough frames with different IVs and we can find the key, whereas with WPA PSK and WPA2 PSK, we cannot do that. In the case of WEP, due to these many weaknesses, even if the key is hard to guess, it doesn't help to protect the key. Whereas with WPA PSK and WPA2 PSK, it helps if the passphrase rather is hard to guess. It's not a simple dictionary word or simple combination of dictionary words. The process whereby the PTK is derived is through this exchange of messages known as the four-way handshake. And it turns out that we can capture the four-way handshake and use it to do a brute force attack because of the way that the four-way handshake works, which we will demonstrate shortly. This four-way handshake is meant to confirm the existence of the pre-shared master key at the peer. So both the access point and the station would be trying to confirm that the other side has the same pre-shared master key, which means that it has the same passphrase because the pre-shared master key is derived from the passphrase. And then fresh keys could be used for cryptographic operations if you do this four-way handshake because you'll be deriving a fresh PTK. Besides peer-to-peer communications, there's also group communications like multicast and broadcast. So the group transient key will also be sent from the authenticator to the supplicant, so from the access point to the station as part of this handshake. And then another purpose is the confirmation of the selection of cipher suites. Inputs to the four-way handshake include the pre-shared master key, which is derived from the passphrase using this PBKDF2, which we will talk about more in the next video, and a couple of nonces. So each side will generate a nonce. The authenticator nonce, or A nonce, and the supplicator nonce, or S nonce, referring to the two sides. Remember that the authenticator is the one that's trying to guard the access to the network. So in this case, the access point, and the supplicant is the one that's requesting to join the network. In this case, the station. As a result of this four-way handshake, we get the pairwise transient key, which is not sent over the air. But at the same time, we also get this MIC, message integrity code, which is sent over the air in messages 2 and 3. So we are going to look at the four-way handshake in more detail in the next video. And we will talk about that, how the passphrase can be guessed if it's easily guessable. We continue to discuss how we can try to guess the passphrase of WPA PSK and WPA2 PSK using a captured four-way handshake. The four-way handshake, as we had already introduced in the last video, is an essential part of the signaling that happens in WPA PSK and WPA2 PSK, because it is used to, among other things, have the two sides verify that the other side knows the PMK, which is the pairwise master key. It is also used to then derive the PTK, pairwise transient key, which is actually used for the encryption, whether with AES in the case of WPA2 or RC4 in the case of WPA. And there are other purposes as well, as we saw in the last video. In this video then, we want to take a look at how we can exploit the information that is revealed in a four-way handshake in order to try to then guess the passphrase. What do we mean by exploiting the information that is revealed? Well, it turns out that, and it sort of makes sense, that because at the time when the four-way handshake is happening, the communication cannot be encrypted, and it cannot be encrypted because the PTK itself is being derived in this process, and so it cannot be used yet until this four-way handshake is over. Then the encryption can be turned on. So because of that, the information is being exchanged in plain text, and so the idea here behind our approach is that we need to be able to capture a four-way handshake that happens between some other client, a legitimate client, and the access point. We capture a four-way handshake. Now, the PTK is not going to be very useful to us in this case. Anyway, it's not even sent over the air, as it shouldn't be. Given the four-way handshake, we are going to be able to see what is the A nonce and what is the S nonce. So remember that each of these entities, the supplicant and the authenticator, in this process of the four-way handshake, they are generating a nonce. This is a random number. And so they are known as the A nonce for the authenticator nonce and the S nonce for the supplicant nonce. This is part of the computations that are done in deriving the PTK. So once we have the A nonce and the S nonce, together with the PMK, we should be able to compute the PTK. Now, we cannot use the computed PTK for verification purpose to check whether our guess is correct, because the PTK is not sent over the air. Not to worry though, because there's another entity that is sent over the air, and that's the MIC. We see in message 2 and message 3. So the first message is coming from the authenticator, there's no MIC, but in message 2 there is, and in message 3 there is also the MIC. Based on this then, if we have either message 2 or message 3, we are able to see what the MIC is, and as you might be able to guess then, we guess a passphrase, and then from that passphrase we use PBDKF to compute the candidate PMK, and then with the A nonce and S nonce we can compute the MIC. We can check if it's the same as the MIC that is seen in this captured handshake. If it is, then we're successful and we have successfully guessed the passphrase. If it isn't, then we keep trying. So this is the way that it works. We just need one four-way handshake, because even if we use another four-way handshake, we have to still do the same computations. It's just another pair of anons and snons that we can use, and anons, snons, and MIC that we can use, and we would still have to pass in our candidate passphrases through the whole computation and see if we get the matching MIC. So we just need one four-way handshake. In fact, we don't even need all 4 messages, because looking back at the diagram, we see that if we have message 1 and 2, we have both the anons and snons and MIC. If we have message 2 and 3 only, we have snons, anons, and MIC. Message 4 is just an acknowledgement. So we see that we don't even need all 4 messages. If we have 1 and 2 or 2 and 3, we should be good as far as our purpose is concerned. And then we go through many different candidate passphrases using a word list, compute the PMK, and this uses the SSID and PBKDF2 SHA-1. So because it uses the SSID, we cannot just simply have table lookups of PMKs based on whatever passphrases, because if that were the case, then the procedure would be, instead of using these word lists, we would use lists of PMKs that are associated in a one-to-one way with these words that you might find in word lists. But because it is also a function of SSID, generally we have to start with the word list and then compute the candidate PMK corresponding to the candidate passphrase. Clearly then, we are just guessing and verifying, so this won't succeed against well-chosen passphrases that use combinations of words or even not words. It's just various random combinations of letters and special characters. In this video, we will demonstrate a basic dictionary attack on access points protected with WPA PSK or WPA2 PSK. In the process, we will see 2 familiar tools, if you will, that we have seen in many videos before, but with different personalities. What do I mean by that? I mean that we have seen them used for cracking WEP, but now for WPA and WPA2, they provide us some additional helpful capabilities, which we will see. In particular, AeroDumpNG helps to highlight when it has detected a four-way handshake in the frames that it has captured, whereas AirCrackNG takes an additional parameter, which is the name of a file which contains words, and this will be a word list that it can then use to try to retrieve the passphrase of WPA or WPA2. We will now demonstrate how to find the passphrase of a WPA2 PSK protected access point. As usual, we begin with taking a look at our network card, see what state it's in. So WLAN 0 is managed. Okay, that's fine. And we will do an AeroDumpNG to take a look at what's around us. Previously, we had not really bothered to focus on the first line of AeroDumpNG. For today, we will be looking at this first line because we're going to be looking for something that's going to be showing up at the top right of AeroDumpNG. That will be helpful for us to know when we have retrieved certain information that we need for our WPA2 cracking. So firstly, we are looking for test 2, the access point test 2, which we see here. So we can get its BSS ID from this line here, and also the channel. Having obtained these crucial bits of information from AeroDumpNG, we then proceed to run AeroDumpNG again and focus on this channel to try to get the handshake for a connection from a client to this access point. The handshake is important for the WPA2 cracking because then we can use the captured handshake to test various candidate passphrases and hope to find the passphrase that's actually being used by this access point. So we specify the BSS ID, and as usual we copy and paste, and the channel in this case is channel 11, and then we write it to, let's say, test 2, I don't know, WPA, something like that. We notice that the beacons are being found, but there's no handshake found. So we don't see a handshake here. And what I'm going to do is to disconnect and then reconnect a client so that we'll be able to capture a handshake. Meanwhile, more and more frames are being captured as we see the number of beacons increasing, but still no four-way handshake in sight. I disconnected the client. Now I'm going to try connecting it. Meanwhile, our interface WLAN0 is down, so we restart that. And we're speeding up the video by 3 times here. So it has detected and found the WPA handshake, as we can see here. So this is the crucial thing that we need. And given that, now we can stop this capture because we have what we need to use for our brute force attempt to find the password. Let's see what we have. So because we restarted the arrow dump, so we got the second capture here as test2 WPA-02.cap, and we are ready to use that. What word list are we going to use for our brute forcing? We have created a special small word list here that contains the passphrase. Since I happen to know what that passphrase is, later on we will see a more realistic scenario in which we will be using more comprehensive word lists. But for now, this is just to demonstrate how we would go about it. And we go back to our old friend aircrackng and test 2 WPA-02.cap, and we had to tell it the word list, so we will use this. And almost immediately it found the key, which was hello there. The reason being that this word list is very small, so it hardly took any amount of time. And let's take a look at our word list that we used. What's the name of the file? And while we're at it, let's also examine the aircrackng output. It opened this .cap file, found packets, and it detected this handshake. We captured one handshake, as we know from earlier. And then it tried with the words in that word list. And once again, the word list was test words. So let's take a look at test words. We see hello there is right in there. And so therefore it found that hello there was the passphrase. Now that we have retrieved the key, we can also use Wireshark. And let's do that. We can use Wireshark to further explore what happened in this session, and we'll be doing that in the next video. Continuing on now from the last video where we had successfully used a standard dictionary attack to find the passphrase of a WPA to PSK protected access point. We will explore with Wireshark and take a look at the capture file. Remember that in our last video we had captured a four-way handshake. So let's take a look at what that looks like with Wireshark. And let's open the file. New 2 was where we... So we were in new 2. And this was the file that we wanted to look at. It's a small capture file because we didn't really capture a lot, and then we got that handshake already. Let's open it. So these are the frames that were captured when we were trying to get the four-way handshake, and finally arrow dump NG told us that we had managed to capture a four-way handshake. The problem now is how we find the four-way handshake among all these frames, and we can go through one by one and slowly eventually find the frames. But let's take advantage of the filtering capabilities of Wireshark to do that for us. The four-way handshake is not using 802.11 but EAPOL. So we can do this. That's Extensible Authentication Protocol over LAN. So EAPOL. And Wireshark helps us by showing that we have message 1 of 4, message 2, message 3, and message 4. So we can see the messages here. And we can open to take a look at the values like the nonce, A nonce, S nonce, and so on that are inside. So that's message 1, message 2, message 3, and a message 4. Now let's just remove this filter so we see these messages. With other frames around them. So we see these 4 EAPOL messages, which are the handshake, and we see other messages around as well. So one thing that we notice is that we did not provide Wireshark with the WPA PSK. So we didn't provide it with the key or the passphrase, and it was able to view these handshake messages. And if we think about it for a moment, it makes sense because these handshake messages are being exchanged in the process of the client and access point trying to come up with a shared key that they can use. They're not going to use the pre-shared master key, remember. So they're trying to derive a key that they can use for encryption. So if these messages are already encrypted, that's going to be a problem. Clearly, these should not be encrypted until the shared secret is set up, and then other messages can be encrypted. So therefore, we see things like probe requests. It makes sense. Probe requests, that's before you associate, before you do anything. How will the client be able to see encrypted responses? And it doesn't make sense for the client to send encrypted probe requests. So these are also in plain text as well as the EAPOL. That's why we were able to inspect them without having to let Wireshark know the pre-shared key. Not all the frames are sent in plain text though. So let's take a look at something that is encrypted, and we will need to provide Wireshark the key in order to see. That way we can see the difference between frames like these handshake frames and other data. So for example, ARP request. So like this one here, broadcast. We see it's encrypted, so we don't know what it is, at least until we tell Wireshark what the key is. Since we have retrieved the key already, well, rather we guessed it, so we can go put this in. And edit it. Previously we had entered this WP key, but now this is a different kind of key. We see that there's two for WPA. One is WPA password and the other is WPA PSK. So WPA PWD is used when we want to enter a passphrase. And WPA PSK is the actual key itself, which is in hexadecimal, and we don't know it. Well, we can always use a piece of software to go derive it from the passphrase that we know. But since we know the passphrase, let's just enter it here. And now, so remember that we were seeing this broadcast message. It was just like data, and Wireshark didn't know what it was. So we did not move our cursor, but now we see that suddenly the display looks more informative. So now we see that the frame that we had selected previously was a DHCP frame. So DHCP discover, which was broadcast, and then we see things like ARP. So these things that were just data before and Wireshark didn't know how to interpret them, now we see that Wireshark knows how to interpret them because it has the WPA passphrase. It should be clear that the word list that's used for trying to crack the WPA PSK or WPA2 PSK passphrase is very important. The reason being that if we don't contain the passphrase in the word list, then we wouldn't be able to guess the correct passphrase. So having said that, let's consider what word list we can use. We previously created a word list and that contained the passphrase hello there, which therefore aircrackng was able to find. In real life and in general, we will not have the luxury of knowing the passphrase beforehand and being able to put it into a file for our own convenience. So what can we do? There are some word lists that come with Kali Linux. So let's take a look here. User share word list. We see that some of these word lists are actually in other places. But anyway, so let's see. User share fast track. User share word list. Have to be more careful here. Yeah, so this looks like possible passwords that people can use, but this file is pretty small. Let's do a WC to do a word count. Yeah, we see it's only 222. So if we attempt to use this, let's say aircrackng test2 WPA 02 aircrackng didn't take much time to go through all of these potential passphrases and find that it was not in there. So passphrase not in dictionary. So that's what we expected also from such a small dictionary. So let's try another one. Let's go back and take a look at another one. How about the one used by Nmap? So let's see how large that is. Nmap nslib data passwords 5,000. Okay, maybe that's a better one to use. And let's just copy and paste to speed things up. Oh, key found. It's hello there. Okay, so let's do a grep. Yep, hello there is in that password list. So let's also just take a look at the password list. And there we see the most common passwords that people use. So don't ever use these like 50 Cent, Kevin, hello there, and so on. But you can imagine that in general, out of these 5,000 common passwords, you'll find that many access points are not using these as passphrases. So is there something larger, something more comprehensive? Well, we see that this rocku.txt.gz, and just by the size of the file, even when gzipped, we can expect that it's going to be a pretty large file. Actually, before we look at that, just take a quick look at some of the others. Copy and paste to speed things up. Some of these are folders and you can go take more time to go look in them. ls, and you can see that there's a whole bunch of different passwords, different things you can try. Anyway, DNS map, because some of these word lists that you find might not be very useful as far as guessing passphrase is concerned, and I'll show you why. So 17,576 words, pretty cool, eh? So you might think that this will give you a better chance than the 5,000 words you find in the Nmap word list, and that was like 5,000 words, but very common words like hello there, and that showed up. And so we were able to guess the passphrase. Anyway, let's take a look at this file. And now we see why this is not very useful, because it's a specialized word list, not really the sorts of words that you would be using in passphrases, or most people will be using. So it's not just the size of the file, but also the quality of the words as far as the likelihood that these might be used as passphrases. So let's get back finally to that raw queue, and let's go there. We unzipped it. It's huge. Look at the size of that file. And let's see how many words it contains. Wow, awesome. 14 million over words. Let's look for this known passphrase in raw queue text. Whoa, all these variations of hello there. Okay, so let's go back and do the aircrack ng thing. User share word list raw queue.txt. Yep, so it found hello there. If you want to look for additional word lists and raw queue.txt that comes with Kali Linux is not good enough, you can just do a simple Google search. Let's say word list, yeah, something like that. And there's all kinds of websites you can find. So let's say you take a look at this one, and I think it lists rawqueue.txt, and it also includes others, darkcode.lst, and you can go try get some of these other lists. We begin by looking at our wireless configuration. That's fine. WLAN 0, so aerodump ng, WLAN 0. We're looking for our access point test2 again, and so we see it there. So we stop aerodump ng. We see that test2 is on channel 11. We also want to get its BSS ID. We can copy this. Another piece of information that we'd like to know is whether there are any clients that are aware of test2 and that might be at least probing for test2, perhaps even associated with it. So we see that we have the station here, 9094, that is probing for test2. We try again with channel 11 to reduce the clutter. So test2, okay. Now, in fact, we see that this BSS ID, this is for test2. So the station 1994 E4 0721 71 got associated with test2. If we're just going to do an arrow dump now, just to try to get the traffic from test2, we can do this minus BSS ID test2 to filter out the other access points, and then write that to test2. Oh yeah, in this case we gave it an ESS ID, so okay, put it this way. And it's going to take us a while to get a handshake because the client has connected and it is not necessarily going to be de-authenticating anytime soon. So if we are not so patient and don't want to keep waiting around, and we don't mind doing something a bit active rather than being completely passive, what we can do is a de-authentication attack to de-authenticate this client, and usually what will happen is that it will then immediately try to connect again with test2, and that will allow us to capture the handshake. So we do that using air replay ng minus d off 1 minus a, the BSS ID, minus c. Now we have to get the client MAC address here. Sometimes stopping arrow dump ng can be helpful because it will refresh the information when it restarts. Yeah, so it was this one, 1994. That's the one of interest. So we're going to try to get 9094 E4 072171 to be deauthenticated, and then it will try to re-authenticate, and in that process then we can capture the handshake. This is different from our first demo of WPA PSK and WPA2 PSK cracking, where we went to manually disconnect the client from the network and then try to reconnect it again, because we don't always have, and usually we don't have, that kind of control over most of these clients that are around. All right, so let's proceed. All right, so it deauthenticated the station. Well, we still didn't get the handshake. Why did we fail in our deauthentication attempt? We booted off the client from the access point when it was associated and authenticated, and it did not come back to try to re-authenticate and associate with the client. Therefore, we couldn't capture the four-way handshake. We couldn't induce the four-way handshake to occur because the client wasn't cooperating. It wasn't coming back. The reason is not because of the Wi-Fi specification specifically. It's more a matter of client behavior. That's just the way that it's implemented. And this client is on a Windows machine. So in the Windows operating system, that was a Windows XP machine, by the way, you can specify the preferences for the Wi-Fi access points that you will automatically connect with. And in this case, it was having the access point test 2 as the top priority, but then there were several other priorities after that, and unfortunately we were within range of one of the other access points. So what happened when we booted off our client from test 2, instead of trying to reconnect to test 2, it just went down the list and connected to the next access point in the list. Okay, so you have to be aware of the behavior of the software. Sometimes it might be doing these kinds of things. So what I have done now is to remove that other access point from the list. So it will then not be able to find some other alternative and then try and reconnect to test 2 again. So then now we can retry our DOF attack. And let's just take a look to see where test 2 is, and then we will try that again. So test 2, let's see, do we see it somewhere? Yep, test 2 is there. It's on channel 11. Okay. So channel 11 to filter out the other channels. And we wait for the client to reconnect. So we're looking for 9094 something. There we see it. It attempted and it got the handshake, but this is the initial attempt. We want to try the DOF attack, so we pretend that we didn't capture this handshake. Anyway, we didn't write this to a file, so it's kind of not helpful for us. So now we're ready. We will write to a file. And yes, so of course our client is associated with our test 2, but we don't have the handshake. So now let's try the DOF again. Replay, yes, replay ng DOF. So let's proceed, and when we do that, then you can take a look up here to see if it gets a handshake. So, okay, so we did that, and let's see. Okay, yes, successful. Compare this with what we had done earlier, where we manually went to the client. That was not a realistic thing to be doing. In practice, what we just did is what you want to be doing, because you wouldn't have access to the client machine, which will be some Windows laptop or whatever, and you will be doing something like this to make it disconnect momentarily, and then it reconnects. The human user might not even realize that it had been disconnected because it would automatically then reconnect. Of course, they might reconnect to a different access point if there was that list and it could find one of the other access points. That is an operating system specific behavior. But anyway, in this case, we have shown how then we can induce the client and the access point to redo a handshake and allow us to capture it. We have seen that WPA PSK and WPA2 PSK, even though we can use the four-way handshake that we captured and run a dictionary attack on it, it's not very satisfying, not in the same way that we were working with WEP and just needed to get enough different frames with different IVs. So the question then becomes, what else can we do besides this kind of dictionary attack? What if we don't have a suitable dictionary because the client has, the person who set the passphrase has chosen a passphrase that's just not in these word lists. What can we do? So we're going to take a look at some alternative approaches related to weaknesses in other parts of the chain, so to speak. We had looked at Cafe Latte for WEP, and that was for the case of isolated WEP clients. So this is a client that has previously connected to a WEP access point, and so they have the WEP key stored in them, and if you can get them, sort of induce them to start communicating with what they think is the access point, then you can start capturing frames. Now, what about in the case of WPA and WPA2? Can we do the same kind of things? Similarly, target an isolated client. When I mention weaknesses in the chain, so we're here focusing instead of on the access point itself, which is kind of like the hardest point to crack, let's take a look at isolated clients. So it's a client in isolation from the access point. Going along these lines as well, we also want to target what is often the weakest link in the whole chain, because besides the access point and the client, you also have the human user. So if you can somehow get the human user to actually give you the passphrase, that's even better from the point of view of getting passphrase. Firstly, we'll take a look at isolated clients. So this is purely a technical challenge. And then we will start looking at also the human user, but not so much for this video. We will just introduce it at the end of the video. Let's take a look at isolated clients and the technical challenge of trying to get the client to reveal certain information that you can then use to run your dictionary attacks on. So remember that with WEP clients, they can be attacked with Cafe Latte, Herte, and so on. The idea was to set up a fake access point claiming to be the access point in question. So perhaps you know that the ESS ID is something, and then you just set up a fake access point with something like airbase ng and claim to be that access point. Once you can then get the client to try to connect to this access point and to associate it with it, then after that you can induce the client to keep sending frames that are using this WEP key, and they're going to be having multiple IVs, which is what we want to capture. So for example, the classic way is to be sending up fake ARP requests and then getting the client to be sending ARP responses. So what about WPA and WPA PSK and WPA2 PSK? Can we do something similar? Is there something like Cafe Latte for WPA and WPA2? In fact, there is. We can similarly also set up a fake access point. And the idea here is that it's, in fact, even easier in some ways than for WEP, because we don't have to induce the client to keep sending frames with different IVs. We just need to capture a four-way handshake. And in fact, we don't even need the whole four-way handshake. We just need 2 messages of it. Now, is this something that a fake access point is able to do? I mean, to provide its part of the four-way handshake without knowing the passphrase. Let's take a look at the four-way handshake again. We see that it starts with this anons that's sent from the access point. Now look at this. We don't need to know the PMK. We just need to generate a random anons and send it. So clearly this is something that a fake access point can do without knowing the passphrase. Then the client, the isolated client in this case, will generate the snons. It will calculate a PTK using the anons and snons. And then it sends back the MIC, woohoo! So this is valuable information that now the attacker knows, the MIC associated with this anons, snons, and the pairwise master key. Now this step here, to calculate the PTK, well, in a real access point it will do that, but the fake access point doesn't have to do that because it's not needed in the following message. Of course, it's not going to send the PTK, so it just needs to send back the MIC, anons, and some other keys. Perhaps this can be fake information. Doesn't really matter. In fact, we don't even need to complete a four-way handshake, because with these first 2 messages, we already have the anons, snons, and MIC. So the fake access point has the information that it needs, and we can then run a dictionary attack as we saw before, using different passphrases. You might have heard of the term honeypot, where in this case, when we talk about Wi-Fi honeypots, we're talking about something that attracts something to do a certain behavior. So just like honeypots would attract bees to come to get the honey. So in this case, for Wi-Fi honeypots, it's something like this fake access point that attracts the clients to associate and then perhaps to be sending frames like responses. Sometimes if we don't know what kind of authentication is being used, we can set up multiple honeypots, let's say 4 different honeypots with open WEP, WPA PSK, and WPA2 PSK for the same given as ESS ID, because maybe what we know is the ESS ID. We set up these 4 and then see which one the client gets attracted to. We have seen how Airbase NG can help with a bare bones honeypot, but it's limited in the sense that just with Airbase NG by itself, that we don't have DNS, we don't have internet connectivity and so on, so the client is not really getting a good deal here. We're not acting like a full-featured access point. In fact, we can set up full-featured access points that are more like rogue access points with DNS, routing, internet connectivity, and so on. Generally, you might want to do this in conjunction with some additional step, which is, for example, to get a passphrase from the user. Now they have what they think is normal connectivity, and you can do some social engineering. For example, instead of just quietly capturing the 4-way handshake and then trying to guess the passphrase in the usual way, perhaps put some kind of pop-up that would induce the human user to enter the passphrase. In the last video, we mentioned about isolated clients. Previously, we had seen that for access points using WEP, we had attacks like the Cafe Latte and the Herte attack, which preyed on isolated clients. Then we discussed that similar things could be done with WPA and WPA2. In fact, it is even easier because it just needs to induce a 4-way handshake and then it's good to go. In this video then, we will be demonstrating such an attack on an isolated client with Airbase NG. But first, let's just take a step back. We are now talking about methods to facilitate dictionary attacks on WPA and WPA2 PSK. So we have seen, for example, how to get the word list, how to find better word lists, and we have seen how we can do a DOF attack to induce a client to do a 4-way handshake with an access point. However, if we're unlucky and the client then finds another access point that it can connect to, then it might not always happen, but it's just another tool that we can use. Also, in this video, we will show a demonstration of setting up a fake access point with Airbase NG to induce this isolated client to do a 4-way handshake, even though there's no real access point around. It will think that it has the access point there to communicate with, and so we can capture the handshake which we need. One more thing which we will look at in the next couple of videos would be how to speed up the dictionary attack itself. So besides getting the handshake, we still need to do the dictionary attack. That can be very time consuming. So GPU is a graphics processor unit, and GPUs tend to be better at such computations than CPUs. There are tools like Hashcat that are not just for Wi-Fi, but various kinds of dictionary attacks, and we will show how it can be used for speeding up a dictionary attack as well. But for now, we go into this short demonstration of getting the isolated client to do a 4-way handshake. The next thing that we would like to see is what happens when you only have an isolated client. So now we already know that this machine 1994 E4 072171 has the WPA2 PSK. It has the credentials. And imagine now if the access point is not around. How can we make sure that the access point is not around? So we can just turn off our access point, and let's make sure, let's take a look and make sure that the access point indeed is going to go away, because I'm going to turn it off now. We see it's still on the list because we're scanning through and not yet on channel 11. It did look on channel 11, so anytime now we're going to see test 2 disappear from this list because we just turned it off. So unless it's just the ghost of the access point still in operation, okay, yeah, there we see. Test 2 is gone. So there's no access point, and yet we're going to be able to capture the four-way handshake. That's because we have the client. And in order to do that, we're going to set up a fake access point that will claim to be test 2. And we'll use Airbase ng to do that. So minus ESSID. And this is the important thing, that the client is looking for test 2. It's going to be sending probes for test 2. We're going to set it up on channel 1, let's say. And so we're going to write to here. What we're going to try to do here is try to capture the handshake. We're also going to look for the probes from the client. Yeah, so we see that the client is probing for test 1 for WEP and then test 2 for WPA2. The interesting point is that it only cares about the ESSID. It doesn't care about the BSSID, so we can change it. It doesn't have to be 00016B60107C. So it can be something like this. Clearly fake, but it doesn't know and doesn't care. And then minus C1 WLAN0. And then now minus capital Z for WPA2. There's a few options that have to do with the kind of encryption. So in this case, we choose option 4, which is CCMP. We will look at the options after this. Anyway, let's go with this. Oops. Oh, minus ESSID, I guess. Yeah. So we see that the station has been probing, couldn't find test 1, couldn't find test 2. But then now we've set up something for test 2. So let's see if it's able to find test 2. And sometimes this has to do with how often the probes will be sent, and it depends on the operating system as well. Speeding up the next 10 to 15 seconds of video. Aha! So there we see it. WPA handshake with AABBCCDDEEFF, this nonsense SSID, but the client didn't know. And so then it associated, and we got this handshake. So success. We had an isolated client and we're able to induce a four-way handshake to be captured. Now that we have it, then we can use our usual tools like aircrack ng to try to figure out the passphrase. And as I mentioned, the options, we can see the options. I mentioned about a minus capital Z. So let's see the options here. Minus Z, this is for WPA2, minus little z for WPA1, but it's the same tags, so that's why CCMP, the very common one, we are using CCMP, and therefore here it's a WPA2 CCMP associated. In this video, we will demonstrate the changing of a passphrase in WPA2 that makes aircrack ng take a much longer time, and that motivates the use of more powerful tools like hashcat to do our brute forcing. I have changed the WPA2 PSK on the access point. I haven't done it on the client yet. WLAN0. Test 2 is on channel 11. So let's make our life easier by just filtering for channel 11. And let's write to test 2 as before. So if we capture a suitable handshake, and let's also just filter for this so we don't capture a handshake that's related to a different access point. Minus minus. We're speeding up the next 10 to 15 seconds of video. Now it's interesting that even though I had changed the WPA to PSK passphrase on the access point, error-dump ng still sees that the client attempted to associate, and it thought it even associated because it was able to get the first couple of messages of the handshake. It did not actually complete the handshake, but we will see that this is an interesting case where we just need to capture the first couple of messages in the four-way handshake, and we can use that to recover the passphrase. So the access point is not having the same key now, not having the same passphrase. It's just that the client still thinks that the passphrase is the old passphrase, which is hello there, and so it was trying to do the four-way handshake with that passphrase. So let's take a look. So let's do aircrack ng. Okay, then minus w. And let's copy that. That's the rock you wordless. And yes, so it has taken a bit longer, but because it wasn't using that very small word list, but it has also found hello there. And so, hey, so this is a case of having an isolated client because the access point had just changed its passphrase, and the client still thought it was the old passphrase. Anyway, I'm going to change the passphrase to the new one in the client. We're doing that off camera. But once it's successfully done, we'll try to capture another four-way handshake, this time a proper one, with the new passphrase. Speeding up the video a bit. We go back there, and we see that we were a bit too late. After I changed the the passphrase, the client already got connected there, so we are not able to get a handshake, but we can induce it like we did before. So let's go induce the handshake, and we do that by air replay ng minus d auth 1 minus a 00 16 b6 01 07 7c minus c Okay, so now we got the handshake because it de-authenticated and then it re-authenticated. The client tried again. Alright, so now that we have that, the next question then is, which file contains the four-way handshake that we had captured? Let's see, it's test 203. And we're off! Aircrack ng is going through the words in the word list. While aircrack ng is plowing through the word list, we can feel free to scroll back and check things. And we can come back and take a look at more words flying by as aircrack ng is plowing through the word list. So it's taking some time because there's so many different keys. So we see that it's showing, like you look up here, the number of keys tested out of the total number of keys. So there's still quite a lot more keys to test, and it will take a while. So here's where we see that in general, unless we're very lucky that the word is near the beginning of the huge word list, in general it's going to take some time. And so it could be more efficient to use a specialized tool that takes advantage of the computational capabilities of a GPU, graphic processor unit, to speed up the checking, because this brute forcing is taking a long time. Speeding up the next 15 seconds of video. The chosen passphrase was somewhere towards the end of this rock your word list, so it's going to take another hour and 20 minutes almost. It's, based on the estimate here. This is the motivation then for using tools like Hashcat that can take advantage of GPU processing capability to speed up this process of guessing the passphrase through a brute force dictionary attack. In the last video, we changed the WPA2 passphrase from something simple like hello there, which is in rockyou.txt, and then we found that AirCrackNG was taking quite a long time to go through the word list and to try to find the passphrase. The reason is that it has to go through one by one and compute and compare for a match. Is there a way that we can speed it up? Because we can imagine that rockyou.txt is just one word list. What if the passphrase is not found there? We might need to use a much longer word list with many more words. Maybe even another thing is combinations of words. So what else can we do? It turns out that when we were just running AirCrackNG, it was using the CPU. Most operations on computers will be running on CPUs unless we arrange otherwise. So for example, there are GPUs, graphics processor units, that are available in many machines. Usually they are reserved for the computations for the display, but for certain kinds of operations, like these kinds of computationally intensive operations, it makes sense to try to run them on the GPU rather than the CPU. CPU is more general purpose. Can we run AirCrackNG on a GPU? Well, it turns out it's not so simple to just run any piece of software on a GPU, because these GPUs have specialized drivers and you need to do something a bit tricky. You need to do certain things in order to get software to run on GPUs. Generally then, if you want to do certain computationally intensive operations on GPUs, you would find that the best way is to go for software that is intentionally written to make use of the GPUs. Hashcat is one such example. Hashcat works with a variety of GPUs and it offloads computation of hashes, which would be things like passwords and so on, onto GPUs rather than to use the CPUs, which would be slower. So Hashcat can schedule these computations and it can also detect the various GPUs. So it is designed to work with GPUs and multiple GPUs, not just one. It is open source, runs on Linux, Windows, Mac OS. You can compile it to run on a variety of different operating systems. Now, it may not be so easy to get it running properly though, because there's various issues about drivers and so on. That's another matter. We will be showing some demos and you will see some of the challenges, some of the issues that are faced as we go through the demos. It supports a wide range of computations, so it is not just meant for WPA or WPA2, unlike AirCrackNG, which is more specific for Wi-Fi related cracking. Hashcat is designed to support various kinds of brute forcing, especially things like password recovery, passphrase recovery and so on, where the typical process is that you're going through a large word list and you want to brute force, you want to check. You typically then will be computing hashes again and again and again and comparing these hashes with some value that you might have obtained. In the case of our WPA2 cracking, this was in the four-way handshake file. So this process is quite similar to password recovery and various other computations for a wide range of scenarios. Another thing that Hashcat supports is rules. So there might be certain rules where you don't just use the word in the word list as the only possible passwords or passphrase or whatever it is, but maybe certain rules like you can combine, so you have combinations of these words and you also try combinations of these words. That makes it more powerful than if it were just to simply use straight direct brute forcing. How do we install Hashcat? We can find the Hashcat packages just by Googling, and there's different versions of them. So we will see when we go to the demo that sometimes some package might come with pre-built executables. For example, we will find that the latest one does not come with the pre-built binaries for Windows, whereas the next to latest one does, and so we would use that one just for convenience. There's also samples that come with these packages. We can also build from source, and so if we have time, we might do that just to show, like, to build on Mac OS. And generally, we're going to need to update various drivers and related bits of software. We will show that in the demos as well, because typically your GPU drivers might not be up to date, and then you might have problems getting Hashcat to work with those older drivers. Generally, the latest versions of Hashcat would like to work with the latest drivers to fully utilize the GPUs and the capabilities of these GPUs. A popular practice for using Hashcat is to run it in the cloud. For example, EC2 machines on Amazon Web Services or AWS. These are virtual machines that you can get on Amazon, and it's very convenient because if you just need to do something, you could just for an hour, you can start a machine for an hour and then you can stop it, and you just pay for what you use. It's also convenient because, for example, later we will see in the demos, when I am installing on my physical Windows machine, I might find that I might not have enough RAM on that machine and things like that because it's an older machine, and then Hashcat might not work with that. Whereas with EC2, you can get an instance that you know has enough resources and is able to run Hashcat properly. So we will show a couple of demos on Windows, because I think a lot of people would want to use Windows if they're not using the convenience of EC2 on AWS. So we'll show how to find the GPU that's installed on your Windows machine and how to install and run Hashcat. In this case, as I mentioned, my laptop didn't have enough RAM, and I thought, well, okay, I can go get more RAM, or I can just show you how to do it on EC2 on Amazon Web Services. I will also show a demo on that, and if there's time, also on Mac OS, how to install Hashcat. We will now demonstrate how to do a couple of things related to using GPUs for assisting in dictionary attacks against WPA PSK and WPA2 PSK. Firstly, we will take a look at how you would see what kind of GPU you have on your machine. Secondly, we will look at updating the drivers, and this is not going to be comprehensive. It's just an example. Depending on the GPU you'll find, it may vary, but you can Google around to find out how you might do it for your specific GPU. Anyway, then we will see how to download and use Hashcat. On a Windows machine, there are several ways to get the information about the GPU. I'm showing here a Windows 7 machine, and one of the ways, which is to run the DirectX diagnostic program. We do that by searching for DXDIAG for DirectX diagnostic. There we have found it, and so we can just press enter. That brings up the DirectX diagnostic tool. We can then go to the display tab, and there we have it. It's from NVIDIA, and it's an NVS 3100M. The version is 8.16.11.8955, so it's actually 18955, which is arguably a bit old. Now, how do we update the drivers or check the drivers? We go to the device manager. Display adapters, select this, right click. Well, let's go to properties. So let's see if the driver is okay. Let's try to update it. Search automatically. Alright, so you cannot find an updated driver. Let's hope that this driver version is okay for running Hashcat. we tried to update our selected the NVS 3100M. But if you're coming here the first time, let me point out some things, because you'll need to, for example, if you're using a notebook, it might initially be showing something like NVS series. Well, firstly you have to choose a series, so in this case it was NVS. But then within the NVS series, there's also the NVS series and NVS series for notebooks. At first I just selected NVS series, and I didn't see the 3100M over here. So I was wondering whether my GPU was somehow so obsolete that it was no longer supported by NVIDIA. And then I went back and checked, and I found that there's this NVS series notebooks. And this has the 3100M listed here. It's not the latest or top of the line, but at least it's still here. Then, yeah, Windows 7 64-bit is the right operating system. ODE, and then search for this. So it finds a relatively newer version of the driver, which is shown here. So 342, so that looks good. And let's download it. Agree and download. This user interface is not that great. It should have popped up some kind of box or something, but I can see a bit of a change in color here, so it kind of shows that it's doing something. There's something happening over the network. Finally, a couple of minutes later, see this. All right, so I can download this. It's done, so open it. Yes, I allow this. Norton says it's safe, that's good. And where do I want to save this? Yeah, this seems fine. We're going to skip to the part where the installation finishes. Great, the installation has completed successfully. And we can go check. Yes, so we have version 342. We now continue to see how Hashcat can be downloaded, and then we can begin using it on a Windows machine. Well, it turns out that Hashcat version 3.6.0, or at least the binary bundle that you get from the Hashcat website for version 3.6.0, just has the Linux binaries. It doesn't have the Windows binaries, so you don't find the .exe files. Well, perhaps someone has built version 3.6.0 for Windows, and you can find them somewhere. I did some Google searching, and after looking around for quite a bit, because it's kind of really hard to find, then I thought, okay, well, maybe let's just take a look at the previous version. I mean, version 3.5.0. And so I did that. Just go to download, and in there you will see that you will have the 32-bit and 64-bit version of Hashcat for Windows. So that's your most convenient bet at this time. Of course, later on, perhaps there's going to be other versions, 3.7, 3.8, whatever, and perhaps those will come with the Windows exe files as well. So once you do that, you can use a program like 7-zip, and you should be able to look for these Hashcat 32exe, Hashcat 64exe, depending on whether you want 32-bit or 64-bit. Now, Hashcat has its own format, so it doesn't take .cap files, but we can convert to the preferred format for Hashcat in several ways. And to see what are the current ways for doing it, we can do a Google search for Hashcat WPA2. Well, I did that, and and this is one of the first few results that came out. So it's from the official Hashcat webpage, and you'll see that there's this thing called hashcat.net cap2 HCCAPX. So anyway, the format that it needs is the HC cap X, I guess standing for Hashcat cap X. And there's various ways to do the conversion from cap. So here we will go to a website conversion where we can just upload the file. Now, of course, if this is sensitive data, you might not be really willing to do that, but in this case, it's just for demo purposes. So we are just going to try this one. And then convert. Save it. We have a couple of other files as well from our various experiments, so we will also go ahead and do them now. Convert. So this is test 202, and then we will do test. Strangely, it's not letting me save. Well, let's just move on to the next one. All right, so we've got a couple of files. And then, so this Hashcat 3.5.0. Okay, there's one important option that we need to know if we're going to be using Hashcat for WPA and WPA2. So if Hashcat 64.exe -- help, and the one that I want to show you that you need to know is this. Where is that? Oh, I saw it earlier. WPA and WPA2, so it's 2500. So it's -M to 2500. That's the important one you need to know for WPA, WPA2. So -M 2500. And then Alright, we don't have RockU here, but we'll just check with example dict. And ooh, device local memory size is too small. Well, that's too bad. What can we do about this? Stay tuned for the next video where we'll talk about some options. We continue our demonstration of running Hashcat on EC2. We resume where we left off in the last video. We just need to install some updates for the NVIDIA driver and related software. After that, we'll be all set to use Hashcat on this EC2 instance. So we want to get the NVIDIA drivers installed. NVIDIA CUDA toolkit as well. Speeding up the video. And back to normal speed as we finally approach the end of the updating. Now we can try again. Aha, so now because we have installed the driver, we can see the information here. We have the NVIDIA Tesla K80 indeed. And so now we're ready to proceed to do hashcat -I. Yes, much better. So now it sees the GPU from NVIDIA, the Tesla K80. And we can do some benchmarking just to further check that things are in order here. So we try to get the hashcat benchmarks to show up, but nothing happens. It seems that there's a problem. And perhaps it has to do with the fact that we just installed various updates and we had not done a reboot. Sometimes some other dependencies, some other things that are installed need reboots before they come into effect. Previously, we had updated the software on this EC2 instance, and the problem that we found was that when we were trying to do the hashcat benchmark, it just was hanging for a long time. And sometimes that's because when we first install new software, we need to reboot, and so we just did that. After this reboot, let's try again to look at the hashcat benchmarks, and hopefully it will be more responsive this time. Yep. We already have gotten further than we got the last time. So it's running a bunch of different benchmarks. You can get better performance with a more powerful GPU, but for our purposes this is fine because at least we know that it's running on the GPU and it's doing something. So then we can go ahead and try it on some real data and see for ourselves how much faster it is than running aircrack NG. Speeding up the video. There's many different benchmarks that Hashcat is trying. Anyway, we have seen more than enough for our purposes for today, so we will stop here. And let's take a look at what we have uploaded these files already into here. And so let's see how Hashcat will perform on these files. So remember -M 2500 for WPA and WPA2. And then we first try test 2.1 HCAPX with the dictionary RockU text. This was not even a challenge with aircrack NG, so we see that Hashcat found the passphrase hello there. Let's try with the other file, which is test2 tree. Oops, we haven't run it yet, so we need to run through it so that it will create the file, and then we can use the -show option to see what it found. So this one is taking a bit longer. We can look at the status if we want. So it shows you the in progress status. So if we can see the percentages, how far it has come. Can do that again. So it's about halfway through. Speeding up the video. Almost getting to the end. Let's press S one more time. Okay, almost there. Yeah. Approaching final key space. Okay, so we're done. So the status is exhausted. Hashcat was not able to find the passphrase in rockyou.txt. Now, this was a case where the passphrase is not in rockyou.txt, so it was not able to find it. But the interesting thing is that it just took like what, a couple of minutes, whereas aircrack-ng would have taken an hour and 20 minutes from what we saw earlier with aircrack-ng as shown in another video. So it went through the whole of the rockyou.txt very quickly, and this shows how much faster than Hashcat is compared with just using aircrack-ng. So with Hashcat, we're running on a GPU. With aircrack-ng, it's on a CPU. So we can see the difference. We continue our exploration of using Hashcat on an EC2 virtual machine, so that you can easily get a machine with sufficient GPU computing power and just have it running for as long as you need or as short as you need. In order to use Hashcat well, it helps to know certain concepts like the concept of the pod file and how you can remove it. And also it helps to be aware of some utilities that you can use depending on what you're trying to do with your password cracking. And these utilities are designed to be used alongside Hashcat to increase the power of what you can do. To demonstrate the so-called Hashcat utilities, we will show how you can generate HCCapX files from cap files using one of these utils, and the name of this util is cap2HCCapX. We have previously seen that you can indeed use a web-based service to convert from cap to HCCapX, but the official Hashcat website strongly recommends using cap2HCCapX instead. Hashcat utils comes with other utils as well. So these are multiple standalone programs. They do various sorts of things that can be useful to you when you are working with Hashcat. For example, to combine multiple word lists, to make all combinations of a short word list. And Hashcat utils are open source and freely available. Easy to install, as we will show in this video. We're back in the EC2 virtual machine that we have been using for demonstrating Hashcat. And the last time we saw a case where Hashcat went through the entire rockyou.txt list, didn't find the passphrase, and gave up. The point we were trying to demonstrate at that time was that it could go through so quickly, just within a couple of minutes, compared with aircrack-ng using a CPU, which estimated time was an hour and 20 minutes for doing that. But we still want to show that Hashcat is not just fast, it can also find the passphrase. So what was the reason that we couldn't find the passphrase the last time? The reason is that the passphrase was ABYGUR, well, let me write that, ABYGURL69, which is actually not in rockyou.txt as is. What do I mean by that? I mean, if we grab for this in rockyou.txt, we'll see that there are 4 words in rockyou.txt that contain this passphrase, but not the exact passphrase. So we will show how with rules we can overcome this problem. But first, I want to show you something else, because the last time I showed you how you can create a HCCapX file using a service. That's a website that will convert a cap file to HCCapX file for you that then Hashcat can use. But there's also Hashcat utils. So let's go do it that way. Hashcat utils is a set of utilities, and one of these, as we see here, cap to HCCapX, this is user generate.hccapX files. And so we will do that. We'll just follow this link here. Okay, latest releases. Latest release for Hashcat utils is 1.8. Then we go here. We're looking for the URL to clone. So clone or download. We copy this. And we go back to our EC2 machine. So let's make a new folder. Let's say call it Hashcat utils. Go in there. And we clone this. We just got a link from the website. So it's cloned in here and we can see, okay. Well, I guess we didn't have to make this Hashcat utils ourselves. Now we have Hashcat utils and inside Hashcat-utils, but well, okay, minor issue there. Then we can just build it. If we look in bin, there's nothing there at the moment. So you just go to src, and these are the source files. And there's a make file we can use. So we just make will do the building. So it'll make all the targets, and so now we see the various .bin files, including cap to hccapx.bin. Okay, go back. So now we have set up this new here where we have the .cap file, which has the passphrase abbygirl69, and so let's convert that to hccapx so we can proceed. We need to execute that cap to hccapx bin that we saw before. So the format is in and out. So test2, and then let's call it. So just like that, and we have it. You see some confirmation here that this came actually from an access point with ESSID test2. And it's returned the handshakes there, but it doesn't know what the passphrase is yet because it still needs Hashcat to do that. And so we can run Hashcat. So let's see. Yeah, we have that file already. So, okay. Hashcat minus M2500 test2 cap, and then we want to use rocku.txt, which is in the parent folder, and so we begin. There's this port file here, which from previous times when you run Hashcat, sometimes previous results might be stored already, so sometimes then it helps to remove the port file so that you can try again. And where is the port file found? It's in your home folder and then Hashcat. So if you look in there, there it is. So we can just remove that and then try again, because otherwise it thinks that all the hashes are found in the port file. Use ---- show to display them. Alright, so we have removed that. Now we can try again. We continue where we left off in the last video and conclude our demonstration of matters related to Hashcat here. And this time it's going to be unable to find the passphrase because the exact passphrase abbygirl69 is not in there. And now we're speeding up the video. It's on its way to exhausting the possibilities and giving up, but hasn't gotten to 100% yet. Okay, so it's exhausted as expected. I'll just demonstrate that if you add the word to rocku.txt, I mean you add the passphrase, now this is all at the end, so now it can go through again the whole file and then eventually it'll find it at the end because now we've added it. But of course, this is not the way that you would normally be using Hashcat because you wouldn't know what the passphrase is. You're trying to find it, right? So there needs to be another way, but this is just for proof of concept to show that Hashcat really can find the passphrase if it's in the dictionary file. About halfway through, we could have put that passphrase somewhere in the middle or maybe towards the beginning of the file and gotten quicker results, but anyway, Hashcat is fast enough that it just plows through rocku.txt quite quickly by itself anyway. Getting there. Yeah, we can see roughly where it is in the file by looking at the candidates that it's considering at any given time when we press the S key for the status. So yes, you see that it was coming to the end of the file and this range here had the last word, which was our correct passphrase, and so it's correct. So we can use this ---- show command because now it has the results in the pod file. So ---- show shows that yes, indeed it had found this. And of course, this is not the right way to use Hashcat. So we should really remove our passphrase from there. Delete, so dd write quit. So now it doesn't have, and we can go and again, we can try it again and it will not be able to find it. I have done that before, and so trust me on that, you can try it yourself. But to save time, so we won't run Hashcat again just to show that it's unable to find it. What we will do instead is that now we will show how we can use rules to let Hashcat try other combinations. Alright, so firstly we will do a simple rule that we know will work, because this rule is to remove the first letter of words in the dictionary. There are other rules as well, and we will show you what they are, but this particular rule is to do that, and it's a targeted rule just for quicker demonstration. Alright, so now to use rules, we modify the command here very simply, -r for rules, and then I put it in my rules.rule, so we just do that. And it's starting again. So again it has this pod file here, so we remove from the pod file. I mean, we remove the pod file and then try again. Now that was pretty quick because it didn't have to go through the whole rocku.txt file this time. You can see that it's using this rules, myrules.rule, and this time it was just a few seconds. That's because remember when we looked in our file, so once it came to this word and then it removed the first letter, it found the passphrase. So you didn't have to go through the entire file. There are other rules that we can use. Generally, you wouldn't use such a targeted rule because you wouldn't know that, well, just remove the first letter and you'll find it, right? So you can find other rules, pre-written rules files in this folder here. And a popular one is this best64 rule, so we can take a look at that. So we see various rules like nothing, reverse case. Nothing means don't change and use the words as they are in the word list. And special number append, special number append. So various rules, high frequency override at n, high frequency prepend. So various rules that commonly work to give various other alternatives, derivative passphrases from the list of words in the word list. And if we're curious how to write other rules, we can go just do a Google search and get the so it gives you samples like input word and output word. So do nothing, it passes it directly through. The one that I showed was this truncate left, delete first character. So password, delete the P. Right? You can have multiple rules. The only thing is that the more rules you have, the more time it will take to check all of these. We consider another kind of attack on Wi-Fi access points and systems, and specifically we will look at fluxion. Previously I had mentioned about honeypots and the motivations for why we might want to be doing something like this. These days people are using WPA and then WPA2 personal and enterprise modes instead of WEP. So a lot of the attacks that had been previously possible, like with WEP to get the key, would no longer work. We had seen also that now with the pre-shared key of WPA and WPA2, we need to use dictionary attacks, and this is not a very good way of breaking into a system because it relies on being able to guess the password. You check many different possible passwords, but these are things that are in a list. So if somehow the passphrase is not in the list, what can you do? This alternative approach of using something like a honeypot is to try to induce a human user to provide the passphrase rather than doing brute force through many different combinations. We then tied this with our other building of knowledge regarding fake access points, because we have been using Airbase NG for a number of different demos, and generally we have not been having a full-fledged rogue access point by just starting Airbase NG. So we don't have all the features that you find in a normal access point, but Airbase NG provides the minimum in order to respond to probes from stations and to get them to think that they are authenticated and associated with an access point. And the main reason is then to be able to capture certain frames that the client sent. In order to get beyond this, we can actually add additional features because real access points support additional features, and some of these are listed here: DNS, routing, internet connectivity, and so on. And then we can have more full feature fake access points, also known as rogue access points. Since these go beyond Airbase NG and provide IP connectivity, even a HTTP server, this allows it to be more powerful and allows additional capabilities like social engineering. So now we can have this rogue access point asking the human user for the passphrase and making it appear that it's coming from a legitimate access point. Humans are used to entering the passphrase at various points because with these pre-shared passphrases, sometimes you need to enter them into your machine. The machine might forget after a while because of some configuration issue. And so humans are used to doing that once in a while. They might not really enjoy it, but they're used to doing it. And so if you can get them to believe that that's what they're doing, then they would do it. And so then the rogue access point can capture that passphrase and can bypass all the dictionary attacks. This can also be used in conjunction with a DOF attack in order to capture the four-way handshake as well, to verify that the passphrase is indeed correct, because you don't want to be relying on the human to enter it correctly. What if they had a typo in their passphrase and then you think it's correct, and it's kind of troublesome. So it's good to be able to verify as well, and we can take advantage of the client software to participate in a four-way handshake if they have been de-authenticated. So is there a package that includes these things that we were just talking about? And yes, there is indeed. That's where we come to Fluxion. So Fluxion sets up a honeypot with these various features of access points so it can become a more regular, full-fledged access point. Host APD is a key part of it, and that's where it has the various access point protocols that are part of normal access points. Together with host APD, there are other pieces that you would normally find or that it might be useful for this rogue access point to have. So like an HTTP server, Lig HTTPD is used for this purpose. It also comes conveniently packaged with DNS and DHCP servers. So you have a whole bunch of things that will make the client feel at home and feel like it's really connecting to a genuine access point, where actually it's connecting to this fake access point that has been set up by us. Fluxion also conveniently runs a DOF attack, so it can also try to capture this four-way handshake if needed. And then it can verify the passphrase using previously captured handshake. Now, it doesn't reinvent the wheel, so we see that Fluxion is using packages and components that were created by other people. It's putting them together in a convenient way, whereas in the past you could do the same kind of thing, but you'd have to put together the pieces yourself. Now it's coming together in a convenient package with easy configuration to get this going. It uses tools like AerodumNG and so on, as we will see in the demo, rather than reinventing the wheel. So this is attacking the weakest link, as mentioned. So this is a form of social engineering, and it facilitates man-in-the-middle attacks, because you can imagine what you can do after this. Perhaps the users might go to certain websites, they enter passwords and login credentials and so on. So all kinds of things as a man in the middle. And it's still under development. It was, in fact, available from a particular GitHub repository, and then it was removed for whatever reason. So for some months it was not available from there, but you could get it from other sources. And then it was brought back up. We begin our demo of Fluxion in this video. And it's the first of 3 videos showing how to install and use Fluxion. We can get Fluxion from GitHub, and just by doing a Google search we'll find that we can get the URL. What it is, I'm typing here. So this is something that you just find by Googling for Fluxion, and it's not the original URL, but it claims to now be the official repository for Fluxion. So we start by doing this. The typical cloning from a GitHub repository. We're speeding up the next 15 seconds of video. So once that's done, we'll see that it is in the folder Fluxion, and we can go there. There's this fluxion.sh, which is a shell script, and that will check for things like dependencies. So let's do that. And it finds 4 dependencies that are not installed. Those are in red. We can get these to be installed on our machine as follows. So the script is install.sh sudo install-sh. Some of the steps might take a bit longer, but not to worry, it's all automated as we are seeing here. As part of the process, Fluxion might install additional software such as a DHCP server in this case, and it might open another window to do that. So we see that it's running some scripts in another window and doing installations on our behalf. In this window, we see that it's installing the ISC DHCP server for us. Host APD is also being installed by Fluxion for us. So we'll be patient and wait for the installations to finish. Now an HTTP server. PHP CGI. And if we click on here, we see that things that were already on here, it doesn't need to install again, and other things like DHCP, like HTTPD and so on, it's installing. Cloning into Revolver. Okay, so now we can try sudo fluxion sh again. Oh, wonderful. All the dependencies are there. So we can officially start using Fluxion. We are working with English, so let's choose one. Oh, okay, need to connect a wireless card. Now I haven't done that yet. Okay, connect, because I'm running this on VMware, so connect to Linux, and we'll start it again. This time it will find the wireless card and proceed further. Once again, language English. Do we want to scan all channels or a specific channel? We can just choose. So let's say all channels, and our familiar arrow dump ng display. We're speeding up the next 12 seconds of video as arrow dump ng listens. So I just turned on the access point test 2. Shortly we will see test 2 on the list as well. Yes, there it is. So Control C to stop. And now we can select 21 for test 2. So we see that it's numbered the different access points. So more specifically the different ESS IDs. So we see that test 2 is 21. And it has got the information that it's WPA2, channel 11, 54 megabits per second. It has the MAC address here. We already know how to do an airbase ng attack, so the reason we're using Fluxion is for this first option here, the recommended fake access point with host APD. Let's go with that. We have previously captured some handshakes. /root/new tree. Let's go back to the other window. Copy and paste here. Alright, so that's a handshake that it can use for verification purposes after it has somehow managed to fool the human user into giving a passphrase. A corrupted handshake! It turns out that this version of Fluxion had trouble with both test2-03.cap and test2-01.cap. In the next video, we will see a newer version of Fluxion that does not have this problem. We continue with our demonstration of Fluxion. The Fluxion project is in flux, so to speak, pun unintended, and So the URL that I showed you the last time, from which we got a version of Fluxion, is not the official URL. And I just checked that the official URL is back up. So it was down for a period of time and people were going to this other place to get it. So now the official URL is back. We'll try to get a more recent version of Fluxion from that URL. It is still in flux and still under development, but at least we get something from August 2017 rather than June 2017 as we had got from the other site. So just to be clear, this was the other site that we downloaded Fluxion from, GitHub Wi-Fi Analyzer Fluxion, and we're looking for this one, Fluxion Network Fluxion. All right, so let's do this, copy and paste. And we're cloning it into a new folder, new 5. Speeding up the video of it downloading from GitHub. So let's try again. Fluxion shell. The dependencies are okay because we got them yesterday when we were installing the other version of Fluxion. English this time is number 4. Okay, so we select number 4. Wireless interface, fine. And I know that test 2 is on channel 11, so I'll just specify that. Yep, it's there. Close the Fluxion scanner to continue. So let's Control C here. And we select number 4 for test 2. Now it provides 2 options. One is an evil twin access point and the other is a handshake snooper, not snopper. I think there's a typo there. So let's try the captive portal. So we see this captive portal versus the snooper. There wasn't the snooper option just 2 months ago. Now it's available. And we're back to the screen where we could select either a host APD or airbase ng rogue access point. So we choose the host APD. The path to the capture file. 1. Test 2-01. Let's do .03 -03 pirate recommendation. All right. We haven't created an SSL certificate, so let's do that. And let's select English, so that's number 7 here. At this point, Fluxion has all the information it needs, and so it is starting up its fake access point and the corresponding servers that we have installed earlier. And we're all set. So now we have to get a client that has previously connected to test 2 and that knows the new passphrase. So currently it's off, so let's go turn it on. The top left screen shows this client trying to get an IP address with DHCP. The top right shows one client for this access point, and the bottom left shows DNS queries. Looks like the client is taking the bait. So we see DNS. I have various windows open in Chrome, and it was asking for Google and whatever because those things are on the machine. And you see that the DHCP request, it was coming from this machine, this client, which is Daniel Wong 2010. It's a Windows laptop. So on the client machine, I'm having a browser, new browser window, and putting google.com in it. And we are seeing this screen where this is something that's coming from Fluxion. So it's from our fake server trying to induce the human user to enter the passphrase so that then it can be captured by Fluxion. So let's say we do that. Aha! So yes, Fluxion found the passphrase and verified it. It received the passphrase that I entered and saved it and compared it with the one that was found in the handshake in that file that we specified, and that it verified and the key is found as indicated here. So it didn't have to search through many different possibilities in a dictionary attack. It just captured it by inducing the human user to enter the passphrase, which I did, and then now it has successfully obtained the passphrase. In our previous video on Fluxion, we saw a demonstration of how Fluxion could be used to trick a user to give us the passphrase of WA2 protected access point. In doing so, we captured footage from both the client machine, which was a Windows machine, and the Kali Linux machine, which was functioning as a fake access point under the control of Fluxion. Now, since we had footage from both machines, we showed part of what we captured, but for example, we switched away from the client machine just before the user pressed enter or submit in order to go back to see what was happening on the Kali Linux machine with Fluxion when the submit button was pressed. So there's some additional footage that we didn't show in the last video, and we will show that. That will naturally lead to some discussions on ways that Fluxion could become even more enticing for the user, even more tricky. Because, for example, if certain additional things were done, it could make it even more difficult for the user to know that they were being faced with a fake access point and that they should not actually type in their passphrase. Induce the human user to enter the passphrase so that then it can be captured by Fluxion. So let's say we do that. Aha! So yes, Fluxion found the passphrase and verified it. It received the passphrase that I entered and saved it and compared it with the one that was found in the handshake in that file that we specified, and that it verified and the key is found as indicated here. So it didn't have to search through many different possibilities in a dictionary attack. It just captured it by inducing the human user to enter the passphrase, which I did, and then now it has successfully obtained the passphrase. So it's from our fake server trying to induce the human user to enter the passphrase so that then it can be captured by Fluxion. So let's say we do that. Aha! So yes, Fluxion found the passphrase and verified it. It received the passphrase that I entered and saved it and compared it with the one that was found in the handshake in that file that we specified, and that it verified and the key is found as indicated here. So it didn't have to search through many different possibilities in a dictionary attack. It just captured it by inducing the human user to enter the passphrase, which I did, and then now it has successfully obtained the passphrase. If we look back on the PC, it is just asking the user to wait while the password is verified, and it looks like Fluxion doesn't care anymore about the user because the user has been successfully tricked to enter the passphrase. So now they're just stuck here, and Fluxion does not provide additional screens and other stuff beyond that. It already has what it wants, but it's in a sense a proof of concept that now you can go do other things besides this. For example, the big access point can continue to provide internet access so that the user might not know that the passphrase was stolen from him. In this case, you might be kind of wondering also what's going on, and maybe you try again later. And as a human user, you are used to various sorts of errors, so you might curse your PC, curse something, and then try again some other time. So you might still not know, but anyways, this is what we see on the PC. And then on the Kali Linux side, back here with Fluxion, we see that the passphrase was found. For our convenience, also it even saves the password, so you can imagine that you're running this and you're off doing something else, you come back later, then you can go look at that file. So it saved the password in this file. So let's say we exit from here, it's successful, and then we want to take a look at that file. So we cd attacks captive portal netlog test 2. I'm just trying to press tab so I don't have to type out the whole thing. Oh yeah, because it's not a folder. What am I doing? cd to this netlog, and yeah, we see the file here. We'll do more on it, and let's bring this up to see. Yeah, so very convenient for us. We see the SSID, the BSSID of the access point, and the channel. It's also WPA2, and shows us the password. Exactly what we want. No dictionary attack was needed in this case because the human user helped us out in the process. And before we know it, we have reached the end of this course. As they say, all good things must come to an end, and it's been interesting going through all these ways to hack Wi-Fi networks and examine WEP, WPA, and so on. But now it's time to begin our wrapping up, and so I'll go through some summary and conclusions. So to recap why we're doing these penetration tests for Wi-Fi in the first place, one reason that we're looking at Wi-Fi rather than cellular or Bluetooth or some of the other wireless technologies out there is that Wi-Fi is quote-unquote easy to deploy. So we find that a lot of people set up Wi-Fi networks in their homes, in their small offices and so on, whereas the same people might not dream of ever setting up their own cellular network because they don't understand the technology or they think it's too complicated. Wi-Fi, on the other hand, is more of a mass market kind of consumer product, and people think of it that way too, and they feel confident to be able to buy some equipment, get the Wi-Fi network set up, and then begin to do wireless local area networking at home or in their small office. Many people who set up Wi-Fi networks then do it without understanding the security implications of these networks. This by itself would not necessarily be a bad thing if Wi-Fi came with good, strong security. Then people wouldn't need to really understand it, but they just get it set up and trust that the products that they're deploying have strong security that comes with it. The problem is that Wi-Fi, as we saw from the history of looking at Wi-Fi security was not always as good as what we can get with WPA2 enterprise mode. So we see that it's very possible to deploy Wi-Fi with weak security mechanisms. And we went through quite a few videos where we talked about those weaknesses of WEP and so on. and even WPA or WPA2 with PSK, pre-shared key. We showed how the security could be easily broken, and in fact that's also one of the purposes for doing penetration testing for Wi-Fi, to show whoever is owning the network, once you have their permission of course, that it's easy to do certain things like getting the password, the passphrase, using easily available tools that are low cost, and so within a short amount of time it's possible to break the security. Having a demonstration of the security weaknesses sometimes helps people to realize that they need to do something about it, and then you can recommend better ways to secure the Wi-Fi deployment. We have seen that we have a wide spectrum then of levels of security that can be available in a Wi-Fi network. You can go from something like open authentication, which is practically nothing, and to something very weak like WEP. And we can say, well, for authentication, for ciphering, rather than just one word WEP to cover everything. So we can also specify specifically what security services are using what. But anyway, since WEP was so weak, additional non-standard ways of doing things like MAC address filtering were added to the early access points, and you can still do them with more modern access points as well, but generally it's not a good idea to use MAC address filtering by itself. Just it should be used together with other mechanisms. Because of the problems with WEP, WPA, PSK, and WPA enterprise modes were introduced. PSK is also known as personal mode, with pre-shared keys where everyone is sharing the same key or passphrase. So clearly that's not very secure. It's better to use enterprise mode. The problem with enterprise mode is that it's harder to configure, and you need a radius server. Fewer people know how to set up a radius server properly in order to attain this higher level of security. With WPA2, you have AES, so that's stronger encryption than you get with WPA. And it also comes in two flavors, PSK and Enterprise. We saw the various sorts of tools that you as a penetration tester for Wi-Fi systems might be using. So suitable hardware and drivers where you have certain hardware that's easier to put into monitor mode so that you can see things that are going on around as far as in the Wi-Fi networks. Then a platform like Kali Linux, where you have lots of different software tools, and convenient, you don't have to go collect your own software tools, although you might still want to install certain additional tools. So we saw in certain cases that we installed Fluxion and Hashcat utils and so on. So you can still do that, but it comes with already a good collection, and occasionally you might still be able to install, you might still want to install other software, and it lets you do that. Running on a virtual machine has certain advantages, and Linux-based machine especially. So we saw various tools like AirCrackNG, Wireshark, Fluxion, and then we saw that something like Hashcat could be run separately, perhaps on some other machine which has more powerful GPUs, and we also saw how that could be done on an EC2 instance with Amazon Web Services. Because generally your Kali Linux machine might not be having those really powerful GPUs, so it might be a good idea to bring it to a different machine and do that. And finally, we come to the second part of the conclusions. We will be going through the things that we saw in the course and briefly summarizing and saying some concluding words about the different Wi-Fi security schemes that we saw. So let's take a look at what we saw in the course. Open authentication is doing nothing for authentication. Then there's the infamous WEP, and that can be used both for authentication and ciphering. Typically they would be used together, so if you're using WEP for authentication, you would also use it for ciphering, where ciphering is encryption to encrypt the data that's being transmitted. There's non-standard mechanisms like MAC address filtering, where by non-standard I mean it's not specified how to do it in the 802.11 standard documents from IEEE, but it's very common that that capability exists in various access points, so you can do some kind of MAC address filtering. Generally, it's a bad idea to use it alone, and you would normally want to use it in combination with other mechanisms because it's not very secure. MAC addresses are easily spoofed. Then, because of the weaknesses of WEP, there's WPA and WPA2. The main difference in WPA2 being the introduction of AES, Advanced Encryption Standard, which is very strong. And both WPA and WPA2 have the PSK, which is the pre-shared key, and the enterprise modes. There is the infamous WEP, or wired equivalent privacy, which was perhaps ill-conceived. It was meant to be just something that's equivalent to wired privacy, because wired communications has some inherent protection because you have to be physically in contact with the wire to see the signals, unlike wireless where it's inherently a broadcast medium. However, besides the inherent weaknesses in WEP, the implementations of WEP added additional flaws. So for example, the IV is not always changing in some implementations, so that instead of having a 64-bit key, you might end up effectively having a 40-bit key, that kind of thing. And many attacks have been discovered over the years, and not just theoretically, but practical implementations have also been made widely available. So in your installation of Kali Linux, for example, you can find the tools that you need to crack WEP protected systems pretty easily. You just generally need to capture enough frames with enough different IVs, and then you just process that with aircrack-ng, and eventually aircrack-ng will find your WEP password for you. The first attacks you might do might be cases where you are within range of an access point and can capture frames that are going between an access point and a device that's within range of the access point. However, we also saw that it's possible to launch attacks against isolated WEP clients because the clients also have the shared key. So it's a shared secret. So client has knowledge of it, and if somehow the client can be persuaded to send frames with different IVs, then that will also be sufficient in order to crack WEP. And so we saw attacks like Cafe Latte, Herte, and so on. In these, it would induce a client to send ARP responses by sending fake ARP requests and things like that. So there are ways that you can pretend to be an access point and then get the WEP client to then be sending frames that you need in order to crack WEP. So generally, we do not recommend using WEP. In your penetration test, if you find any Wi-Fi system that is still being protected by WEP, even if it might be the 128-bit version rather than 64-bit version, don't use it. So recommend that it be stopped and something stronger be used. We saw that with WPA PSK and WPA2 PSK, every device shares the same passphrase, which derives to the same pre-shared key. So already just from general security principles, this is not a good idea. As long as just one device is compromised and the passphrase somehow can be retrieved from that device, every other device becomes compromised. And we saw that you just need to capture one four-way handshake, unlike the case of cracking WEP, where you would typically capture thousands of different frames with different IVs. You just need one four-way handshake because the approach is different. Rather than doing some kind of statistical analysis and trying to get the key that way, what happens is that the handshake is just used for verification purposes, and the cracking approach is to be looping through a word list. So there are many files that have typical passwords that people might use. So just looping through the word list and then doing brute forcing verification with this handshake. So that's why this handshake is important, because otherwise you wouldn't know if you have selected a candidate passphrase that is correct. There's no way to verify. And one other thing about this four-way handshake is that even though the full four-way handshake is 4 messages, we don't even need all the 4 messages in order to do the verification for this way of attacking WPA and WPA2, because information that you need for verification is available in subsets of the messages. So let's say like 2 or 3 of the messages should be sufficient. And we saw that with Hashcat, you can even specify rules so that you don't have to just simply use the words in a dictionary, but you can combine them, process them in certain ways, and that makes it more powerful. Of course, it slows down the attack as well. With WPA2 Enterprise, or WPA Enterprise, that's where you get the most security, and it's highly recommended for any system that truly wants to be secure to go with WPA, or especially WPA2 Enterprise mode. Because now every device has its own username and password. It does its own individual authentication. So if somehow one device is compromised, the other devices are not compromised, and it's possible, for example, then to say that, okay, access point knows which one is compromised and then stop recognizing that. You can still use the system. And then it uses EAP, which is Extensible Authentication Protocol. So with EAP, then various kinds of authentication can happen on top of it, and not all are equally strong. It is therefore highly recommended to use EAP with some mechanism with a secure tunnel for end-to-end protection. And this will be end-to-end between the network interface card and the radius server on the other side. Examples of this are PEAP, which is Protected EAP, and EAP TLS, using TLS as a secure transport layer. We also saw that WPS is not recommended because it has great weaknesses, even though modern access points try to make it harder to do something about that.